Oh, Peter is in the Zoom. Great. If it, okay, great. All right. Okay, it's time to start. Hi, everyone. So I guess it's time to start. So first, welcome to this 3D Vision and Robotics workshop. And I'm Zhenyu Jiang, the host of today and also one of the organizers of this workshop. I'm a PhD from UT Austin, working on robotic perception with Professor Yike Zhu. Okay. So as the title of our workshop suggests, the focus is on the intersection between 3D vision and robotics. Since robots are designed to operate in a three-dimensional environment, it is natural for their perception systems to incorporate 3D vision. And in recent years, we have seen tremendous progress in the field of 3D vision, with numerous innovative methods and topics emerging. For instance, neuroimplicit representations, particularly NeRFs, have become popular representations for 3D objects and scenes. Additionally, inspired by the success of pre-training 2D vision models, large-scale 3D pre-training has been explored in order to learn more generalizable 3D representation. And coupled with the advance in generative models such as diffusion models and novel 3D representations like neuroimplicit representations, there has been a significant progress in 3D generative model as well. All these developments have undoubtedly elevated 3D vision to new heights. Simultaneously, the field of robotics has also made remarkable strides. One of the most notable advancements is application of large language model for robotics, spanning from high-level planning to reward learning. This has allowed for more sophisticated and efficient decision-making process in robotic systems. The foundation model philosophy, this thing's a little bit stuck. Yeah, the foundation model philosophy has also been utilized for learning general-purpose robots. Moreover, we have seen emerging research on agile and dexterous robots, ranging from quadruped robots to dexterous hands and humanoids. These developments have pushed the boundaries of what is possible in terms of robotic movement and manipulation. Up-to-date research in robot learning has significantly driven the progress of research on general-purpose robots. Throughout this workshop, we hope to explore ways to further push the boundaries of 3D vision robotics, addressing questions such as what representations to learn and how to learn them. How can we acquire data for learning robot perception in a 3D world? How to ground language and concepts in spatial reasoning? How can we build a foundation model for 3D vision and robotics? And what real applications will be enabled by new advances in 3D vision and robotics? Let me now provide a brief overview of our workshop schedule. The full-day event will conclude at around 6 p.m. We have 8 invited talks scheduled, each lasting about 40 minutes, along with a panel discussion. We have also accepted 14 papers for presentation in one of the 2 sessions. Each spotlight talk session will be followed by poster session. Our posters will be displayed on poster boards numbered 192 through 201. Our invited speakers for today include Pete, Tsu, Georgia, and Sarab in the morning, followed by Andrew, Anjo, Xiaolong, and Jitendra in the afternoon. And the panel discussion will be hosted by Aaron Lee, and our panelists will be Anjo, Pete, Sarab, and Xiaolong. So finally, I would like to extend my heartfelt thanks to all our speakers, authors, and organizers for contributing to this outstanding workshop. Without further ado, let's welcome our first speaker, Pete Florence. So let me give a brief introduction. Pete Florence is a research scientist at Google Research. His research focuses on topics in robotics, computer vision, and natural language, including 3D learning, self-supervised learning, and policy learning in robotics. His work has been recognized with multiple Best Paper awards. Okay, so Peter, are you ready?
I'm ready.
All right, one moment, let me.
You can hear me, Jen, you over there?
Well, I need to put put the Zoom on the, on the screen. Okay, stop share. And okay, I think we are ready to, can you share screen now? Okay, great, we can see your screen. All right, thank you.
Great. Okay, and I'm assuming everybody can hear me too. Please just stop me, Jenyu, if folks can't hear me or if something's wrong with the video. Good morning, everyone. I hope you're having a great time in Vancouver. I've been to NeurIPS in Vancouver in December, but I've never been in the summer, and I imagine it's lovely, and I hope you're having a great time. And I'm joining you here from home in San Francisco. And thank you for the intro, Genu. And I'm excited to talk with everybody today about a couple topics I wanted to do. So nerfing and embodying language models. So there's really going to be two overall parts for the talk today. The first part is two different ideas in NERF for robotics. And the second part is going to be the 3D story of Palmi. I won't have too many specific slides specifically on 3D, but I want to try to really help highlight the 3D parts of that story, because we did do some 3D neural scene representation fusing into language models in Palmi, and it's, I think, pretty interesting to compare with the other options we looked at as well. But first, though, let's do these couple ideas in NERF for robotics. So, Jen, you mentioned in your intro for the overall workshop, certainly one of the main areas of research in the past couple of years in 3D broadly that a lot of people have been excited about is NERF. And of course, there's many related methods to NERF. I think NERF itself is specifically large enough of a innovation, shall we say, that we can kind of just use a NERF as a catch-all phrase for all the other related methods. And of course, they continue to develop. Specifically in robotics, I think there's been a handful of interesting ideas of how we can use NERF in robotics. I think this continues to develop. I think NERF is certainly very powerful, and there's much more to extract from existing NERF methods and extend them more, potentially with feedback from sort of roboticists trying to use them in how we can make them better and better. This is not comprehensive at all, but I think here's a list of good list of a handful of key works in using NERF in robotics. And one thing I want to think through with you is, I would say, arguably, for each of these four, which were some of the first ones in using NERF for robotics, and this also would apply to a lot of other works trying to think about how do we benefit from the greatness of NERF in robotics. I would argue that all of these four use NERF to then bottleneck the entire method through some other 3D geometric representation, and then use that for the robot. And there's a lot of benefits of these methods, and they make a lot of sense. I do think that there are potentially other ways to use NERF too. And we'll talk about that in a moment, but just to go through what are the different 3D geometric representations that are used in these different methods. In iNERF, the whole point is to estimate 6 DOF poses. In this DexNERF paper, they condense everything down to a depth image and then do grasping from there. In this navigation paper, everything goes through an occupancy field. That's kind of a first-class part of NERF, but it is also somewhat separate of an idea from the actual NERF itself. And then in this NERF supervision paper, we go through key points to descriptors. So these are all other 3D geometric representations that we are taking NERF and bottlenecking through for the overall method. Instead, I don't think it is something that is uniquely necessary, but I think it's an interesting alternative to consider. The couple options that we're going to look at today instead send NERF into the sort of overall robot policy without going through some other 3D geometric representation. I think that's kind of interesting. So let's go through these first couple for today. So this first one is a collaboration with Chelsea Finn and her students at Stanford. So Alan and Mujin, and then as well as Leray at MIT. And this paper is at CVPR this year. And I want to call out that the poster is on Thursday, and Alan is there, Chelsea's there as well for the next couple of days. And you should go talk to Alan on Thursday. I'll give you the sort of prep of the story, though. So one thing that I want to do before we get too much into the actual method is just take a look at sort of what does this what generally we're talking about here in terms of what this enables on the robot. So shown here are some videos of rollouts of the resultant policy of training with this method, and a couple really nice things to highlight. I think first is that this is a grasping method, which is closed loop and real time. A lot of grasping work is instead not closed loop, but instead just looks at the scene and then chooses a pose and then moves to it open loop. This is instead closed loop. This is closed loop because we can move around the objects in the scene and the robot will respond and go and grasp things. The other thing that's really nice, and it's really hard to achieve these two different things in conjunction with each other, is that the method works considerably well for even very thin and very shiny objects. And that is really challenging for a lot of more traditional, shall we say, 3D methods, and especially for grasping. So I think those are two pretty compelling aspects to have together. And I want to talk about how this works. In order to appreciate the sort of whole setup here of this method, I think it's useful to go, sort of away from vision and back over into robotics for a moment and think about learning from demonstrations. So very common setup in robot policy learning from demonstrations. One very concrete example might be we teleoperate the robot and we have a bunch of expert demonstration trajectories and we learn some policy purely with supervised learning. So this would be behavior cloning. And that's a very concrete example. A key, also Genu, I see you're moving things around. Is everything good?
It's good. It's just someone trying to record the meeting.
I see. Okay, no problem. So the a very fundamental problem that is very well known, talked about a lot in imitation learning, especially doing supervised imitation learning, is the problem of compounding errors. Just so we're all on the same page of what the problem of compounding errors is, it's I think helpful to visualize. If we have some kind of expert trajectory of states that we would hope that a learned policy would follow, if instead our learner is not perfect at matching all of the desired actions that an expert policy would follow, instead what we get is a little bit of error on the first action that the learner uses, and then that little bit of error might cause even more error in the second action that the expert would use, and this can compound, and the sort of error from nominal trajectories grows over time. There's actually a lot of theory on sort of bounds of what this error can be. It can be very bad, especially over long horizons. And this is a key problem in imitation learning, again, probably initially popularized by this dagger method cited here on the bottom from Stefan Ross. And we're going to talk about that method that they came up with in that paper. So there's been a lot of proposed solutions to compounding errors in the literature. We'll go through a few. One of them is the algorithm, well-known algorithm called dagger, which was proposed in that paper that, again, I think is probably the one that popularized this whole concept of thinking about compounding errors. And the way that dagger works, I think it's quite simple, the sort of key idea in it, which is all we do is we just ask the expert what they would do in the states that the learned policy ends up at that we don't want the learned policy to be in. So we ask the expert what they would do, and the expert will show the learned policy how to correct these things. Now, this all sounds good and dandy, but what this means is that we have to take our original data set, and we don't only have our original data set anymore. We also need to add another data set where we have an expert labeling the on-learner policy data. And in some cases, like maybe playing video games or other things, this is very doable. But in general, especially for complex context-rich tasks like visuomotor manipulation, I think this is highly challenging. So it's both a nice idea, but it's also certainly not the end-all solution for compounding errors. Another idea, which is nice and very simple and has some nice both theoretical and practical properties, is this idea called DART. And the idea of DART is during the expert demonstration process, we actually go and inject noise into the teleoperator's actions that are applied to the robot. This is a concrete example of doing that. So what this means is the actual demonstration, the original expert data set is no longer the same. We don't have the same original expert data set that we had before. We instead have a noise-induced expert data set. What's nice is we only need to collect that one data set, and we don't need to do any of this funny business of having an expert label what the on-learner policy should do. But we have kind of, in some ways, affected the quality of our original data set. And this can be not necessarily advantageous. It's also hard to know what is the scale of noise you want to add. this is potentially kind of tricky. So just to visualize kind of in this trajectory view, what happens here with this Dart noise injection process, we force the original data set to make it so the expert has to show how to recover from mistakes. And with the data set now having many examples of how to recover from mistakes, the learner can learn how to avoid compounding errors. So that's Dart. Dagger and Dart, these are two common methods. A third method, which doesn't really have any formal name, and the first time I actually know of somebody doing this was we included it as kind of a side note in a paper, which was actually the last paper that I did in grad school. It wasn't the key point of that paper. It's an incredibly simple idea. It's like super obvious, so we didn't try to claim it as a major contribution, but I think it's actually pretty useful. We can call it noise augmentation. Kei Ke had another paper where I think she independently came up with the idea, and the focus of her paper is on this concept, and she has a very nice analysis of it. I cited her paper at the bottom as well. So I think we can call it noise augmentation. And let me show you what it does. But before, I just want to call out that an excellent part of using this method is that we don't need any data, and we don't affect the original expert trajectories. So we still have the original expert trajectories. There's no quality degradation there, and we don't need to collect any new data. So it's very nice and simple in that way. It's kind of the key advantage of it. So the idea behind this noise augmentation is to take that expert trajectory and don't collect any new data, but just through pure augmentation, imagine that we had messed up trajectories and also imagine how to correct them. And there's various details of how to do this. But we can kind of concretely walk through this as saying, okay, we have some state ST, and we're going to add noise epsilon to it. And then we're going to compute what the corrective action would be. In the general case, you can do this with kind of some noise distribution and a perfect inverse dynamics model. So let's add that to our little visualization here. So if we have some noisy version of state 2, then we can compute how to correct back to the nominal trajectory that we want to be on. Or we have some other noisy state, and we do this for all the different states in our data set. Okay, that's great. And what that means is when the learner is rolling out its learned policy, when it messes up, these messed up states that it ends up in are sort of in the region of attraction of the augmented states in our augmented data set. And so purely through this way, we can actually teach the method to recover from mistakes just through augmentation. In terms of the noise scale, even just a very small amount of noise can significantly help here. This is a table I just pulled from my paper from a while ago, where the details don't matter too much here. The point is just that the numbers difference in this case was massive. Like basically, this trick alone took the method from not working at all, 3 to 5% success, to 95% success range in certain cases. So it can be really massive. And I remember the noise scale here was just, standard deviation on the scale of 1 millimeter. So very, very tiny. This is not imagining huge errors, just very small errors that can avoid compounding over time. The major limitation, though, with all these prior uses of this method is that we only ever applied it to state observations. Both in my paper and in Kei's paper, is only ever applied to state observations, so nothing visual. And that really kind of has prevented it before from being something that is more a generically useful method. Instead, Dart and Dagger, you can use those with visual observations, no problem. But this has been a key limiting factor. And that is something that we look at resolving in this NERF in the palm of your hand work. So imagining new visual observations, that seems like that's a pretty good fit for NERF, and that is exactly what we do. So the idea behind using corrective noise for offline vision-based imitation, which is what we do here, with a bit of a focus on closed-loop 6-off grasping tasks. If we think about, here's just a concrete scene. How can the robot grasp the wine glass? We've got a wrist-mounted camera here. The key insight is that the changes in state, if we have a wrist-mounted camera, equate to just different camera views. And that's a really good fit for novel viewpoint generation methods like NERF. Note that it does mean that since most novel view synthesis methods especially work best if the scene is static, we're going to stay in static scenes during training. But what we're just going to do is we're going to imagine different perturbed wrist camera observations, and we're going to compute, since we have all the states of the trajectory, we know how to compute the corrective actions to get back to our nominal trajectory. and we're going to apply this feedback augmentation method. We call this Spartan. It has a nice little acronym, synthetic perturbations for augmenting robot trajectories via nerve. Just to give an example of how large the scale of these synthetic views look like, here's what some of them look like both in simulation and in real. As you might know, NERF is especially good at doing kind of mostly interpolation, shall we say, view synthesis rather than extrapolation. And that is a great fit for this application because we only really want to do views that are very close to our original training set, just maybe slight modifications of it. So it's really in a good regime for NERF to be working well. And then I'm about to show you a bunch of simulation experiment results, and I just want to give you a visualization of what these simulation experiments kind of look like. So this is a simulated environment from one of Leroy's prior papers. So we look at the results. I think the quantitative results really tell a pretty compelling story, I think, which is if we look at a few different comparisons here, all in this not too big, but very information-rich table. The first is that just doing these synthetic perturbations, we can get an RGB-only grasping policy. And this, by the way, is on complete withheld test set objects. So there's this is generalizing quite well. So this is on grasping objects that are not in the training set, a complete, entire, actually different data set, not just a test set of that data set, but a completely different data set that it was trained on. We see a pretty substantial increase in the RGB only grasping on these objects. So increasing from 29% to 75%. That's a pretty sizable increase there. The only difference between those methods is just using these synthetic perturbations with NERF. Another point is that we can outperform the sort of DART style online noise injection when we have the same number of expert demonstrations. And the reason there is because we can just increase purely through feedback augmentations as many imagined trajectories as we want. If we instead limit the amount of different imagined views, then DART and Spartan you would expect to be similar, but that's not really kind of the important comparison. It's a useful comparison to think about, but the one we're showing here is where we have the same amount of expert demos. And Spartan, we can arbitrarily make that as many augmented demos as we want. So that's, again, I think quite an advantage. It also can even start to outperform methods that use depth cameras, including the DART version of those. So this is showing where NERF is there. This style of using this augmentation together with NERF is starting to outperform grasping methods. Typically, grasping methods, especially in simulation, work very well with more raw 3D representations. They just generalize super nicely, but we can start to outperform those as well. And it even starts to do quite well compared to methods that use additional online data. So doing like online reinforcement learning methods, which would need to collect millions of additional environment interactions. So quantitatively, the results are really quite nice. And I think this is a pretty rigorous set of evaluations that we're done here. In the real world too, it can work quite well. So this is even just grasping from a pretty small number of demonstrations. Here, the robot is grasping a banana with 14 demos. Here's the vanilla BC method on the left, Spartan on the right. This is actually a pretty tricky object to grasp because you can only grasp it from a very select set of orientations because it's too wide for the gripper and on the other orientations, this thin box. You can see the vanilla BC method when it does fail, it looks like these very typical failures that we get with compounding errors where it just kind of ends up in a funky spot and it doesn't know how to recover. Whereas on average, Spartan method is much better at sort of recovering from these. Here's another one on the top. This is a very thin and very shiny object. This fork, again, can get pretty nice grasping results. And the wine glass is both very thin and very transparent. Again, very challenging for a lot of different types of traditional methods. Quantitatively, in the real world, overall a nice boost from using Spartan for the real world results as well. And again, this combination of closed loop and real time together with thin and shiny objects, I think is a pretty nice combo. So that was Spartan. A couple things I want to note is, as we were talking about before, instead of going through some intermediate 3D representation, here we are using NERF to offline synthesize a robust RGB only policy. So all the NERF goodness gets encoded into the weights of the policy, and there's no NERF training or inference required at robot policy inference time, which, as you know, sometimes these methods can be computationally intensive. So it's nice that there's nothing required, anything at all in that regime at policy inference time. And then in terms of limitations, I think good to point out, one primary area, would love for people to think about extending it, would be to get this to work in more fully dynamic scenes. Again, we sort of made the assumption that at training time, the scenes are going to be pretty static. The policy can then generalize to a little bit of motion, but it's not really intended to work with very dynamic scenes. It's a definite area for future work. So the next NERF in robotics paper I want to talk about is this reinforcement learning with neural radiance field paper. This was a collaboration with Mark Toussaint's lab at TU Berlin, led by Danny Dreiss. You'll hear more about Danny with the next paper I'm going to talk about as well. And then we also had Yunju from MIT working with us as well on this one. So RL with NERF. So a couple key ideas here to think through. One is, it might be a pretty nice idea for robots to model the world with NERF. And that sounds good, but it's not clear exactly what we want to do if we model the world with NERF. We can synthesize views, but then it's kind of tricky to think about different ways to then just directly use that for having the robot use that for a policy. Another idea that we are going to build on is modeling the world as a latent condition NERF. And this was, as far as I know, first done in the NERF in the Wild paper. Here, the things that change about the scene in this visualization on the right are more of like weather and lighting effects, things of that nature. But we're actually going to use this to model other very important types of changes too, which we'll see, which includes actually, for example, objects moving around or objects being present or not being present. And that is the key idea of NERF RL, is to use the latent code of a latent condition NERF as the scene representation for policies. We use this for reinforcement learning, but you could use this for any type of policy learning that you'd like. And this really is the key idea. And I think this is a actually super general idea. It seems to work very nice in these experiments from this initial paper. And it would be one that I would definitely be curious to bet on more as we do more in this area. So in addition to latent condition NERFs, which again, as I mentioned, is from the NERF in the Wild paper, another key idea that I just want to acknowledge, the pixel NERF, there's a couple others that came up with this, is not just having a latent condition NERF, but have a latent condition NERF that is conditioned on, shall we say, current images. So image conditioned latent NERFs. And this is a key idea which then allows us to adapt the latent condition NERF to observations that we're seeing now, so to speak. This is going to be very enabling for us as well. So the overall key process of NERF RL is all, I would say, visualized in this one key figure. So there's two overall steps. The first is that fully offline, we're going to train an encoder decoder where the decoder is a NERF and the code is the latent space that we're later going to use for the policy. But this first phase, we have multiple different views. We're going to have, if we want, we don't need them though, we can have masks for these different multi-view observations, so masks of different objects in the scene. Again, we don't need them though, but they can be nice. We can use those if we want. And we're going to train this. We're then going to freeze everything. We're going to freeze the encoder and the decoder. We're actually going to throw the NERF decoder away, and we're only going to use this encoder. And we're then going to train RL policies on this frozen encoder. So this is the overall process. What does some of this look like? How do we train this thing? These are some simple simulation experiments, but this is a gist of kind of the variations in these ones. So this is this sort of three-dimensional mug hanging, shall we call it, experiments where we have a mug. The mug is actually varying in a few different parameterizations of its geometry. And then there's also this hook that it's supposed to get onto that is also varying in different aspects of the geometry. We send a bunch of different input views sampled all over the space to train the encoder decoder of the NERF. And then we would later train RL policies on this. So this is using PPO to do reinforcement learning, and it has a dense reward telling it to how to get the mug on the hook. And this is an example of both the resulting RL policy, which learns to put the mug on the hook, which is what we would hope. Great, RL works. And then also on the right, this is showing what the NERF reconstructions look like. So very nice. This is, again, a very simple synthetic environment, but very nice dense reconstructions in terms of novel view synthesis of these environments. Here's another one. This one is also, I would say, another pretty simple environment, but it has a couple key aspects of challenge. So one is that in this one, we have either a blue or a yellow block. So we can have objects either be present in the scene or not, and that will all work fine in this framework as well. And in this one, the policy is going to learn to, if it's a yellow block, push it to the yellow side, and if it's a blue block, push it to the blue side. So there's actually it seems simple to a lot of people, but some type of very single point of contact pushing task is actually pretty tricky for policies to learn. You need a lot of feedback. This is something that RL can do quite well. Great, RL works. But it's nice as well. You can see on the right, we get these really nice reconstructions, and the RL policies can train very well on this frozen NERF-trained encoder. More specifically, though, just that it works, is it actually seems to work very well. So in the experiments, we found that these NERF RL style of training can actually outperform things, including like the ground truth states of these objects, where the ground truth states, since there's variation of different shapes, they're sort of expert knowledge chosen key points. Also works better than a couple other different types of autoencoder or contrastive learning baselines. So that's kind of the key takeaway. This seems to work very well in these experiments as being a representation for reinforcement learning. So again, I think it's interesting to note, this uses NERF offline to guide an image encoder to produce a good latent space. And these are the same 2 points as with our last method. The NERF goodness gets encoded into the weights of the policy, and there's no NERF training or inference required at all at robot policy inference time. I think these are both really nice properties. Another sort of just like looking back at this method aspect is this is very similar to a super classic style, or maybe classic's not the right word, but been around the block style of doing policy learning, which is we train an autoencoder and then we just use the encoder for policy learning. This has been done many times. Here's a couple of key references, but the key difference with this is that the decoder is a latent condition NERF. So some limitations. A primary one is that, I would say these experiments that we showed were still very much in the kind of simple simulation environment regime. And in practice, it might need a fair bit of work to get this to work sort of in the real world, especially, shall we say, in the wild. I think in the real world, in kind of more constrained scenes, this could actually work quite well. Danny has some results in a related paper doing more dynamics rather than RL, that it can work quite well. But in the wild, it might be pretty tricky. So I think that's a great area for thinking about for future work. Okay, looking at time, I have one more thing I want to run through, which is PAMI. So PAMI is an embodied multimodal language model. This is work with a bunch of colleagues from Google listed here. And there's a lot of different aspects of PAMI. We have been very excited about this work. On the one hand, PAMI is one model that does embodied robotics tasks, vision language tasks across multiple robot embodiments and across multiple modalities, including 3D neural scene representations, which I'll show you. A key aspect of the experiments that we saw with PAMI that we are excited about as well is that we get significant positive transfer from other domains, so vision and language, into the embodied domain. PAMI turns out to be a pretty competent visual language generalist and gets state-of-the-art on the OKVQA dataset for our largest 562 billion parameter model. We also saw some interesting aspects of minimizing catastrophic forgetting with scale, and we get some emergent visual language capabilities like zero-shot multimodal chain of thought. This is kind of the overview of what PAMI is and some different things it can do. Where in the middle, here we have kind of a simple architecture visualization of the key idea, shall we say, of PAMI is having text be encoded together with other modalities into a language model, which we all train together. And then we use this for embodied tasks as well as general visual language and language-only tasks. Here's a couple examples of the multimodal chain of thought capabilities that we are able to see with PAMI, which, as far as I know, is the first zero-shot multimodal chain of thought capabilities to just sort of emerge from a large language model that had been adapted to be multimodal. So on the top left, this is a picture of Kobe. The prompt is, given this image, question how many championship rings did the player on the left win in his career? Answer, we can prompt it to say, let's think step by step. We never trained it with any of these types of traces, and the model can just respond by saying, Kobe Bryant is on the left. Kobe Bryant has won 5 championship rings. On the bottom right, this is another, I think, very compelling example. We actually did not train the large PAMI model at all on any multi-image examples, but we can get zero-shot generalization to multi-image comparative reasoning. So in the bottom right, this one is photo 1, insert the first image, photo 2, insert the second image, question what is in photo 1 but not in photo 2, answer let's think step by step and explain, and the model can just respond. Again, it's never been trained ever on multiple image examples, and it can say photo 1 has sunglasses on top of folded clothes, photo 2 does not have sunglasses on top of folded clothes, therefore sunglasses are in photo 1 but not in photo 2. Some other examples here as well. For real robot results, in terms of time, I want to get going, so I'm actually going to skip them, but there's a bunch of nice ones at our website. I think it's the best place to see them. Maybe if we have more time at the end, I'll come back. To cover some related work, just mention some things briefly. There's been a lot of work, and actually, Jen, you mentioned some of this in your intro, in using LLMs for robots for high-level planning. A key difference, at least with work from our own team, and in contrast to a lot of other works that have been done in the field, with PAMI, we actually have a multimodal LLM as opposed to a text-only LLM that we somehow graft other representations into text. With PAMI, we directly train a multimodal large language model. And this work is very much enabled by the advancement of making language condition policies work better and better. So PAMI does not directly output actions to run on the robot, but rather outputs short horizon language instructions that lower level policies would then run. There's a ton of other related work generally. Also, I want to just briefly mention as well in multimodal language modeling. One particular one I want to highlight and give some attention to is this Frozen paper. It didn't necessarily have fantastic quantitative results, nothing state of the art, but it was a really interesting study and one of the first looking at just directly graphing vision encodings into language models. A lot of interesting results there, as well as there's a bunch of other multimodal language models that have come out over the past year. Flamingo, another very pioneering one. Poly, another Google model, state of the art on many tasks. Blip2 is a really nice model from Salesforce. Cosmos One, Microsoft, GPT-4, OpenAI, of course. These are all in this category of vision and text models to text. Another very relevant and inspiring work here as well I want to acknowledge is the Gato work from our colleagues from DeepMind as well. Okay, so a couple key questions with PAMI that we looked at in this paper. So one, very precisely, is can multimodal features be input to an LLM while leveraging the generalization of LLMs from body reasoning and planning? A second one is looking into different types of multimodal input representations, which I can show you more about. And the last one is just sort of other key aspects of training these models. Can the LLM be frozen or fine-tuned? What type of pre-training is best for the encoder? Sample complexity, things like this. One more actually set of research questions as well is around large scale. So scaling the model, scaling the language model, scaling the VIT, scaling the tasks, and things that sort of emerge from that. So minimizing catastrophic forgetting and other capabilities like zero-shot multimodal chain of thought. So a concrete way, I think, to think about, what are we sort of after here with some of the things that we do with PAMI, specifically in the embodied domain, is we want to take some language model and have some input long horizon, big picture goal, like how to move the yellow block on top of the blue plate. And then we want the model to come up with a potentially very complex plan that is required in order to achieve that goal. So like this example, output text on the right. But we want to ground the language model directly on observations of the world. So we want to be able to input the current views of the world into the large language model. You might think about how would we do this? What a lot of prior works have done is looked at describing the world in text and just putting into the language model. And this might work okay for some scenes, for some types of applications you might think about, but in general, this is pretty tricky to do. think about trying to describe exactly such that you could sort of paint this picture, for example. And this isn't even a necessarily super complex robotic scene, but it's one that's sufficiently complex to, okay, it's kind of hard to describe in text exactly how this is all put together. An image is worth 1,000 words. So we're going to look at learning an encoder directly from visual observations of the scene into the language model. And we look at a few different things here. So not just actually visual observations, but also using raw state observations, as well as pixels or pre-trained 3D neural scene representations. We also look at fine tuning or freezing the language model, a bunch of things like that. A visualization of how PALMI works, and to walk through a little bit of the details. If we have some text and we tokenize that into some text tokens. So concretely, these tokens might be something in RD, like for PALM8B. This is a 4096 dimensional vector. We have the sequence of all these 4096 dimensional embeddings, and we're going to throw that into PALM. And we're training a prefix large language model. So we have some sort of prefix like how to grasp the white object, answer, and then we're going to train the model to complete these next tokens. So this might be what a long completion looks like for this example. But then when we do the grounding of observations into the language model, we can think about having some vision observations that go through some encoder. And we are going to map the encoder also directly to the same dimensional space as the text token. So we're going to use a sequence of these. We use 256 for each image. And these are going to be the same dimension as the text tokens. And we're simply going to inject them into the language model and train through the encoder and potentially through the language model in order to get this whole thing to predict these text tokens on the other side. So that's the gist of making PALMI a multimodal vision language model in one case. However, what we're going to do is we're going to interleave these images into the text. This is something as well done in papers like Frozen or Flamingo. So we're going to say, okay, given this image, now this image is interleaved within the text. This helps in these sort of downstream emergent properties like multi-image reasoning. Given this image, how to grasp this object, this is how we generally would form this prompt. A little bit of the 3D and actually object-centric things as well. This is something that we also studied in PALMI. It ends up not being the main story of PALMI, to be honest, because PALMI ends up being quite compelling at just sort of the general nothing fancy needed vision case. But one thing we looked at as well is using the large language model to have object-centric representation such that it can refer to entities. So what we can do is we literally say in the prompt, object 1 is, and then we insert the tokens of one specific object. In this case, we would assume that we have object masks. Then we can say object 2 is blank. What's nice here is that then the outputted text can refer to specific objects because it has been grounded on these specific objects through the formation of the prompt. And this can help, for example, if PALMI is trying to communicate with a lower level policy and it's hard to describe in text what it wants to do. Let's say there's a bunch of different objects that all look similar. It can be hard to describe in text how those different objects are distinct from each other, but we can just have these multimodal tokens that are grounded specifically on ones that it's trained to do. And this is where the 3D neural scene representations came into the PALMI experimentation, because we wanted to be able to train these object-centric representations fully autonomously without any type of object mask. And the way we're able to do this is with object scene representation transformer. This is a work from Mehdi on our team. And so similar actually to NeRFRL, what we do is we train the OSRT encoder decoder, then we throw away the decoder, and we insert these slots as these object-centric representations into PALMI. And that's how that works. So a couple minutes, I'm going to try and leave a couple of minutes for questions. So with that in mind, I'm going to kind of do some skipping, but I do want to highlight one of the key results, especially with respect to the 3D part of PALMI, is that this OSRT style of pre-training, that's shown on the bottom here, can get very compelling results. This is even in a very low data regime where we only have about 100 examples for these different planning tasks. Very compelling generalization using these OSRT pre-training style. The sort of however, I would say, and it depends on what your preferences are, OSRT, that doesn't need any large-scale pre-training vision data. It gets quite good results through the structure of that model. But another very compelling option is to use a massive vision transformer trained on billions of examples and co-trained with all of your vision language data and all of your different robot data sets. So that's that VIT4B mixture, full mixture line. And that actually ends up getting pretty comparable results on not all, but many of these different tasks shown here, 74 to 76. That's not a huge difference. 74 to 82, that's a little bit larger of a difference. But this actually really, this large scale vision pre-training also really helps these results. And if the line just above it is VIT4B without all this vision pre-training, nowhere near as good results. So basically the point here is that either using some type of structure like OSRT or doing large-scale vision pre-training, both, if applicable, are very effective. The thing is, though, we can easily just apply this large-scale vision pre-training to any environment without needing any domain-specific data. That's kind of the challenge of the more OSRT style, is we need a ton of domain-specific data. So there's key trade-offs there, which we can talk about maybe at the end. I'm going to skip some of this, skip what the training mixture is. You can look up in the paper. We ran PAMI in a bunch of different robot environments. We got, I think, really compelling transfer results from different domains into the embodied domains, skipping some other things for time. PAMI is a really good visual language generalist, again, sort of state of the art at OKVQA, also pretty good results on data sets like VQA V2 and COCO, although not quite as good as models like Poly. There's plenty more of these zero-shot multimodal examples on the website. The scale catastrophic forgetting thing is really interesting. And jumping to the end, PAMI is an embodied, an investigation into embodied reasoning as vision language modeling. We looked at a bunch of different types of transfer. PAMI is a competitive general visual language generalist. And we looked at other input representations besides just raw vision. And the sort of 3D question I would encourage people to think about, at least it's something I think about quite a bit, and I think is pretty compelling to wonder where this goes, is that large scale, massive scale, billions of images, 2D vision only pre-training is extremely powerful. And it's interesting to try to capture sort of the best of both worlds. So 3D, often it's not really a thing at the moment. It's at least not nearly as common as it is with just 2D images to do that level of scale pre-training. But I would suggest that that could be a quite compelling area for more people to be working in, which is truly large scale 3D generative modeling from images or other raw representations. So with that, I will close. And if we have any time for questions, I'm happy to take some questions.
Thank you, Fit. And do you have any questions? Through Zoom or like through the. If you have any question, you can come up to the microphone and directly ask. One moment.
Yeah, nice talk. But a question about really the representation. If you look at large language model, you don't explicitly represent concepts and like relationship, right? Do you think for robotics you actually do need like these object-centric representations, like have these slots and explicitly?
Yeah, it's a great question. I think that depends on your philosophy. I would say I'm open to different philosophies, but I think maybe the one that's hardest to argue with at the end of the day is just run some quantitative experiments of trying one version versus the other, and that's what we try to do. And I think actually, especially if you have massive enough pre-training, both on the language and vision side, you can do quite well without any type of object-centric representations. Arguably, you could say language itself is really nicely kind of a object-centric representation, so to speak, but it can be trained just from large-scale data. But the object-centric versions that I talked about as well can have advantages. Both can work. But yeah, I would not underestimate the value of, not designing anything specifically object-centric and just training from massive scale vision and language data. It is quite compelling. Yeah.
Right. I guess, yeah, we don't have time for more questions, but there are a few like questions over Zoom. Maybe, yeah, I guess maybe you can discuss this offline by sending emails to Pete. And again, thank you, Pete, for your great presentation. And thank you.
Thanks, Jenny, for the invite.
All right. Okay. Now let me rest my cursor. Okay. Okay. Our next speaker will be also like online, but it's so, and he sent a video for the presentation, and I think he might join the QA session later. So yeah. So first, a brief introduction to Wu. Wu is a professor at Shanghai Jiao Tong University, and he has won Best Paper Award at Non-Photorealistic Animation and Rendering, and one most cited paper among all papers in SIGGRAPH in recent years. His research interests fall mainly in computer vision, deep learning, deep reinforcement learning, and the robotic vision. Okay, now let me play his video presentation. Okay. I think this comes to a moment, sorry. Oh, here's my. So it's a little bit confusing.
High learning efficiency. I come from Shanghai Jiao Tong University. First of all, I will introduce the background. The advantage visual guidance grasping ability are recognized by early human and make tool to technique becomes possible and believe the facility the equation of human. But however, the robots fall far behind human in visual guidance grasping ability. First of all, the contact model is still unknown, and the object shape is unknown, and the scene is cut. Variable of the mechanical design and make this make robot general grasping difficult. So my research objective is to make robot with human level general grasping ability. We emphasize the capability of the grasping algorithm in efficiency graph learning. So my talk contains 4 parts. First one is the benchmark and how to benchmark grasping in computer. And the second one is methodology. The methodology, we propose a new methodology to make the grasping in the deep learning more easy. And another one is any grasping. We hope finally you can grasping any objects in the general manner. The next one is we file can make the grasping adaptive to different different quicker. So this is my talk content 4 parts. First one, I will discuss the benchmark. As we know, we went with the discussion the grasping problem. We also need to make a good benchmark. But we always making the real robots, so it's not efficient. We try to build a benchmark, make the benchmark the robots grasping problems more easy. For the background, human can easily use the parallel grapher for grasping easiness can detect, human can detect in the vision, detect the grasp holes in the very short time. But until the 2019, until the 2019, the robot still take about 10 seconds to detect a grasp holes. It's also not very accurate enough for general object detection. So for the general object grasping, in the deep learning time, the grasping holes detection is learned in the data-driven manner, and we collect a large scale of the data set and train in a neural network. And this is the pipeline. And also we input the single view RGB image, and we get some grasp post detection, and finally we output the grasp post density, and we hope this pipeline is very general. Let's say we even for the unseen object, we can easily grasp to detect the grasp post, and not all and is very efficient. It's very fast in the short time, even can equal to human level to detect grasping post. So for the general grasping, first of all, we say we should build the data set, right? There's several important data sets for the grasping. For example, there's about 1,000, more than 1,000 objects and 2,000 objects in the EGAD, and even more set about 8,000 objects in a bigger data set. So and with more and more objects should be, so this given this logic, we should collect and we get the, so if you want to get more and more objects, it's very difficult to collect in the real world. So we get the data label in the simulation. We can no choice to get the more data labeled in the simulation, and training the simulation and testing in the real time. Okay, this is also we think we can some assumption for this program. Let us to review the assumption. First of all, we will assume once the first assumption is that the one largest data set equal to which collect the more objects, and the reasoning we need to so many objects. We cannot only build in the data in simulation. And finally, the statistic assumption 2, we can achieve the pretty good performance with a sync to real transfer. So this is some common sense before we start the research in this app. So we had to recheck and to review those two assumptions again when we begin for the general object grasping research. So let us review first. Assumption 1 is the large data equal to its means. We have to collect more objects. This is first assumption. What does the large data set mean for the grasping problem? Let's review this assumption. okay, when we carry the general grasping, if we do not consider the task-specific requirements, the large data to provide more rich local geometry inside the grid. This does not necessarily to meet more objects. So we first review the assumption that is a larger state is to mean that we need more objects. So let us check again. We to discuss we need more objects to improve our data sets or improve the performance. We should be to analyze or on the graph coverage analysis. We collect two data sets. One data set we call the big one and had about 40 objects, and the V2 we had 140 objects. So obviously the V2 is much larger than V1, and we want to analyze the coverage. We take a much larger data set to see the performance for the V1 and V2. There we use the EGAD object data set. It contains over 2,000 program generated objects in simulation, and we have very complex shapes. So we believe this data set have a large amount or not enough local geometry to enable our coverage analysis. So we analyze, we annotate the some graph posts in the training data, and for the testing object, if we find a similar graph post local geometry in the training set, we state, okay, this is covered. This is covered enough the geometry. In training data sets V1 and V2, we indicate how well the graph local geometries in training data sets can cover the test object sets. Okay, we can see this is V1 and V2. We know V2 is much larger than the V1 in terms of object number. And then we to check the how about the graph coverage in the large data, the EGAD in the data sets. When we uniformly sample the 1 million graphs posted in the each training object stage or data training each training object, we show the coverage curve and in the training data sets. We can see the object 1 and the V1 and V2 is very close. The performance is very similar. So we can make the conclusion that actually the object number is not an important factor for the coverage, the object, the grasping coverage analysis. When we sample the 4 million graphs posted on each training data set, we show that the coverage curve is for the training sets. Increasing the label density on training sets more important than the increasing the number for the training data sets for training object. So we can see that this in this figure, the number, the sample, how the label density is more important than object number in terms of the graph the coverage analysis in terms of grasping coverage. So this will show some example that our training data set, training objects covers of the graph flows and local geometry in the large scale diversity EGAD object data sets. So we can answer this first assumption that the larger data set mean we need one object. Actually, I think is not necessary. We should include the density or the grasping label to make the coverage for the analysis of the coverage, the grasping concept. The result is we need so many objects, so we can only build a data set in simulation. Okay, I think we can only limit or some or not so much object in the data set. We can build the qualified data set. So we answer the first assumption, and we answer the second assumption in the following the presentation. We know that we should densely sample the density. We get the density sample is more important. So now we build our benchmark for the generally grasping. The real world. So we can have three requirements. The first one, we should real world perception. We adapt well to the real world and the low cost sensor. Of course, you can say we use very higher cost for expanding sensor, but we argue that we should for the real world we more like the we prefer the low cost sensor, and which density same level grasping label. Grasping cost annotation and building level. And with the first one, we can argue a standard evaluation. We think the real good standard evaluation should be low cost evaluation. So the research in different areas propose different solutions. How to give in a real session and to get the dense grasping pose. For human depth annotation, we give you an image or 3D point out, and we to label the different grasp, but it's fast, very fast. So we cannot get the dense pose. The second one is a local correction. Those two ones, but yes, we can do in the real session, but it's more very expensive and inefficient. And the last one also we say the simulation, but simulation the program is not real, as we know, not real, and yes, we can get the dense pose, but it's not real. No existing methods can generate the dense X, Y, L. I say X is the real perception, and Y is the dense grasping pose. This is our solution. We call grasp one feeling. We get the real perception and we get the grasping pose. First of all, we get the 3D point cloud RGBD image, and then we can scan the object model, and we can analyze the model we can analyze the grasp pose in simulation work, and then we can push the grasp pose in the real world. So it's very easy to make a very dense pose labeling. So my question you may answer that we scan all the object and then we make a digital twins in the real thing. Is very expensive. Okay, I think it's very expensive, but we have solution that. We have solution, and we can 1 hour annotate. We can 1 hour annotate one thing with automatically system. That's we scan the object automatically, and then we push and quick and press paste another very new things. So we can create one thing and get the host very easy, and you 1 hour to annotate less than 1 hour to annotate one thing. In this week, we can collect a large number of the dense grasp pose. right? We compare which different data sets, how many dense posts in our data set, in different data set. We can find that our data set is about 2 billion glass posts in our data set. It's largely significantly large than previous data sets in the glass posts in terms of glass posts. So as we present the previous presentation, we say the dense glass post is more important. So we can build the new metric our data set in this benchmark that inputs your real inputs in, and you can build your algorithms. You can divide different algorithms in your whole in algorithm, and we can propose the post estimation. You can get your proposed post estimation, cross post estimation, and we bring in the simulation work to check the accuracy, and then we report the accuracy. Actually, we found the accuracy is very close to the real world grasping. So many people now have used this benchmark to test their algorithm, because we do not really use a real robot to test. It's very low cost, and we only to test in your computer. This is why I think this metric is maybe important for the scalable. Can be important for the general grasping if you want to test your algorithm very fast. So next one I will about the methodology. The methodology maybe we have very dense grasping post, and then we discussed the new methodology. For the learning, now we have X and Y, right? X and Y, and the XY is the real perception, and Y is the dense graph post, as we know. And usually people training a real network to approximate in the this flows. Usually people are training a the neural network to approximate this flows to the post process. Usually the standard maybe previous doing is the previous method is to sample evaluation, and then for the random and theoretically sample class candidate and evaluate each local patch, right? Then we use the network to check this graph or not, yes or no. This is not end-to-end pipeline, and then the pipeline is very another, of course, another is end-to-end to pipeline and extract the feature in the whole thing. The sample class, the point is uniformly across the thing, and for the inverse they all in. This is two types of graphing methods. However, the number of negative graph posts is 100 times larger than the positive graphs. In the same, either random sampling and uniform sampling is very expensive, and many computation research is based in evaluating the potential negative graph posts, right? So we propose formulate the graph detection pattern in the different level. Actually, we have 3 levels. We let's decouple the parameter or grasping. X, Y, Z means they are the location, or the location, or the position, or the graph. And the YW and YVW as the parameter of the width, right? Actually, we use the Bayesian formulation. We can giving decouple this operand. We want to get a thing, and we will estimate the XYZ and RVW. But actually, we can decouple, we decouple this problem. First of all, we give a thing, we estimate X, Y, Z, that is where we degrasp. And then we give X, Y, Z and thing, we estimate the RVW, right? And we use the RVW, and then we add thing, giving us the point y the probability for the X, Y, Z. And the V point by the probability is X, Y, Z, and the thing we estimate R and V. And then we have the R and V and X, Y, Z, we estimate the Y, the Y. So it can make the problem easy. We can see the three network. The first all is the possibility where should be can be grasped, and the point the V wise or the probability, and the angle wise or the probability. Right? We can compute that all computed from our data set. We design an end-to-end neural networks to model those three terms or three terms. First of all, we give the possibility of where can be grasped, and then the possibility where grasped we can put as the input for the V point, and the angle point we can build an end-to-end the deep learning model, so we can end-to-end to get out the grasp pose. We design to end-to-end the neural networks. During the inference, we free out the point and build for the lower possibility in the east text. Our network can predict the 1,000 or the grasping pose in the two in very fast about the 200 only very short time. Very short time. This is our result for the predict the grasp pose. Another problem is sometimes we need we always need to rely on the depth extension, but when the extension is correct, for example, the correct, how to do that? We automate data collection and collect data online through online optical checking, and collect the data or the pair or the RGB and input the data and the accuracy the depth information. Learning the mapping from the state RGB and imperfect depth into accuracy depth. Optical based object checking system. This is our optical based object checking system and automatically data collection. This is our grasping system in the some transparency objects. Okay, next one is anti-grasping. We can learn the perfect effective and the efficient of the anti-grasping system, and we found that we can use the small size of the data sets the object. We can get the pretty good accessory. For example, we compared with the DeskNet, we only use the 14 objects because we have them sampling, and we can produce in testing in the large object. We also can get the pretty good result even in very small size object because we use the dense sampling. The anti-grasping is anti-grasping we can try in the anti-grasping. In the anti-grasping, comparison with human, we compare with Terragraph, we can even we can defeat defeat the human. We can the sensory and the accuracy is better than human. So we record the corporate test. The assumption tool is we can achieve the pretty good performance in the scene to real transfer. Now we have a compression to use our method. We know the scene to real can work but we do know how we are working compared to real data. This is use our methods to try in the real data and the synthetic data. We found the success rate is our success rate is significantly less than the synthetic data. In dynamic post environment, the graphing post detached in each frame could be switched their the local locations and the orientations. We need to track in the object pose to contain the stable package, and so that the robot can move along the small trajectories. Most methods cannot guarantee the semantic coherence or the graphing pose. Even we use the nearest neighborhood or post evaluation. So we propose the detached association methodology. First of all, we define the graphing distance across things. This is our definition of the distance or the graphing here, and then we can propose the association in label through a corresponding matching. In this association matching, we can score between the two graphing posts in the categories by the cosines, the similarity or their feature. And the scores with here, the graphing feature is learned through the supervised contrastive loss. This paper is assessed by PRO. So there's the see the result. The fish is unseat. We totally do not train before the fish. Robot still try to own the first 5,000 objects for the graphing program and mainly so successful in simulation. Though difficult to learn the different general graphing grid. So many different given hand with content models very not available, and hand model can make thematical is very difficult to know and time consuming enable the thing. We found a method can be enable the robot to learn different weapons in different hands efficiently. Now our ongoing work can easily transfer to finger to gripper to the different mechanism gripper. For the normal gripper on the about 100 fighting 120 fighting 120 oxygen. Do not have more parts. Thank you very much.
I'm sorry about the video quality. I think that's for Toby's presentation, and I didn't find Toby on the Zoom, so I guess I will just start the Spotlight talk session. And so our first Spotlight speaker will be Sheng Yang. I think is Sheng here. Right. Good. And
can everyone hear me? Yeah. Hi everyone, I'm Sheng Qian, a final year PhD student working with David Foy. Today I'm presenting our paper, Understanding 3D Object Interaction from a Single Image. So first imagine what we can do in this image. There are a few objects of interest and we want to formulate the problem as a prediction as a query location problem. For example, given a query point, we ask, what can I do here? Here we can open the door and we can also sit on the sofa. And there are not really anything we can do on the wall unless we destroy the house. And this is like the negative examples. So given a query point, we aim to predict a series of properties. First, we'll predict whether what can be moved. If it can be moved, should it be moved by one hand or two hands? We then predict if it's deformable, rigid, and articulated. What's the access and what's the affordance to manipulate it? At the same time, we also predict the segmentation mask and the dance steps map. With all this information, we can predict how to open the door and what will happen after we open the door, which is shown on the right side. To solve the problem, we need a brand new data set. We hire an annotation company and ask them to draw 5 query points for each image. We sample images from multiple sources. For example, this one comes from internet videos. And this one comes from Epic Kitchen, which are egocentric videos. This one comes from 3D renderings by Omnidata. Now we have the data set, and let's talk about our approach. So our inputs is a single image and a set of query points. For example, we have 2 query points here. One is on the sofa, and another one is on the door. We build our model based on detection backbones such as detour and segment anything. The model makes an individual prediction for each query point. For the blue one, we find it can be moved by a single hand. It's non-rigid and a free-form motion. We also predict its mask and its affordance map. And we can do the same thing for the red one. Finally, we add a learnable depth query. When the prompt is a depth query, the model will predict dance depth estimation. So here are our results. When the query point is on articulated object, the rigid object, or even deformable objects, our model obtains reasonable results. And we can even do 3D animation of this model to show what will happen if we want to open this door. We can do the same thing for a drawer, which has a different motion. Finally, we test our model on robotics data to test its generalization and show it generalized quite well. Thanks for listening. Please come to our poster session for more details.
And we'll have a group QA session after the 4 presentations. All right. The next spotlight is a remote spotlight. It's from Zhang Tong. So, sorry. Okay.
Hello everyone, I'm Chen Zhang from Tsinghua University. Here I'm going to present our work, a universal semantic geometric perception network for robotic manipulation. This is a joint work with Yingdong Hu, Hang Zhao, and Xiang Gao. Robots rely heavily on sensors, especially RGB and depth cameras, to perceive and interact with the world. RGB cameras record 2D images with rich semantic information, while missing precise spatial information. On the other side, depth cameras offer critical 3D geometric data, but capture limited semantics. Therefore, integrating both modalities is crucial for learning representation for robotic perception and control. A growing body of research is focused on utilizing trained 2D vision models to learn visual representation, such as R3M. However, the current emphasis has largely been on training on huge volumes of 2D images. When confronted with the immense complexity of real-world environments, a robot with only 2D prior knowledge may face challenges such as partial occlusion and geometric shape comprehension. One nature and an intuitive solution is to develop pre-trained 3D vision models. However, despite some attempts in the visual community, such as UD, current models are not yet sufficiently transferable to robotic manipulation tasks due to 2 main reasons. The first is the lack of large-scale 3D data sets. The second is that 3D point clouds do not provide diverse semantics. To address the challenges, we proposed a semantic geometric network, a hybrid perception model for robotics that capture both the high-level semantics and low-level spatial patterns. We first utilized a large vision foundation model to encode semantic picture maps from 2D images. Secondly, the context-rich 2D picture vectors are then projected into 3D planes and combined with the point cloud features that are extracted from point clouds using a point-based network. These fused features are fed into a number of set abstract blocks, which join models and cross-model interaction between 2D semantics and 3D geometric information. We conduct extensive experiments on a broad spectrum of robotics manipulation tasks from our bench. The results show that our SG is significantly outperform image to action and 3D to action agents, highlighting the effectiveness of considering semantic and geometric representation choice.
Okay, so thanks. And our next presenter, I think, is Hanghi. Is he here? One moment. And our next presenter, Kang-hee Lee, is here it is. All right. Good.
Hi, my name is Kang Lee, and I'm a PhD student and post-tech, and will now present our paper, Learning to Register Unbalanced Point Pairs. And this is the joint work with Juna Lee and Josh Park. The point cloud registration is the task of recovering rigid transformation parameters between the two overlapping point cloud frames. However, first of all, this to estimate the camera pose of the given point cloud, generally the 3D localization methods first perform the frame retriever, and then they refine the pose through this point cloud registration. However, frame retriever requires large number of RGB frame sequence, so the data acquisition is often costly. So we assume the scenario where we have only a single reconstruction point cloud by aggregating several LiDAR data, and we call it as unbalanced point cloud registration as in our paper. In this unbalanced point cloud registration, there's no need to obtain a large number of RGB frames, and also the frame retriever stage is not required. Actually, this Redo dataset provides the reconstructed mesh, which is constructed by aggregating only 5 LiDAR frames. So here we assume a scenario where RGB frames are not available, and we estimate the pose of the input point cloud frame only with this single reconstruction point cloud. In this unbalanced point cloud registration task, input point cloud frame and the single reconstruction are under extreme imbalance in terms of spatial extent and point density. So as I mentioned before, there are extreme imbalance in terms of spatial extent and point density between the single reconstruction mesh and the small point cloud frame. So to address this problem, we designed first neural architecture for unbalanced point cloud registration and handle these imbalance issues with hierarchical framework named subregion matching and superpoint matching and point matching. First of all, in subregion matching, we build subregion candidates that are likely to be overlapped with the query and generate global descriptors for each subregion and query. So finally, we choose top case subregions through matching global features. So with this subregion matching, we can significantly reduce the search space. After that, similar to previous benchmarks, we build point level correspondences through the superpoint matching and point matching. These two modules operate similarly as in the previous benchmark. However, these putative correspondences are often very noisy, so we propose the structured matching to filter out the noisy correspondences. First, we can make a binary matrix by computing the spatial compatibility. However, spatial compatibility is not enough to remove outliers because it only considers local consistency. So we utilize a coherence matrix, which considers global consistency by calculating the number of commonly consistent correspondences. This coherence matrix can be obtained by simply multiplying the compatibility matrix with DSF. And here is the result on Redo dataset. We evaluate the registration recall under various spatial extent imbalances. And as in highlighted in red box, especially this is the most challenging case, and our UPPNet method outperforms the COFINET, which is the one of the state-of-the-art registration method by 30% registration recall. And next, we also evaluate our method on KT-UPP dataset, which we create carefully to generate unbalanced outer dataset. Also, in this experiment result, our method achieved the best generation ability under the various spatial extent and density imbalances. And this is the qualitative results. Focusing on these highlighted red boxes, our UPPNet outperforms baseline methods qualitatively as well. So thank you for listening, and please check our paper or visit our poster session for more details.
Thank you. And our next presenter is Maury. Yes, thank you. All right, good. Let me open the.
Hello, everyone. My name is Mauro. I'm a PhD student at the University of Bristol in the UK. And this work is about reconstructing 3D objects using vision-based tactile sensing and neural fields. So neural fields like NeRF, occupancy network, or GPSTF are extremely popular techniques in computer vision to encode and reconstruct 3D objects. And they're usually performed using camera-based sensing. But this has a few challenges, like such as in the presence of occlusion or highly reflective, transparent, and homogeneous surfaces. So a question we had was, can we use vision-based tactile sensing to encode and reconstruct 3D objects? Similarly, I think to what we have seen earlier with NeRF, reinforcement learning. And the answer is yes. So we are proposing an approach where a robot is sampling, so it's touching an object. Every time it touches an object, it extracts a tactile image, which is the marker pattern you see there. Then we use a real-to-sim model to map this tactile image into a depth map at the touch location. And then we use a CNN to predict local surfaces, so local point clouds corresponding to these tactile images. This is what you see in the second phase. And finally, we use GPSTF so a neural field to reconstruct the entire shape of the object based on this local surface that we predicted. And we tested this both in simulation and in the real world. So you can see simulation we tested with both seen and unseen objects and poses. The object that we want to this is just an example. We did it with about 1,300 objects. What you see, the objects to reconstruct is the lower row, while the upper row is the reconstructed mesh with about 20 touches. And the same thing with the real world. So we tested both with 3D printed objects and everyday objects. And our next steps is going to be combining camera-based sensing, so basically vision and tactile sensing, and we're also working a bit in VR to explore reconstruction and virtual reality. So yeah, so if you're interested in knowing more about this, come and chat with me or DeepSTF 3D deep learning. Yeah, thank you very much.
I have the others on the stage for the QA session. Just come to the stage so that for the QA session. Yeah. Do you have any? First, do you have any? I think on the side of the room. Actually, I have questions for that. So first thing about your articulated reconstruction. Do you know how do you can? I mean, it's a supervised training, so how can you generalize to like very different articulated object like a lot of like daily objects are a random articulated object. How is it possible to generalize from the supervised training to this?
I think it's very hard to generalize to like arbitrary articulated objects. When I talk about generalization, I mostly more care about the generalization across scenes. For example, from a lab environment to like everyday environment. When we do train it on our training data set come from egocentric video, internet videos, and as well as the Omni3D data set. And this makes sure it can generalize to everything. But if you talk about like random articulated objects such as multiple joints, I acknowledge this is really challenging, and I don't think our method will work on these also objects.
I see. So do you have any insights on how is it possible to do this?
I think I don't know if you have checked OPD. I think they have do some interesting work on that. They do some detection inside the object, and I think maybe as long as I don't have too many joints like a robotics arm, their method seems more promising on this side.
I see. Thank you. And Mara, I have one question for you. So you said you have trained this in to predict like local surface from like tactile input. So how do you get this ground truth for like?
Oh yeah, really good question. So I think you're referring to the second step here. We used the PyBullet simulator, and in PyBullet, something that PyBullet allows is to cast rays. So basically, I designed a small method to cast rays from a tactile sensor, and we collect the intersection between these rays and the objects, and this is basically our point cloud. And then we use this ground truth to map tactile images to this point cloud.
So have you ever tried to like apply to this real world experiments, like real world tactile sensor and real world objects?
Yeah. So yes. So we did that. So in the lower road, this is real world.
Oh, I see.
Yeah. So this is the whole first part was just in simulation. Once we proved that it was working fine in simulation, we went in the real world. This is more challenging because in the real world, the pose is always unseen and the object is unseen usually, except for the 3D printed objects for evaluation purposes. And this is really challenging because deep STF and neural fields usually want canonical poses and seen objects, but if the latent space is robust enough, you can interpolate in the latent space, and this is what happens here, and this is why we get.
So your method is train the simulation directly applied to the real world?
Yes.
Oh,
yeah.
that's pretty cool.
Yeah.
Right. Thank you.
Thanks.
Thank you, guys.
Oh.
Okay.
Yeah, I have a question. I see the testing set is very similar to the training set. So what's the result on something like more different objects?
Yes. So the data set we used was ShapeNet.
Yes.
So we sample 6 categories, about 1,300 categories on ShapeNet, and you can see, for example, the number you see there is the chamfer distance, the small number there.
Okay.
So the chamfer distance is actually really low.
Yes.
We did not normalize so the chamfer distance is with respect to the objects in the ShapeNet data set, because sometimes in paper you see the normalized, so the chamfer distance with respect to the normalized objects.
So do you try something more different? Personally, not from the data set.
Yeah. So for example, the everyday objects, were objects that we found in the lab. So we used mugs and jars. It's important that you select objects that are somehow similar to what you found in the training sets, because you need to be able to interpolate in the latent space.
Okay, so if I select an out of distribution sample, then the performance will be not so good.
It depends.
Understanding that.
Yes, this is true. So if it's out of distribution performance, if you're using something like DeepSTF, performance will be poor because DeepSTF wants canonical pose. But if you choose an object which you did not have in the training set,
Yes.
but is somehow so once you project the embedding of these objects is somehow close to the embeddings of the objects that you found in the training set, you can assume that the model is able to interpolate in the latent space and you get something sensible.
Okay.
Like in this case, for example, where you see the mug. The mug is our reconstructions is taller than the real mug, the mug that we found, the real mug. And the reason is because by interpolating the latent space, the model did not retrieve the perfect embedding, and this is why you don't have a perfect match.
True. One last question. So roughly, what's the size of your model? Like the number of parameters, what's the underlying operator?
Oh, you mean the DeepSTF model?
Yeah.
Yeah, it's exactly as the DeepSTF in the paper. So it's 8 layers, 512 neurons,
Okay.
and the embedding is 128 dimensional. Yeah, we used all the tricks. So we used clipping. I did, so I'm not using the raw input, but I'm using positional encoding, which is helping. So if you're not using positional encoding, do it because it helps a lot, similar to what NERF does. Yeah, so it's the model. Yeah.
Okay, thank you.
Yeah, thank you.
How can you select the 20 touches?
Yeah, good question. So 20 touches are selected randomly. And this is because we assume that we do not have prior knowledge on the objects, because we don't have, right now, we don't have vision, meaning we don't have a global view of the objects, even though we're working on implementing that. So what we do is we build a virtual hemisphere around the objects, then we sample randomly, and then we move the end effector to that point, and we sample the object randomly. So everything is random, meaning that in some cases, if we're lucky, with just 5 to 10 touches, we can reconstruct the shape, especially if the latent space is robust. In some cases, you need up to 20 touches. Yeah, thank you.
Which will all be remote, and then it's a group QA again. So let's start. Okay. Like this.
A warm welcome to my presentation, everyone. My name is Jörg Heufel, and I conduct my research at the Human and Robots Lab at the University of Bonn in Germany. Robots should be personalized, and let me tell you why. Robots should be personalized because users may have personal gold standards about the interaction. So imagine closely collaborating with your personal robot at home or at work, and ideally the interaction should be as comfortable and natural as possible. So users may have individual preferences about how the robot traverses their home or how they actually approach. And here, personalization is a key factor. So today, we talk about the preference alignment of robot navigation behavior. In this work, we learn a preference reflecting navigation controller that relies mainly on depth vision. Using a virtual reality interface, the user intuitively demonstrates preferences by drawing trajectories right onto the floor using a handheld controller. To learn, a TT3 reinforcement learning architecture is used with an additional behavior cloning loss on the actor. And furthermore, a separate demonstration buffer is used that provides the agent with demonstration trajectories throughout the entire training process. The robot-centric state space captures information about the position and presence of the human in the robot's field of view. And also the goal position is provided. Most importantly, for 3D scene understanding, the low-dimensional latent representation of the robot's depth camera is included. And then the perception pipeline consists of a variational autoencoder that compresses the depth image to a latent space of dimensionality 32. And below, you see input and output, so reconstruction of the variational autoencoder. To demonstrate, the user draws preferred trajectories onto the floor in virtual reality. The user's dynamic motion is here also recorded. And then later on, the demonstration data is used in the learning process. Let's look at the qualitative performance of the controller. The robot has to avoid the dynamic human denoted in red on the plot when navigating from the start, that is a black dot, to the goal, that is a blue star. Ideally along the demonstrated preference, and that is the orange line. In the cup scene on the left, the robot should navigate at the opposite side of the room, ideally like along the cupboard. Around the suite in the middle plot, the robot should take a wide turn around the armchair to make room for the approaching human. And in the entrance scenario on the right, the robot should take a left-hand turn while the human passes along. Let's get a better understanding by looking at the animated map. Right, a visualization of the robot's perception is shown. And we can conclude here that the robot successfully reflects the demonstrated preferences on its way to the goal. Further quantitative results and evaluation studies, you're kindly invited to have a look at the paper on the workshop's webpage. To conclude, we demonstrate how to learn a preference reflecting navigation controller that relies on depth vision. For further discussion, feel free to get in touch with me now or after the workshop. And the QR code provides all of my contact details. So I would also like to take the chance to invite you to have a look at our websites for more research.
This is we'll have the QA like in the group later, and okay, next one.
Hello everyone, I'm Patricia. Today I'm going to present our work, 3D intuitive physics, or more generalized 3D broadly visual intuitive physics under challenging themes. This is a joint work with Antonio Proga, Joshua Campbell, Daniel Evans, Legally, and Pichon. As we can see from the figures, humans are good at achieving intuitive understanding of the 3D physical world around us. And given the certain actions, we can roughly know how the object will move. And we call this kind of intuitive physics. which can help us better interact with the physical world around us without extensive try and error process. For humans, given some visual inputs, the physical interactions around us, the challenges is like fluids or granular materials, we can form an intuitive understanding of the challenging dynamics in 3D space. And given the mixing, we can generalize this kind of intuitive physics into objects of different shapes or different amounts. So there are some previous works on this direction, and some of them work on 2D, so it's hard to generalize in 3D. And some of them need really dense 3D annotations that be probably close of each frame to learn the 3D intuitive physics dynamics learner. And also with recent work, NeurFDY used implicit in 3D representation, and we found that this is hard to generalize it to extrapolate settings. And here's our framework of 3D intuitive physics, which is composed of two main parts. The first is visual inputs, is from videos to the entries versus 3D. And the other part is the dynamics prediction path, which is from 3D versus 3D representation and to learn dynamics. For the left part, we use a rendering loss with a conditional nerve to extract the inner ranges to the representation of the scene. And then we use instant segmentation with color and sparse sampling to get an instant point cloud. As long as we got an instant point cloud, we can learn dynamics prediction hat into the particle space. It should be noted that since we don't have the one-on-one correspondence between the frames of the point cloud videos, so we need to use a distribution-based loss like transfer loss to learn our dynamics predictor. And also we introduce this merge loss to avoid the degeneration of the point clouds. We generate three kinds of videos, which includes common interactions with the real world, like water pouring, the fluid tube shaking, and sand pushing. Both using a KUKA robot, and we have 6 videos and 5 different settings of each scene. We can see that our visual front-end is better than the DY and auto-encoder baseline using multiple inputs, since we use conditional inputs instead of using a global vector to represent a whole scene. Those in the interplay and extrapolate settings. We also show that from the identity, our 3D intuitive physics is better than the DY in both interplay and extrapolate settings. Especially for the extrapolate settings, our method is better since we impose stronger structural inductive bias than the NeurFDY. And here is some polyadic results of the dynamics of prediction paths. And you can see that our methods can better learn the dynamics of the challenges instead of the fluids, right?
I guess this is the end of this one. And the last one for this group.
Hello everyone. I am happy to present our work, New Graphic, learning any basics of robotic graphic in Flutter via the. This was done at the IROSA lab at the Technical University of Darmstadt, Germany. In this work, we focus on any graphic in Flutter, specifically using partial visual information captured using a single view from any random viewpoint. The random viewpoint is especially the norm when using a body camera on the robot, and you have a humanoid or mobile manipulated robot as the picture on the right. The robot is free to move anywhere in the scene, and so captures the input point cloud from any random view. Specifically, our method involves obtaining a neural geometric representation of the thing. This is done using a convolutional occupancy network, which reconstructs the thing. It has been shown that such occupancy network and reconstruction method encodes good features that are informative for graphing. Specifically, our method involves scene-level neural surface rendering. With scene-level neural surface rendering from a partial input point cloud, as seen on the left, from that point cloud here, we can use virtual cameras to complete the scene. And then we can use graph sampling strategies on the complete scene to explicitly sample graphs in areas of the scene that were unseen. This gives us a rich distribution of graphs. We then perform local neural surface rendering to discriminate between graphs. For example, here we see a graph with 3 cameras, 3 virtual cameras around it, and we use these cameras to render this local depth point cloud. The local depth point cloud is very informative towards graph quality. What we show in our work is especially that The local point feature, the encoded features of this local point set are especially informative to graph quality and can be used to discriminate between good and bad graph. And learning the graph quality networks of these features helps in setting high graph system. We tried out the method in simulation with the volumetric graph network simulation setup and with parallel volumetric method. We specifically compared against multiplicity graph network feature and theta, and our method performs very well both in terms of graph acceptance and velocity settling. We then transferred this system to a real robot mobile manipulation with random viewpoints. So as you see, the mobile manipulation moves around, seems to see some random viewpoints. The field level rendering as well as the local rendering ensures that there is a rich distribution of graph that the robot can discriminate between, and that the graph quality network has a support features that graph discrimination to be easier for the robot. For more information, please check out our website, and I'd like to thank you for your attention, and I'll be happy to take your questions.
That's our presentation for this group. So do you have any questions from on-site or over the Zoom? Let me first stop sharing and then. Yeah, we have one question.
Hi there. I have a question about that last presentation. There was a point about using virtual cameras to complete the scene. I was curious if you could expand on that.
Yeah, thanks for the question. So the cameras are just basically a neural rendered camera. They're just any view from any view, and basically it's just a rendering procedure. It's a matter of where you place the camera. So for a local render, you can place cameras close to the gripper and then render a local dense point cloud around the gripper.
Gotcha. I see. Thank you.
So actually I have one question regarding the 3D interphysics. So is the author there? Okay. Maybe it's not, the author is not in the in this, I guess. Yeah, actually also it's time for our coffee break and also the poster session. So for anyone who want to discuss with the in-person presenters, you can go check our posters at poster number 192 to 201. And we will back with the in-person presentation from Georgia on like 10:35. So yeah, thank you all for this session. Thank you. Right.
That sounds good. And let me do the talk. Sure, do that. Wait, that's not what I want. So what are they seeing this?
Yeah, they're saying this. Everyone's saying this on the overview.
Okay. You guys are not seeing my comments, are you? You're seeing the actual presentation. Talk to the Zoom people.
You see what it's like. Are you real?
Okay, good.
Yeah.
Also, I'm hearing some feedback.
I think the feedback will go through the. So can anyone say something? Oh, interesting. Mix that a little bit.
I think it's good. I'll deal with the feedback.
Oh, I see. I should. Nice. Anyone say something over the Zoom?
I think it's okay.
Yeah, I think it's okay. Yeah, maybe I'll just start now. Okay, so yeah, I'll do a brief introduction. So, hi everyone, welcome back to our workshop on 3D vision and robotics, and we're already very honored to have Georgia as our next speaker. And Georgia is an incoming assistant professor at Caltech, and she's currently a research scientist at Tech, I assume.
No.
Okay. Okay, never mind. But she's an incoming assistant professor at Caltech, and she is a recipient of Tommy Young Researcher Award, and she co-wrote and making PyTorch 3D, and also her work has been recognized with the best paper at ICCV 2027. 2017, sorry, not 27. Yeah,
That's true.
that's perfect. All right, let's welcome Georgia. Thank you.
Okay. Thank you, and thank you for being patient with waiting for me. So I want to talk today about 3D object detection in the wild. I do not work in robotics, so do not treat me well. But I've been thinking a lot about 3D problems, and I understand how in robotics 3D problems are very important. And so I kind of wanted to give my view on the field of 3D and how we could improve it so that we could think about robots in the wild that perceive things, so that you guys that work on robotics don't have to think about perception. You can just work with managing your hardware and making the legs go the way they should go. So this is what I want to cover today. I want to talk about 3D from the perception side. And I am at core and always will be and forever a recognition person. So I care about taking images and understanding what they contain, interpreting them in various ways. And there's been a lot of great work done in this field for the last 10, 15 years. This actually 2D recognition, recognizing objects in 2D has been one of the most prominent problems in computer vision for the last decade or so. And I will argue, and maybe you'll disagree, that it is likely the biggest win computer vision has seen, solving some of these problems at a state that are used to the point where we can actually build applications. And I want to give you an anecdote for this. When I joined Meta in 2016, various teams at Facebook, including Zuckerberg, did not see the potential of object recognition in any products. They're like, what are we going to do? We don't need object recognition when it works, so it doesn't work well. I don't think we can sell more products by having a janky like purse detector, who cares? And then mask recognition came along, and we showed that you can actually do this for a variety of categories, and so well that now has turned completely around. There's now no product, no app that works for content in the space of content understanding that's not using an object detector in the back. So this is exactly why I think it has been one of the biggest wins in this community. But it has also been one of the most boring wins. And why that's boring is because all these methods and all of these great success stories and all these awards that some people have gotten assume that the world is a 2D grid. And obviously, I don't need to convince you, you're all robotics folks or robotics adjacent, that is really not the case. And if we want to move beyond just trying to sell purses to people and whatever other products, and we actually want to build some more exciting applications like embodied tasks, robots, self-driving vehicles, or other types of means of transportation, or even assistive technology, that's something I'm very excited about, VR, AR, whatever you want to do, you need to move beyond the 2D grid. So this has been my mantra for the last few years, that, oops, hello, that robots act in a three-dimensional world. So 2D scene understanding is really not that useful. So, and for embodied and general tasks, we really want to get to 3D scene understanding. Now, the question is, what is 3D understanding? The problem with 3D is that it's so wide, it's so broad as a topic that it's very hard to define. And I'm making an attempt here, mostly to maybe think about it, discuss it later, into separating into two axes. The first axis is, how many views per scene do I assume I have? I could assume I have one scene per view, or I could assume that I have one view per scene, or I could assume I have 100 views per scene. And the other axis is scene complexity. Do I assume real world scenes? I think we should. Or do I assume single objects on top of a table? And it's my belief that a lot of work has been falling in various parts of this plot. We have this part to start with, where models assume that you have 100 or more views per scene, and they try to reconstruct and understand the scene, either real world or single object. And some examples here are SFM or NERF. And I know this is a big debate on how NERF and how useful they're going to be for robotics. I actually don't think that these methods that assume 100 views per scene are useful for robotics. Okay, that went well. And the reason is that, imagine a robot that goes into a new terrain, a new scene, that it enters a new scene. For it to be able to reconstruct the scene through NERF or SFM, extract the point cloud, it needs to first figure out how to go about the scene to collect these 100 views. And they're not random views. They have to be 360 covers of the views in order to reconstruct it so well so that it can now act with that reconstruction in place. That seems like a chicken and egg problem. When is it going to act? It has to act in order to capture, then it has to reconstruct from the capture in order to act. That seems bizarre. However, there are other applications in this space that where NERF and SFM are useful. Hollywood, I think, perhaps maybe VR, like gaming. These might be potential applications for these types of methods. So I kind of want to move now to the more useful side of this plot, which is assuming that you have one view per scene. And we're going to start with single object scenes, and that which is something that has been studied very much to an excruciating point. You have all these projects on doing single object 3D reconstruction. They're mostly done with objects like ShapeNet, which are synthetic objects that you render in this white void. Again, I think a little useless, but thankfully, and maybe through and thanks to these works that were in these synthetic data sets, we now see works that operate actually more in the wild for real world single objects, but at least more complex objects. And we have this paper that we're presenting this Wednesday on 3D reconstruction from any objects like Spiral from Nintendo. You guys know? Okay, good, because I gave this image in another workshop and nobody knew what it was. And I was like, okay, maybe I'm too old, but Nintendo, if you're born in the 80s, you know what I'm talking about. But now I want to move to the more challenging case of reconstruction of real world scenes from a single image. And this is definitely a problem that is underexplored because it's very challenging. And so I kind of want to give you my ideas and some progress in this direction on 3D object detection in the wild. You take an image, any image, and you detect the objects. You predict what objects are on the scene, but you predict them in 3D space. That means that now your output lives in 3D, which means that you can actually look at it from all possible views. So you see this image right here of this urban scene. And you get the reconstructions and also the layout if you look at it from a top view. And what you see here, which is this grid, are tiles of 1 meter across 1 meter in size. So you actually get metric outputs in your reconstruction. So this is exactly what I want to cover today. 3D object detection in the wild. And when I say in the wild, I mean truly take any image from the web, an image of the scene, and be able to detect its objects and predict their 3D properties. And this is joint work with some people at Meta, including led by Garrett Brazil, and with Abhinav, Julian, Justin, and myself. So first, I kind of want to introduce the problem. So I know that maybe a lot of you are familiar with the problem of 2D object detection, where you're given an image and you want to predict for every object, detect every object in the image that you are going to describe with a category label, chair, sofa, floor mat, etc. And a 2D box that consists of its XY center in pixel space and its width and height, again in pixel space. This is a pixel space. It's a fake space. It's a comfortable space. So now 3D object detection has exactly the same definition, but instead of predicting an object in pixel space, you now predict in a metric space. So it's center, it's now XYZ in metric space, and its dimension is width, height, and length, again in metric space. Metric space is meters. And in addition to these properties, you also have a pose of the object. This is the pose of how you're going to rotate that cuboid so that it tightly fits the object. Any questions so far? Okay, so that everyone gets that. So how are we going to go about this? So the first thing to note is go back and see how did 2D recognition win? How was 2D recognition able to make progress? And they were able to make progress by having diverse and complex data sets like Coco and Elvis. Now in 3D, these data sets unfortunately do not exist. And actually, there's something that's even weirder that's happening, is that the problem of 3D object detection is actually studied under two different lenses. The first one is the urban lens. So this is data sets that were captured by a self-driving car. So this is a kitty as an example like this, where all of the data sets are taken from the point of view of the driver. And what happens when you're studying a problem in this narrow space is that you start making assumptions that are not just generally true. For example, a lot of work in urban domain assume that all the objects lie in ground plane. Of course, that's true in the urban domain, perhaps, but here's my object, so that is my laptop on top of this stand. So it's not generally true. And then it's also the visual domain. Not all urban scenes are actually from the point of view of the driver. These are also urban scenes, not from the point of view of the driver. And if you try to apply any method that was trained on Kitty on these scenes, catastrophic failure. Then there is the other domain, which is the indoor domain with data sets like Center GBD, which are depressing small apartments of students and offices. I've been a student, I know what it's like, but there is not this diversity of indoor space that is true in the real world. And also most objects are very close to the camera. Actually, the largest distance of objects in Center GBD is 6 meters. 6 meters from me to maybe you. So all of you in the back is like, you don't exist. That doesn't also make sense. And of course, again, it's the visual domain of not all indoor apartments are student apartments with one desk and one chair. You have fancy lofts, you have bars, you have churches. The diversity of indoor space is vast. And then of course, there's also the intersection of, here's an image of urban domain with a bike and a couch. So you have objects from both categories that none of the existing methods were actually able to tackle. So I'm making all of this introduction to say that there hasn't been a comprehensive approach to solution to the problem of 3D object detection that would be able to tackle all of these domains at once without making assumptions about the nature of the objects and the scenes. And this is again exactly what I want to cover today. I want to cover this method that we developed that is able to tackle all of these things for over 90 object types of all scenes. And of course, the first thing we had to do is figure out our data set. So what data are we going to use for this problem? As I said, data sets in 3D are not as popular or not as big, not as widely developed as in 2D. But luckily, since 2019, there were all these wonderful data sets that were released, not for the problem of 3D object detection. They were released for a variety of other problems like inverse rendering, point cloud reconstruction, and so forth, that could actually be repurposed for the problem of 3D object detection. This is exactly the opportunity that we saw and we took, is to take all of these data sets collected from a variety of people in the world and combine them into one data set that is diverse, that combines all of the domains and has 3D annotations that we had to repurpose to make useful for this task. And so this is how Omni3D came about, which is a collection or a concatenation of all of these data sets. There was a lot of work behind it. And the result was a data set of over 3 million object instances, 230,000 images across domains. And here are a few statistics on the Omni3D data set. So here you see the categories and the frequency. So we have our long tails, as we always do. And of course, there's some objects that are more frequent than others. For example, person, chair, I think is very frequent, and other ones that are not, like bathtub, I think is not very frequent. But so there's the distribution. But the most interesting one is the depth range, and this because it's also the most challenging aspect of this problem. And here we plot the distribution of depth and the density of the objects, where you see where this plot goes all the way to 50. However, our biggest depth, like the furthest away the objects are in this data set are 200 meters, which our model has to predict. There's a vast difference to CERN-GBD that was only going to 6 meters in depth. So we have a lot more analysis in the paper that I want to go through for sake of time, but we try to summarize the data set and actually show how it is a very comprehensive, all-inclusive data set for this task. And then the next step, now that we have a data set, is to train this model that will be able to tackle this problem without making any assumptions about the domain, have no priors about objects and distributions and depth, etc. And this is how we came up with our QBAR-CNN method, which is what we consider a baseline for this data set. So the QBAR-CNN is a very simple model that outperforms all other models, not only on Omni3D, but also in the single data set benchmarks, and has what we think are some of the most generalized abilities to generalize to new domains. So we actually applied QBAR-CNN to images from Coco, And we see that it actually works, which is actually the first time that we saw that happen. If you take other models that were trained on these single images like Kitty and StarGPT, they actually completely failed to generalize. Of course, there's still a lot of limitations. I'm not trying to argue that the problem is solved, and you'll see from the numbers, the performance is far from solved. But I want to make the point of training on large data set will get you more towards generalization than training on single domains. So what is QBAR-CNN? Well, we tried to make it very simple, almost to the point where we were sure that reviewers will nag about what is the novelty here, because we wanted to remove all of the extra bells and whistles that we saw were being published in the past few years on 3D object detection and make something that's easy to build upon, modular, that you can extend for your problem. So it contains findings from both state-of-the-art in 2D and 3D object detection, like here, and I want to cover maybe a few of them in the remaining minute that I have. So QBAR-CNN builds upon faster RCNN. This is this family of object detectors that takes an input image, embeds it into a backbone feature map through a network. It can be a CNN, it can be a transformer, whatever people come up with. The backbone is really not, is a plug and play. It's really not attached to the design of the model. Then after the feature map, this is where your task-specific heads start. So you attach an RPM, which is a region proposal network that detects where are plausible objects in the image. This is done in 2D, and we had to deviate a little bit from the original design of RPN and faster CNN. Originally, RPN was designed to do objectness. We deviated and we are predicting IOU-ness. So we're predicting the IOU value with the closest ground truth, which is very critical when you have data sets that are not exhaustively annotated. And Coco and Elvis are exhaustively annotated, or the information of exhaustive annotation is there, but Omni3D is by design not exhaustively annotated. So ObjectNet will penalize what actually be detrimental for this, while IOU-ness bypasses this. Again, if you want to know more about this, go to the paper where we have an extensive discussion. And next up is our 2D head, which predicts the object in 2D. And of course, the novelty here in the design is the cube head, which predicts the 3D properties of the object. These 3D properties combined are making up the 3D center, the 3D dimensions, and the pose of the object that leads to this cuboid predicted in 3D space that is then compared to the ground truth. And this is how we train the model.
Sure, did they take questions during the talk?
Yeah, absolutely.
Can I ask?
Yeah.
I didn't understand the IOU-ness is for like as a loss, like if there is no bounding box at a certain location, you cannot. So how does that actually help with the inexhaustible annotation?
Yeah. So if the ground truth is missing, so in objectness, you're making a very hard decision about whether the object is there or not. In IOU-ness, you regress to an IOU. So it penalizes models less by having missing ground truths.
I see. So
And this is actually a common trick used for open vocabulary detection.
I guess there's use a particular kernel or something to make it not penalize us.
You don't make it a kernel, but you are fixing so you are assuming that you're above a threshold. You're going to regress above a threshold, so it learns to understand objects rather than classifying 0 or 1, which is a much stricter decision to make. Okay, so I quickly want to cover how we set up the objective here, and I'm going into the nitty-gritty details. So if you snooze off here, I think it's totally fine, but I find this interesting. If there are students in the room, I think that you might learn a few things. So for 3D object detection, now that we are predicting more properties about objects beyond 2D. Actually, we're predicting 4 sets of parameters. We're predicting UV, which is the projected 3D center in 2D. And we're also predicting the depth of the object. These 2 parameter sets make the 3D center of the object via ion projection. We assume we know the focal length of the image. Then we'll predict the width, height, and length of the object. Again, this is 3D dimensions in metric space, and we use a log space, and we predict the pose of the object. So we predict all of these 4 sets of parameters. Now, If you were asked to set up a model to train this, what would you do? You would define the loss that looks like this. 4 different losses on all these 4 different sets of parameters, and some weights in front of these losses to weight them because they're all kind of different. So you need to figure out how to put them together in the objective. There is a big problem with this. First of all, it's ugly. You have all of these 4 losses. But basically what it means is that now we're faced with this problem of hyperparameter tuning of all of these weights. We also have specialized losses, and that actually becomes a problem. What is the best loss to predict depth? That's actually an open question. It can be predicting 1 over z, it can be bending. It's not clear what is the right loss for depth prediction. Also, what is the right loss for poses? Again, an open question, and actually depends on tasks. So not only do we have to do parameter tuning for the weights, now we're also faced with different variants of losses. And so now the grid search space becomes large. Now we're wasting a lot of GPUs, which feels really bad. Like we have PhDs, which should be smarter than that, right? So we didn't do this. This is not the loss that we defined. We actually did something different, which is cute and a smart idea that we called entanglement. And then we did disentanglement. But let me go first to describe entanglement. So we have these 4 parameter sets that we're predicting. And I told you that if you combine these 4 parameter sets, you can actually get to a bounding box. You have the center, you have the width and the height, and you can actually convert these parameters to a point cloud where the points are the vertices of a 3D box, of a box in 3D space, 8 points. And this function E3D that corresponds to this box is actually differentiable. It's important. So now I have a way to convert these parameters that I don't know what to do with them in my loss function to a point cloud that describes the 3D bounding box. And now, of course, I also have the ground for 3D bounding box, which is also another point cloud. And so what I'm going to do is I'm going to compare these predictions, not by going to the parameter space, but by actually predicting point cloud. So I'm going to take a point cloud distance like a chamfer distance. So you've seen now that I've moved away from having a loss on all of these different parameters to having one loss that combines all of them with a very nice and elegant point cloud distance. However, there is an issue here. I don't know if you've seen it, but if I have a wrong prediction, and I'm going to have a lot of those during training, it's very unclear which set of parameters is a culprit. Who is to blame for my wrong prediction? And this is a problem because I've entangled my losses. So what I'm going to do is I'm going to actually now do, based on this loss, I'm going to go into disentanglement, where I'm going to define more losses, but where I'm going to replace all of these parameters, apart from one set, with the ground truth values. So this is the disentangled version of this loss. And I'm going to do this for all of my parameter sets, resulting in a loss like this. So I'm going to have my disentangled losses for all my variables. I'm going to have my tangled loss. And now you're going to tell me, Georgia, what are you talking about? Have you lost your mind? But you're back to summing a bunch of losses together. Yes, but all of my 3 losses are not homogeneous. They're chamfer distances. There's no need for weighing because of their homogeneous. And also, we're no longer arguing with co-authors about what the right loss is for various variables. And that's important because it brings peace to the group. Okay. And I'm going to show you how actually this is better than grid search, and I'm going to show you a little later. So that was loss, defining the loss. I'm not done, nowhere near, but I have more minutes, so you're going to have to bear with me. So this is how we define the 3D loss. Now, I actually want to put all of my losses together. And remember, my network is predicting 3D objects, but it's also predicting 2D objects, right? I'm doing 2D object detection and I'm doing 3D object detection. So I actually have a loss that's 3D. I described what that was before, and I now have a 2D loss. And again, students, you'll know what I mean, but when you have these 2 losses, you're not going to sum them like this, right? They're completely different, 2D and 3D different tasks. So you need to weigh them differently. And actually, you're going to say, well, the 3D task is harder than the 2D task, so I'm going to put a weight in front of the 3D loss. And maybe that weight should be something that's smaller because the 3D task is harder. Again, this is an arbitrary decision, and we want to move away from arbitrary decisions. And instead, we actually want to give the model the freedom to decide how to weigh its different losses. There might be cases where the model should not weigh its 3D detections very much because they're very occluded and it's a very hard problem for the specific image. But there are other instances where 3D detection is easier sometimes than 2D detection. So we don't want to penalize, or we don't want to set a weight to the model so that it ignores various aspects of this problem. So what we're going to do instead is actually something that is probably my favorite feature of this model, is defining it as an uncertainty specific quantification problem. So we are going to put a weight on top of the 3D loss, which is going to come through this new value that is output predicted for every instance by the model. So this mu measures the model's 3D uncertainty for each prediction. And let's look at this loss and what it does. So if mu is large, which means that the model thinks it's uncertain about its 3D prediction, then the 3D loss is downweighted because x to the minus u is a small value, but you want to penalize the model for not being certain. So you're going to make it an added, you're going to add it. You're going to add the uncertainty to the loss. If mu is small, that means that the model is certain for its 3D prediction. Thus, the weight on the 3D loss is high, and the additive term is small. So no linear penalization. We don't have supervision for mu. The model estimates it based on the appearance cues and how the objects look in the image because it's predicted from the image for every instance. So it's kind of like a self-learned type, though I hate these terms, but it's important. There's no supervision. The model has to predict it. The model has to self-calibrate in terms of 2D and 3D. Okay. Great. So this covers how we set up our training objective. Now you're going to say, okay, finally, we have a training, we have the model, we have the data, so we're ready to train. Yes, we're not. There's another challenge that we need to overcome, which is maybe my second favorite aspect of this paper and the contribution, which is understanding some of the challenges and the sources of variation in recognition for 3D. So, now that I'm a faculty at Caltech, I have to teach all these students how to do object detection. And one slide that I show them is all of the sources of variation a model needs to overcome when it has to solve for 2D recognition. I stole this slide from Ross, but it's really nice encapsulates what are all the problems, all of the source of variation that a model like Mask or CNN or Fast or CNN has to overcome to nicely detect objects. For 3D, you have all of these, and now you have an extra one that was not relevant before, that was not relevant for 2D. And it's simply the following observation. So Omni 3D images were captured by a variety of sensors. Remember, we take images from a variety of groups around the world that use any type of sensors. We don't have any control about the sensors that they used, which means that now our data and our models will generalize across sensors. That's great. We don't want to overfit to a sensor. That's absurd. That's not useful. But it inserts ambiguity. And this ambiguity was actually explained by Euclid, probably paraphrasing Euclid, who said that an image can actually be explained by an infinite combination of focal lengths and object depths. How many of you agree with that? And why is that? Why is that the case? Small x equals f, capital X divided by z. Camera model, projective, pinhole camera. That rule means that there is always an infinite set of possible depths and focal lengths that explain the same image. Yes? I'm paraphrasing Euclid. Okay, great. Okay, so this means now that, remember, my model needs to predict depth. And even though I know the focal length, the space of prediction that I have has many modes because of this ambiguity, which means that making a network predict in the space that has many modes is the worst thing you can do. Neural networks are great at detecting modes, are predicting modes. Are seeking modes. They're not good at doing other things. So you want to create a space for the model that is unimodal, that has a one mode, so that it is able to perform well. So what we do with this in mind, we actually do not operate in this world space of these ambiguous Z's that can be anything. And we operate in this virtual camera space, which assumes that all of the images in our data set are taken by one sensor of a specific image height and a specific focal length. And it turns out, thanks to trigonometry and thanks to Euclid, that there's a way, very simple way in which you can actually convert the world space into the virtual space. And now this virtual space is actually much more friendly for neural networks to predict depth.
We have the workshop paper presentations.
Yeah, so there's more detail and more discussion in the paper, but I want to kind of tell you a little bit about the benefits of virtual cameras, because there is an added benefit that we're not discussing right now. So the first benefit is that now I can train my QBER CNN on all of these images that were captured by all of these many sensors, which is something that I have in Omni3D. And now you're going to tell me, okay, Georgia, but like 3D object detection has been happening for many years. Why are you the first person to have to deal with this ambiguity and have to resolve it? Well, the problem is that all the previous 3D methods that were doing 3D object detection were working on a single data set captured with a single domain. And when that is the case, you don't have this ambiguity. You can just, you overfit to the sensor. But when you're trying to train this model in Omni3D, which is this concatenation of all of these data sets, now you're all of a sudden faced with this problem. And then there's another added benefit. Now I can finally train my object detector in 3D with data augmentations. I'm sure a lot of you train object detectors. You know that data augmentation, scaling images, is the most impactful way of getting to robust and good performance. You take your image, you scale it, and then you crop it perhaps, and you go on with your setup. Scaling images, so data augmentations have the same exact effect as sensor ambiguity. And prior methods were actually shying away from using data augmentations when they trained these detectors. Yes, previous methods of 3D object detection were not using data augmentations. That sounds bizarre, but that was the case. And so what we're doing right now with this virtual camera is actually allowing us to train our object detectors, bringing back the powerful, though hacky, I agree, but very powerful data augmentation schemes, which are so useful for training good object detection systems.
Thank you for your okay.
Someone's unmuted, yeah.
I would like to start with vision question answering as just a general kind of introduction. VQA is a inherently multimodal task where we have an image and corresponding text. And the
Wait, maybe I can find them. Hold on.
Answer the question. So in this case, you have an image of a person with a banana mustache, and the question: what is the mustache made out of?
Okay.
Okay, great. Okay. And then, okay, great. A lot of people are multitasking apparently. Okay, I know I've covered a lot of things, and that is the one lesson of a lecture. Don't try to jam a lot of things into one lecture. But the final thing I wanted to say is just about how to model object rotation. And we have a very nice discussion of why we actually picked allocentric versus egocentric. And I'm going to just sort of skip that. But if you want to know about why we made this choice, please go to the paper and read more. And maybe I want to convince you that all of these things that I try to discuss or present today actually do have impact on performance. So the first ablation is the impact of virtual cameras. And here I'm showing you our model QBER CNN trained in its final version. This is the yellow bar. The first bar is without virtual depth, without virtual cameras. And the second bar is a model trained with augmentations, but they're not controlled with virtual cameras. And you see how both of these versions actually suffer because of the lack of virtual cameras. And when you add that feature in, you're actually seeing a very healthy gain in performance. Another thing is that virtual cameras are actually not a feature that's specific to QBER CNN. That can actually be a feature that is applied to all models. And we did exactly that. And we saw how various methods are actually gaining in performance by having this feature enabled. And finally, all of the other designs that we have, like the 3D uncertainty with disentanglement, which all lead to healthy gains. So the 3D uncertainty, without 3D uncertainty, there's a big gap in performance. So 3D uncertainty is actually good. And without this entanglement means that we actually did search over the possible loss that we have. So we expected things to be the same, but with using much more compute. And the final version, where we don't actually have to have all of these discussions and ambiguities about what losses to use and how to tune them, actually does even a little bit better than grid search, which is fantastic. And finally, I know I need to show some images. So here's some detections, some outputs, some predictions on images for scenes from a single image. So what you see here is the input image. In the second column, you see the detection superimposed and also a top view of the detections, where again, this is a 1 meter cross 1 meter tile, just for you to understand the scale of the scene. A few more. Some urban scenes to keep the urban people happy. And here are also some results from Coco images. We don't know the focal length, but we set it to a value which is like a common value that modern sensors use for images. Some other images, and perhaps one of the most exciting results that we actually took QBursin in and we applied it at a frame-by-frame basis to a capture from this AR headset from Project Aria. It's like these glasses that are kind of nerdy looking, but they're nice. They have all of these cameras, so you can actually capture as you walk through scenes, and they actually have poses with it. So what we can do now is that actually we can track objects, detect and track objects at the same time. Okay, and I know that I'm a little bit over time, and of course, all methods have limitations. Actually, this is a very unsolved problem. You saw performance was at 24% IP. That's very low, so huge room for improvement. And now that you have a data set, you have a baseline, this is a great problem to start working on. So the limitations here are definitely when you have object configurations and layouts that are out of domain, like this case right here, where the model really doesn't really know what to do. It really doesn't want to predict the two cars, a truck and a car actually within each other. It has never seen that before, so it's really struggling with that. And other similar cases where you have some sort of out of distribution layouts in the scene. Oof. I'm done. Thank you.
If you have any questions, you can just come to the, yeah.
Thanks, Professor Georgia. Thanks for the great talk. I'm a Chinese student. I have a question for you. So I have said that we assume a virtual camera, right? So we can avoid a lot of inconsistent ground truths I assume the constant focal length, but we also assume that we have the camera that look front, not look from any angles, but our image is not that ideal, right? So
where is your camera? Where is your image not ideal? I didn't get that.
But I think we assume that model is kind of we assume that the virtual camera has a constant focal length and it's may look front, right?
Yeah, so nothing changes in the camera. The only thing that changes that we kind of play around a little bit with the height and the focal length.
Yeah.
But nothing changes in the visual domain.
I see, but
here's just like the space. Now you're operating at a space, but by doing this normalization in this virtual camera space, you're operating this virtual depth space, which is not the world space, but it's normalized so that it has a single mode rather than this ambiguity of multiple modes.
Yeah, I understand. So afterward, we have to get the result.
You have to revert back.
Yeah, so we use something like PNP to convert between the.
No, it's an equation.
Yeah. And there will be a lot of this back and forward conversion.
No, so because it's actually a closed form solution, there's no loss. It's lossless. Like you don't sacrifice anything.
But afterward, the model assumes everything is shot by a camera that has constant focal length, right? So
yeah, so we're converting we're converting cameras to do a single camera. Camera here is defined by the focal length.
Yeah, but it's
Maybe we can take this offline. I think that I kind of understand your confusion.
yeah.
But maybe, yeah, we can talk after.
Okay, thank you.
Yeah.
So your tool using the 3D uncertainty is quite interesting. Could you say more about how to estimate 3D uncertainty? Are there analytical methods or?
It's just an output of the neural, it's just an output of the neural net. So if you look back at the model architecture, these are all the 3D box properties, and this is uncertainty. There's a scalar that's predicted for every detection.
Do you need to use any specific architecture to generate this, or how much trust can you have on this?
How much trust can you have on this? I think that it was actually, I don't even think that we do any clipping. I think the model, I think it does make training a little bit stable at the beginning, but it actually, I don't know if Garrick is Garrick here? I don't know if he's here, but yeah, yeah. Yes, Mr. Advisor.
So how are you dealing with so you're not using categories in any specific way, so it's category agnostic and whatever you have in the data, right?
Correct.
Now, if there is a category which has a fair amount of size variation, then does that not land up introducing an ambiguity? So if you have humans, then we land up estimating their distance based on the fact that we assume they're all like 5 feet 6 inches.
Right.
Now, if you have, for example, big cars and toy cars and so forth,
Yeah, I think.
What are the consequences of that?
What are the consequences? That's a great question. We don't make any assumptions whatsoever. It is whatever the data has. So if we never see a toy car and at test time we're giving a toy car, I think the model will assume that it's not a toy car. However, it will play, it's very likely. I actually don't know if we have, I see you, hi. Have we tried any examples where adversarial like that, where we try to fool the model? I want to, this is a great suggestion. I want to try it because I also wonder whether the contextual cues will help it.
Yeah, so that's a trade-off. See, getting some benefit from the, say, the spatial layout and other objects and so forth. And what I want to understand is if the reasoning was totally local, then you are screwed. Then it has to just estimate the wrong distance. But if the reasoning captures some spatial layout, then you have a chance to recover.
Correct. I think we should investigate that. But we haven't looked. I mean, it's a great suggestion. We should look into. Yeah.
So to follow up on the question, so you have some like a pose definition for the objects, right? So but like
rotation, yeah.
Yeah. So for Dalek, so to define a proper pose, do you need to assume some kind of
yes. So it's not a pose. It's not a pose like a canonical pose, like this chair. The back means that it always has to be shifted right. We made this design actually on purpose because most objects don't have a definition of a canonical pose. Like a bottle doesn't have a canonical pose because it's symmetric. Pose for us means the rotation of the 3D object so that it tightly matches the object. So it's not axis aligned. It's not an axis aligned prediction. It's a rotator prediction to tightly capture the object.
So how do you handle this object? Like if you have some kind of symmetric.
Yeah. So this is where the chamfer distance comes in. And that's why it's a great loss because it makes it. You don't have a loss in the pose. You have a loss in the 3D points. So it's all about bringing the 3D points together, no matter what pose that is. This is the other benefit, but I didn't. This is extreme detail, and I didn't want to confuse everyone. Yeah.
So about the virtual camera. So first, there are these losses in depth estimation that try to handle the same issue because many of the depth estimation, they're not about 3D bounding boxes, but that has the same ambiguity, right?
Correct.
If you see focal length changing, you don't know how far the object is. Like there are these inverse losses that are optimization, so they're off by the actual loss by a coefficient plus a constant. So
Correct.
it seems like to be capturing some of that. And
So one of these methods is actually doing this.
okay.
It's actually.
But what is the difference? I think mathematically aren't they equivalent? Linear transformation that is.
I think that they're trying. I don't I don't remember in this particular case, but here they also try to normalize with a focal length, something along that.
They do a linear normalization per image. So there's like a shift of a constant and then projecting into a fixed state.
Yeah.
Which I think if your equation is basically like focal length is a coefficient. And you don't have that offset too. So I'm not sure how they're different.
Yeah, but I'll have to check the particular work, but there is a family of 3D object detector methods that are trying to be sensitive to focal length, but I think that they're missing. I don't remember exactly. I'll have to go back and read them.
Most appear in the depth because 3D object detection is more new, but depth
Correct. And honestly, depth is the biggest culprit here.
And
predicting
is your
that.
Z now actual metric depth? Because but then you're losing the focal length. How do you?
No, but we're converting back. So we're predicting in virtual space. Come on, slide, update. We're predicting in virtual space, and then we're predicting depth in virtual space, and then we invert it to get back to world space with this equation.
But do you predict the focal length?
No, we assume we know a focal length.
Oh, okay.
But even with a known focal length, because you have many focal lengths, it's still a very ambiguous problem.
Sure, but at test time, you assume the sensor.
Yes. At test time, we assume focal length, yeah.
The next session offline. Yes.
Okay, I see a question. Maybe we'll take it, yeah.
All right. Thank you so much for the talk and excellent time.
Thank you, guys. Start sharing. This is my laptop.
Yeah, this is yours.
Discombobulated.
Zoom link? Yeah, you can join the Zoom and then doesn't. Yeah, it comes to your own laptop. The same. So Zoom link can share. Yeah. Right. So our next speaker is Professor Saurabh Gupta. So Gupta is a assistant professor at UIUC. He works on computer vision, robotics, and machine learning. And he's interested in building agents that can intelligently interact with physical world and around them. And his current focus is on two aspects: choice and design of representation that enable such interaction, and what and how to learn the active interaction. All right. So let's welcome Saurabh.
Oh, I need to join this Zoom?
It's okay. You're already on the Zoom.
Okay.
You just say, yeah, sorry. Yeah.
All right. Thanks a lot for the kind introduction. Thanks a lot to everyone for coming. So today I'm going to talk about understanding and articulating articulated objects. I'll try to keep it brief so that you can all get to lunch. So articulated objects are all around us, right? Be it simple objects, everyday objects like cupboards and drawers, once what you have. These are simple 1 degree of freedom parts, which are found in varied scene geometries. To more, and they can have different kind of joints. You can have a prismatic joint, you can have a revolute joint, and so forth. We also have more complex objects. So here's a printer at my home. It's not just 1 degree of, it's not just one part, but there's a composition of many parts, right? So this part can come out, this part can rotate. But not just that it has many parts, but these are parts which are arranged in a hierarchy, right? So I can have this extension which can come out and so forth, right? And going further, we actually have other kinds of articulated objects. And in this case, it's not even a fully rigid articulation, but it's also not completely free from articulation. So I'm talking about these plants that you're seeing on the very right-hand side. If you consider each leaf, there is some axis along which it can actually rotate. It can be moved quite a bit. But there are other axes along which it can actually not move very much. So in this talk today, what I'll try to show some work which tackles some problems in this context. In the first piece, I'll talk about how can we articulate 1 degree of freedom objects in varied scene geometries. Then I'll talk about how can we infer articulable models for complex articulated objects, which have like this kind of a tree structure. And finally, I'll try to give a teaser about how can we manipulate articulated objects with complex dynamics. Okay, so let's get started. So this first piece is, this is actually a paper at ICRA 2023, work led by Arjun Gupta, who's my student in my lab. And the task we were interested in over here was to articulate these everyday objects, right? So these single 1 degree of freedom kind of things, right? And this problem is interesting because when you start doing motion planning with these things, if you're not quite accurate, if the robot is off, if you end up outputting a motion trajectory, which doesn't exactly articulate the object as it should, you will experience large amount of forces, and either the drawer will break or the robot will break, right? And we don't want either of those things to happen. So in this work, we were designing an approach which can output precise motion plans which can articulate these objects, right? So that's kind of the problem we are interested in. So the classical approach to solve this problem would be as follows. At test time, I'll be given some sensory observation. I'll have, let's say, a vision system, maybe like one that some version of what Georgie has described, which let's say can estimate the articulation geometry, and it gives me waypoints that I want to follow, right? But I still need to translate these waypoints into end effector, into joint angles that the robot should be at, such that it can actually successfully achieve these waypoints while also continuously moving the arm along these waypoints, right? And you can do that. You can do that with motion planners, and you can output motion plans which will actually do this job for you. But this is not a trivial motion planning problem. This is a constrained motion planning problem, because you want the end effector to follow the specific constraint that you have to follow, right? And so if this classical approach suffers from two limitations. One, it has high sensing cost, because to be able to actually output motion plans, you also need to reason about scene geometry and what will collide with what and so forth as you articulate the object. And the motion planning problem is also not so easy because of this extra constraints that you have to deal with. So in this work, the key insight that we have is that we will leverage past experience of solving similar problems in order to speed up this process at inference time. Right. So instead of working in isolation on one instance that I have to solve, I'm going to try to, at training time, try to solve a lot of motion planning problems and compile my solutions into some canonical motion plans that I can now quickly use at test time. Right. So at training time, I'll have a data set of inputs, scans and so forth with full information. I'll spend the motion planning time to actually generate solutions. I'll get a data set of motion plans. And then I'll train a machine learning model, which can actually output these motion plans. And there's a detail that I'll get into. We don't directly output the motion plans. We are going to output a representation for a motion plan, which will then decode into a motion plan that we'll actually execute on. Right? So this is what we are going to do. And at inference time, it's simple. We will essentially use the machine learning model to output this representation for the motion plan, and then we'll decode it into a motion plan. Right? Okay, so that's kind of what we're doing. So there are three parts to getting this to work. The first is we need to build this data set. The second is we need to develop this motion plan representation, which we can efficiently decode. And the third is we need to develop this machine learning model. Okay, okay. Good. So we are building this simulator on top of this HM3D effort from Facebook, which is a large number of, it's a collection of indoor scans, but these don't have any articulated objects. What we have done is you take these 3D scans, but then you add some lightweight annotation on top to start simulating simple kinematic objects, right? So you have this image of a kitchen. You can mark out, okay, this is the face of the cupboard. There's the handle. And because you have the underlying scene geometry associated with this image available in these scans, you can actually start simulating. You can lift these annotations to 3D, and you can start simulating, that this cupboard is opening and so forth, right? Now this is essentially articulation geometry for an object which is placed in an actual scene, not in isolation in ShapeNet. Plus, you get real appearance to work with, right? So it's not synthetic; it's actually real pixels that we can train models on. Right? Okay, so that's our data set. Now, the second thing, so we have done, I think these are 100 scenes that we have annotated these objects in. We have about 4,000 articulated objects, including basically 4 types of joints. So prismatic, 2 types of joints, prismatic and hinge joints, but hinge joints can be in different things. Like you can be opening an oven, or you can be opening a cupboard and so forth, right? Okay, so this is the data set. Now, let me tell you about our representation for motion plans. And this is actually built upon inverse kinematics that some of you may be familiar with, where essentially inverse kinematics is a process that I have some end effector pose, and I'm trying to figure out the joint angles that my robot should be at, such that the end effector is at the pose that I want it to be at, right? And this process is, you can solve this using inverse kinematics. And what we are doing is solve a sequence of inverse kinematics problems one after another, right? So you take the first waypoint, you get the joint angles. You take the second waypoint, get the joint angles, and so forth. And now note that we are not solving these inverse kinematics problems independently, but we are going to solve them. We're going to warm start the inverse kinematics for the second waypoint from the solution of the inverse kinematics for the first waypoint, right? And just in case you don't know about inverse kinematics, it is basically, you can think of it as gradient-based optimization to output joint angles that will lead the end effector to a desired pose, right? Okay, and because we are synchronizing them by warm starting from one to the other, you can actually interpolate in the joint angle space, and that doesn't cause the end effector to deviate too much. It still follows the trajectory that you would like to follow. If you're familiar with trajectory optimization in robotics literature, you can actually view this process as simplified trajectory optimization, where we are not doing any collision checking. We are not, we're just solving this one optimization problem, right? Okay. Good. So this is a motion plan, and it turns out this actually works quite well. This is a trajectory that you can find with this kind of with sequential inverse kinematics. And note the deviations; they're very low, so it's very precise trajectories, and we can do this fast. This is just optimizing this trajectory takes less than a second, much less than a second. This is unoptimized implementations and whatnot. We compared it with existing motion planning libraries. So you can do unconstrained motion planning, and that will obviously do the wrong thing. The end effector will fly between different poses because they're not accurate. You can do constrained motion planning, which is a whole subfield in motion planning. At least the public implementations we tried, even after giving 15 minutes, it would find trajectories which kind of make sense, but are not exactly accurate. Right? Whereas we can actually get trajectories very fast, very quickly, very good, very fast. Now, this all still has this problem that I need to figure out the right theta zero, right? So there is still an initialization that is involved, and getting the initialization right is important. If you don't, if you change theta naught, you'll get a different motion plan, and that might intersect with the environment, or it might actually not be able to fulfill the task and such. So this theta naught has to be, you have to be intelligent about picking the right theta naught. And so instead of searching for motion plans, we are now instead going to search for theta zeros, which is the initialization for my inverse kinematics process. And that's kind of where we bring in learning, which is that you have an image, you have a target object that you want to articulate. We train a neural network, which is going to output good initializations for articulating this specific object. And this is done using our simulator in this case, where we, ahead of time, just try all theta zeros. We figure out what are good initializations for the robot arm and where the base is and so forth, and try them all out. And here's a heat map. You can think of if theta zero comprises of base locations and so forth. For each location, you can compute whether this worked out or not for this particular instance, and then you can train this network using supervised learning. To do inference, you do this process. You do some internal collision checking based on the geometry that's available only from your onboard camera. You don't need a full scan. So you can do this kind of internal checking. So you get multiple predictions, but then you can pick the one that passes this internal check and you return that as the motion plan. Right? Okay, good. So we have done this, and this is these are results on our data set. And what you can see is I'm basically plotting on the x-axis how many solutions you need to try, and on the y-axis, did the motion plan succeed or not, right? And so this is like the complexity of the internal collision checking, internal checks, how many you need to do. And what you can see is that given a fixed budget of number of solutions you want to evaluate or you want to try, you get more successes and you can get them very fast. So even the first few solutions you try end up working out and you can return them. And that's kind of what the neural network was trying to learn and such. We also tried, other obvious baselines. We tried imitation learning, which surprisingly we could not get to work, presumably because it was getting the coarse motion right, but it wasn't able to get the fine, the tolerances. It was beyond the tolerances that we were interested in. Right? Okay, and here are some visualizations of the motion plans that we are able to output, and it you can see these are pretty good motion plans. Right? Okay, good. Maybe I'll pause here for any questions on this part before I move on to the next. Okay, if not, let's keep going. Now, this worked well because we could easily create kinematic simulations for simple one-off objects in real-world scenes, right? If you wanted to do the same thing for more complex objects, that's not quite straightforward because we don't have an easy way of creating these kind of kinematic simulations for more complex objects. And that's kind of what I'll tell you next, which is how can we create kinematic simulations for complex objects and such, right? Yeah, so that brings me to this second part of this talk where I'll describe this. And this is actually a paper at CVPR, which is work led by Xiaowei. He's actually around for the conference. If you are interested in chatting with him and in getting into the nitty-gritty things, there's a poster on Thursday afternoon that you can go and visit. But in this CVPR paper, we are basically the target is we are building rearticulable models for arbitrary 3D objects from 4D point clouds. So I have a 4D point cloud that is as input, right? So it's a point cloud that you have recorded a sequence of. And what we want to do is we want to output a rearticulable model, which is we want to identify what are the different parts of this object. We want to identify how these parts are connected to one another and how they are moving with respect to one another, right? So this is, in some sense, if you work with robots and so forth, this is essentially akin to, we want to output a URDF file for this particular object, right? And once you have this, you can actually rearticulate this object in arbitrary ways, right? And you can have a retargeting application that I want to get this. I mean, this could be for reanimation, if you will. We want this point over here, and so forth. And now you can actually solve for the articulation of the different joints, which will get the robot to be in, get this object to be in the pose that you want it to be in. And crucially, we're not trying to do this in a category specific way, but we are going to try to do this in a category agnostic way. So we want to be able to handle arbitrary objects without any category information. So the same model that I like to train, that whatever method I have should be able to work for this robot, but should also be able to work for this sunglasses and so forth. Right? Okay. So that's kind of the problem we are interested in tackling, right? So this thing is motion. This is the 4D point cloud. This is the rearticulable model, part segmentation, skeleton motion, and this is the reanimation, right? We can actually articulate this and regenerate things, right? Okay, good. So that's kind of the problem we are interested in. And specifically in this work, we are focusing on objects which have a collection of 1 degree of freedom joints attached in arbitrary kinematic trees, right? And if you look at everyday objects, which are man-made objects, that's kind of a very dominant mode of articulation in these. You can look at this collection of objects, right? And if you also notice, these have 2 types of joints. There's revolute joints and there's prismatic joints. And what we would like to do is what we're trying to do is to tackle these kind of objects. Okay. There's obviously a lot of past work on this problem. Crucially, I think past work either tackles category specific, builds category specific models. So if you can build specific models for humans and quadrupeds and so forth, or people actually do category agnostic, but they either work with fixed kinematic trees or they do not have realistic joint constraints. Whereas what we are trying to do is we are trying to tackle arbitrary parts and categories with realistic joint constraints and reasonable kinematic structure jointly, right? Okay, so how do we do this? So we start with the articulable model. So it comes with a kinematic tree that what part is connected to what other part. We need to define some way of identifying what part is in this point cloud. That we do using an implicit function, which takes in the canonical frame of the canonical point cloud. And we essentially learn a function f. It's an implicit part field, which takes in the coordinate of the point and outputs what part it is in, right? So this is our kinematic tree and the canonical segmentation. And then we have essentially articulation parameters. And we represent these using screw parameters, but you could use other things as well, which is essentially defining where is the joint, what is the axis of the joint and where it is located, right? So that's the screw parameterization of the thing. But you also need the state of the screw, which is, how much have I articulated the object, and, if it's a translation joint, then how much I've translated it, right? So that all falls through nicely in this, screw parameterization that past papers have also adopted, and we are also using the same. Okay, so this is kind of the model that I'm trying to estimate. I want to estimate the kinematic tree, I want to estimate the segmentation, and I want to estimate the location of these different joints and their types. Okay, so model that we want to estimate. And we are going to estimate this by analysis by synthesis approach, where we have point clouds which are in different articulation states. We want to find the articulation states for each of these point cloud, for each of these frames that I've been given, such that I will match the point cloud that I'm observing, right? So I'm trying to optimize over these model parameters. So it's like skeleton, like the kinematic structure, the segmentation, the screw parameters, the screw states, such that the articulated point cloud that I'll get after articulation matches the observed point cloud that I've been given at different time steps, right? And we do this, we have a couple of losses here, one which measures the geometry match using chamfer distance and also earth mover distance, and the flow loss, which is how is the part moving and how do I think the part is moving, right? So we have both of these terms which do this. Now, this is nice and good, but the unfortunate thing is we are trying to optimize over weird things. The kinematic tree is a discrete structure, you know, and the continuous and other variables are continuous. This causes problems. You know, you have structured constraints on the parts that can only be a tree and so forth. So it's challenging to optimize this directly. Instead, what we are going to do is we are going to do a relax and project kind of an approach, where we first fit a relaxed model, where we estimate each part motion independently. We do not enforce this constraint that these are 1 degree of freedom objects, or that this part has to move relative to this part, and so forth. We estimate each part moving independently. Once we have some estimates over there, we then project to a valid solution. And a valid solution for us is essentially a kinematic tree where I can link up all these parts such that things still make sense. And then we do a little bit more fine tuning by essentially using the same optimization function, but with like fewer things. We don't change the discrete variables, we only learn the continuous parameters. So that's kind of what we are doing over here, right? So the relaxation is we're not optimizing over the kinematic tree. We are not optimized. We are not using screw parameters here. We are actually using free form transformations denoted by TIs, and we're just optimizing this function. This gives us, you know, the motion of each part and, you know, the part segmentation. Once we get this, we essentially project it down into a valid kinematic tree based articulated model by essentially using, you know, that once I reduce it to a tree, I mean, the residuals that I get should be small, right? So that's kind of what we're doing over here. And the fine tuning is just this direct optimization in the final articulated model space that we're interested in. Okay, so this is like a little bit of an animation of how this happens. So we are interested in optimizing this loss function that we have set up under the constraint that the joints are constrained. We can't quite do that. We are not exactly doing that. We are solving a relaxed problem where we essentially reason about 6 of piecewise rigid transformations. We solve this relaxed problem. And then once we have solved this relaxed problem, then we project to the kinematic constraints, and then we you know, fine tune further to actually estimate each of these things. And this actually works quite well. So you can take in a point cloud sequence of the form that you're seeing on the left-hand side. You can actually infer, I'm showing you the inferred part segmentation, the skeleton, the motion, and, you know, some reanimation results. So for a complex object, this actually works quite well, right? You can do another robot. I mean, you can have one articulated object, you can have another articulated object, and it kind of does it's able to handle them. The same model is able to handle them. I mean, there's no learning as such. I mean, there's test time optimization. So it's obvious that it can actually handle it. So that works out. We compared to past works which have looked at this problem, and you can see our segmentations are more accurate and our skeletons are more accurate as well. You can have quantitative metrics. I'm not going to go into the details. You can refer to them in the paper. We have thorough sort of ablations where we have, you know, tested the different parts of the system, and all of them seem to help and such, right? Okay, so we have actually, so some of those results were on synthetic scenes that we had created, but you can actually do this on real world objects as well. So here's an object that you can articulate in different ways. You can record this point cloud video. You can reconstruct it using nice apps that you get on phones these days. And now you can actually pass it into a system, and you can infer the part segmentation, the motion, and you can actually reanimate this object, right? Yeah, so this was about how we can infer complex arrangement of parts and such. I'll pause if people have any comments or questions at this point. Yes, please.
Sure. So is like complete point cloud necessary?
Yeah, that's an excellent point. We in the simulated experiments we had access to the complete point cloud. In the real world experiments, we don't have access to the full point cloud at all time steps, right? Because as you start moving this thing down, then certain more points become visible. Yes. It kind of works in this setting, but not as well. Like the printer that I showed, right? That has like so many hidden parts. When you open it, then like whole new geometry becomes available. So we have tested it on some real world objects where this is a challenge, but I think yeah, it's a good, excellent point. Yeah. Yes.
This technique, do you have any transfer from having seen similar categories where, I mean, similar kind of patterns before? Because if you are doing initial reasoning, and the next time you see another draw, you have to figure it out from scratch.
Yeah. So there's a contrast in the first work. That's what we were doing. We were doing transfer across category. In the second one, it's entirely test time optimization. So there is no priors. There's some training that we do where we are learning the correspondence network across categories, and that generalizes across categories. Like we need to estimate, as I'm moving, I need to estimate correspondences to compute the flow loss and so forth. So that network is being learned, but that transfers, and that's, others have shown that result in the past. For the test time optimization, we are not doing that, and that will be useful because this optimization is a nasty one. And if we had some way of sharing this sharing this optimization over lots of objects, then that will help. Excellent point. Yeah. Okay, I think I might have a little more time that I'll talk about manipulating articulated objects with complex dynamics. So this is some work with Erin Zhang, who is another student in my lab, and this is called learning to look behind plant foliage by moving it. The problem we're interested in, this plant self-occlusion problem. So if you look at plants occlude the space behind them, right? So there is foliage. You are, let's say, trying to find whether your fruit has grown, or you're trying to see if there is some infestation that has happened. You will have to move these leaves aside in order to actually see what is behind the plant, right? So any kind of agriculture application or farming application, this would be a problem that you will be confronted with, right? And that's kind of the problem we are interested in tackling over here, which is we want to be able to articulate the plant, or hopefully not murder the plant, by moving the leaves around. And we want to learn how do leaves move, where can you interact with these leaves, and then actually learn robot policies which can actually do it. So this is some results that we have. I mean, the plant has survived all the experimentation we have done, so we have not harmed the plant too much. But what you're seeing here is basically the task is we want to look behind these leaves by moving them. So we are going to, the policy that the robot learns is to actually how to move these leaves around in order to reveal the space that is behind it, right? Now, this is a 3D problem. This is, we want to learn how do leaves and plants articulate, and, how do you represent these? I mean, these are all actually very good questions. I think we have just started scratching the surface of this problem. And this is actually quite challenging because, sensing is difficult. You are actually not seeing the full object. You're only seeing a part of an object. There's extreme clutter. There are thin structures like vines and branches and so forth. There's partial observability, right? So any kind of model building that you would want to do, any kind of, let's say, model-based RL you would like to do, you kind of need to build a model. And if you have partial observability, that is kind of difficult, right? So it's an interesting problem. And what we are doing is some data-driven learning methods to directly try to estimate what we want to estimate. Now, if you look at existing work in manipulation, I think there's no good simulator for plants. Please, if there is someone in the room who has a good simulator for plants, please come in. Let me know. I'll be very curious. It will be very useful for us. So there's no, I mean, to the best of our knowledge, no high fidelity simulator for these kind of things. There's unknown dynamics of the plant and the leaves and the branch and so forth, right? So that makes it difficult to use typical model-free RL, model-based RL and such. What we are doing is we are essentially collecting data for this specific task directly in this real world using self-supervision. And that's kind of how we are tackling this. Specifically, what we do is we predict the outcome of input actions. And the task we're interested in is where will space be revealed after executing an action. So we are training models which can take in an image, take in a candidate action, and try to predict where will space be revealed on execution of this action. So here is our setup. We have this robot, this plant inside this robot. We have this camera that is mounted on the top. This is a view you're getting from there. You can see the space that the leaves are occluding. and such, right? This is, this is where we want to reveal the space. This is the action space. The actions that we're working with are essentially, you sample a 3D location XYZ, you sample a direction, and you do a non-prehensile push in that direction. You poke the gripper at that location, you convey it a distance d in a particular direction theta, and that's the action space we're working with. So we are consciously not, touching leaves and flipping them over, partly because we don't know how they will behave, and this is just the first step, and those things would be to follow. Okay, so here is the approach. We have RGB-D images in this case, so RGB image and the height image from the camera. We have some estimate of the space that has been currently revealed. We do cross-entropy method, so it's nothing fancy, which essentially evaluates actions using a neural network that has been learned that given this situation and the action that I'm going to apply, so it's a push in the vertical direction, where will space be revealed if I do this, right? So this is a neural network that we train, and I'll tell you more about that in a bit. This predicts some space, and what CM does is it takes a union of the new space that will be revealed and the old space that has been revealed already, and tries to compute the best action based on how much new space will be revealed, right? And then it searches over some number of actions and then spits out the action that will reveal that reveals the most space. Now, note over here, we need to characterize where all space will get revealed, not just how much space is revealed. Because if you just output a scalar, which is how much space is revealed, that is not useful in terms of chaining actions together to have this long-term behavior. That's why in this model, we are trying to predict where exactly revealed rather than total how much space is being revealed, which is what past work with supervision would do, where they would just predict the grasping outcome and such, right? Okay, so this happens, you figure out the best action, you execute that action, you recompute what space got revealed, and then you keep doing this over and over again. Okay, so at the heart of this is this neural network that has been learned to predict what space will be revealed. So we have this, as I said, RGB and height images. We pass them through an encoder-decoder network. We represent the action using, where it was executed and in what direction was it executed. All of that gets passed into this encoder-decoder network. It has skip connections and so forth, and it predicts probability of revealing space, right? So these are space revealed prediction network. Could not come up with a better name. Yeah, as I said, we collected data in a self-supervised way. We just try different actions. We compute the outcome of this action, and we compute how much space got revealed and just collect a data set. In this case, it was some 2,200 interactions collected over 18 hours. So that's what we have. And now we can start playing with this model and seeing what it does. So the goal is maximize the cumulative space revealed over a 10 time step episode. And the metric is space revealed in number of pixels in this case. And we compare again some interesting baselines. So the first baseline is a tiling baseline, where you essentially, the students sat down and designed that these are actions which are most likely to reveal the most space. So these are like tangential to the leaves and so forth. And you have to sample 10 of them, and you sample them such that they are all spread apart. So that's kind of how you sample these actions. So that's one baseline. There's another baseline, which is you can not use this learned dynamics model, but you can actually work with a handcrafted dynamics model, right? So instead of using SRPNet in this CM input to CM, we actually use a handcrafted dynamics model, which is actually just the simple dynamics that as you move the gripper, these are radial leaves which will get revealed and such, right? So that's a handcrafted dynamics model. And then you can actually, there's another baseline, which is you can replace it with a model which does not receive any visual input and so forth. So these are the different methods we compared. You can see, here is a plot which is showing how much space got revealed as a function of number of time steps. And you can see that we are revealing the most number of pixels as opposed to these baseline methods. We have a very high camera, so you have pixels which are 64,000. And over the most competitive baseline by a very large amount. And this essentially suggests that you need learning to model behavior of these kind of complex objects. Just handcrafting, just thinking that, oh, it's a simple model of this form actually doesn't work. It's able to leverage the visual observations. It's not just coming from, the improvements are not just coming from keeping track of what space got revealed where, but also, looking at the image and making predictions that, okay, are more effective than other actions and such, right? So it can use the visual information well. We can do other things with this. You can actually do targeted reveal, which is, I want to look behind this particular leaf, right? And again, we are comparing against these same baseline methods. We see we are able to look behind a specific described leaf quite effectively, right? So we're getting an improvement here as well. We have done actually all of this for another plant. So in this case, these are synthetic vines, where we essentially have different configurations of these vines, and we've repeated this experiment in this setting as well, and we get improvements in this as well. Okay, so to summarize, I think what I showed you today was 3 different aspects of dealing with articulated objects around us. The first was, how can you output motion plans, or like precise motion plans for articulating 1 degree of freedom objects in varied scene geometries. Second was, how can we infer re-articulable models for articulated objects through point cloud observations. And the last one was, how can we manipulate articulated objects which have complex dynamics. There are many things that I like to discuss. I think what Georgia was also saying, like when we have output 3D geometry in some way for us, will be actually errors. And how can you design control strategies which are robust to these 3D estimation errors? I think that's something that we should be thinking about. We should be thinking about how can we scale up 3D articulated models through RGB video observations as opposed to point cloud observations that I described today. And the last one I like to bring up is, how can we build 3D representations for plants, right? I mean, should I do voxels? Should I do implicit surfaces? I mean, these things deform. What is the right way of thinking about them is something to think about. And with that, I'd like to thank you all for your attention and acknowledge the students who did all the amazing work. Thank you. Yes, yes.
So actually, I'm curious about second. You just mentioned that you have this correspondence model and then you do test combination. So how exactly is this correspondence model trained?
This correspondence model is trained on lots of ShapeNet-like objects, or like simulated objects, where you articulate them in different ways. And then you compute, because these are simulated, you know what the ground truth correspondence is, and we train with some Siamese laws. Kind of
objects are not articulated.
Oh, yeah. So PartNet, sorry, PartNet and the like. Yeah. And I think one important detail to notice is you resample the mesh when you render, when you do different time steps. If you don't resample the mesh, then it actually overfits on the local geometry, right? So yeah, and by the way, the code for the first 2 projects is already available online. The data set that we collected for the first project is already, you can actually look at it on my website. And yeah, so those details are available. Yes. Yeah. So right now we are thinking of in a task agnostic manner that we want to reveal as much space as possible. Of course, this should be done in context of applications that you are trying to find like a specific thing, or you're trying to investigate specific parts of the plant. We're not doing that partly because, then it'll become task specific, even more task specific. So right now it's more general. You can use for any kind of task, which involves reasoning about space. Yeah. Yes. Yeah. We don't. We are doing, when we are doing CEM, we are actually doing action rollouts with the horizon of 1. So it doesn't require that assumption. If you look, that is largely true for like these big leaf kind of plants. It's largely true. It's not exactly true, of course. With like more like vine-like things, I think it's less true. I think you might see that, okay, you did some interaction, then it doesn't come back to its original state. And that's again a complexity, right? Like when we are trying to compute the self-supervision for this plant case, you have to be quite careful in terms of how do you measure where you saw space, because you could just be moving the entire plant, right? And yes, that will reveal space, but that's not revealing space inside the plant. So we do some ICP actually to align it and then compute the revealed space. Good question. Yeah. Yes.
Thanks for the talk. And for the third part, I'm wondering if you plan to include more complex actions how the approach.
Yeah.
But I'm also curious about whether more complex
actions would actually destroy your plans?
Yeah, that's a very good question. So we are right now not dealing with, we have some sort of a threshold. If the robot experiences very large torques, then stop that action. But more complex action will actually be better. I think, in fact, for the vines, we started with actually the vines, and a much simpler action space works for that. The same simple action space actually doesn't work with this Priscina plant. We had to make it like a 3D action space. So I think that is, I think the reason why we did not do a more expressive action space is it includes, it further enlarges the sample complexity of learning, right? That now you have to reason about 6 trajectories of the gripper, which is harder. But we are trying to do that, I think, yeah. Okay, thanks a lot for your attention.
And that concludes our morning session. Please come back at like 1 p.m. with our afternoon session. Thank you. No problem. Thank you.
Get lunch? Yeah, sandwiches. Yeah. Hi. Hi. Once in a while I've not come, but that's not usually true. Okay. Yeah. Yeah.
So what is the
Yeah, it's 1 p.m. 1 p.m. Yeah, I'll make one slice for coffee for them.
Yeah. Yeah, so you can grab our quick lunch.
Yeah, sure. All right.
You have an afternoon agenda?
Yeah, sure. We have agenda is on the left. On the, oh, sorry, you mean the topics?
Yeah.
We don't actually track the topics from the speakers, so yeah, I guess it's mainly their like recent researches.
But there will be like 3 sections on that, like starting from 1 p.m.
Yeah, like two invited talks, 1 spotlight session, and 2 invited talks and panel discussion. Yeah, it's on the website. If you can.
I try to scan the QR code and also I mean much set up the speaker.
I see. A moment. I mean, this website.
You search for like the 3D vision and robotics 2023. I think the top one on Google.
Yeah, it's
You mind if I take a picture of that?
yeah, sure. You can take it.
Thanks.
Yeah, let me just show like what size will be back.
But you're gonna leave your laptop here.
Yeah, it's fine. I think it's fine. Okay. This is good, right?
Okay.
Sorry for what again. Very nice to meet you. So, I think that's the way of our video. Yes. Wonderful. Okay, I think we would love to do that because we're waiting for the department. So we have made we have mentioned I added like visiting the single part, but we have like connectivity. We have like a whole generator type of. Yes, it's fun. Yeah. So the visiting. Okay, okay, yeah, I was like one of the like happened was the next was I purposely put with the but like yeah, I realized yeah, that'll be great. So how would I send this? Everyone, yeah, yeah, thank you. Thanks. That's how you like it. No, thank you. Unless there's somebody pretending to be walking around, talking smack on
你先拿我这充会儿电，
我这儿有那个充电的。
啊，你也是，
插
插错，
能插是吧？
对，能插了。
行。
我也没找到，先找一下。嗯。
这还是因为有比赛做很多人。
但是没有担心情报。
你说 smart 吗？
对。
那 industrial lab 还是都挺对吧？都是。我的这种偏 research 的 industrial lab 真的或者都是。
那是他们做的最对啊。现在
但是就像 Gemini 是一个很大的 effort， 就是做 LLM， yeah， 一个是在对 focus 的，当然有各种各样的 team， 但是就它这个尽管其实很大的，现在和这个 Google Brain merge 之后，他们有3000，和 Google Research 3000，所以有这么庞大的 research 团队，但其实现在他们压力就挺大，因为没法真的做产品，然后那也太需要 fundamental research 或者那些做然后
Andy, are you online? Andy, are you online?
Yes, I am. Hello, can you hear me?
Yeah, great. We're waiting for people to come in, and yeah, and let's just wait for like a few minutes and also test the screen sharing as well as this audio. I think audio and video is pretty fine right now. We can see you on the big screen. Can you try like screen sharing?
Yeah.
You can see the screen, but oh yeah, we can see it clearly right now. Okay, great. Yeah, let's just wait like 1 or 2 minutes for people to come in the room.
Sure. So it's 40-minute slot, right?
Yes.
Okay, I'll try to stop a little early for questions.
Thank you. I think we're good to go now. So, hi everyone, welcome to the afternoon session of this workshop on 3D vision and robotics. And we'll start with Professor Andrew Davidson speak. Professor Andrew Davidson is a professor at ICL and leads the Dyson Robotics Laboratory. He pioneered SLAM with vision from mid-1990s onwards and brought the SLAM acronym and the methods from robotics to single camera computer vision, inspiring many researchers and industry developments in robotics and inside-out tracking of VR and AR. So let's welcome Professor Andrew Davidson.
Thank you very much. Yeah, so I've called my talk real-time 3D scene perception for robotics, and really my this workshop's about 3D vision and robotics, and my view is that yes, 3D vision is essential for robotics, but more than just 3D kind of single view vision and prediction. It's about 3D scene representation. So I really think that that's how we're going to progress on robotics. We need to keep working hard on this problem of how to go from images and other perceptions that a robot might get from its sensors and turning them into scene representations that we can then really use for robotics. So, I mean, that's something that I've believed going right back into my career. So, yeah, as was mentioned in the introduction, so I've spent a lot of my career working on visual SLAM. So this essential problem of cameras moving through the world, building maps of the scenes around them, and then doing localization relative to those maps. And that technology that I and others worked on going back to the 90s, is now really present in a range of products, some of which you would definitely think of as robots, such as robot vacuum cleaners, like this one from Dyson that I was personally involved in working on, or drones like this one from DJI, but also a lot of other types of products like AR, VR headsets, like mobile phones that do localization and mapping. So if you can go from the sensors that these products have, and they're primarily cameras, fused with other things like inertial sensing and odometry, you can build a representation of the scene around those devices, and that enables intelligent action. So in the case of a robot vacuum cleaner, for instance, it enables localization, and therefore it enables precise, deterministic cleaning. But I just think that's the basis that we need to just keep building on for robotics, and we'll be able to get further and further. So, one way to think about that is that SLAM is evolving into something much bigger. And I've been using this term spatial AI recently to really represent what I mean, and maybe what I was always interested in by working on SLAM, that these robots and devices with sensors should be building a kind of picture, a representation of the world around them that enables intelligent action. And the SLAM systems that are out there in products already are relatively simple in terms of the representations they build. So the key, most important representation is a sparse map of landmarks that enables localization, but we're already seeing additional layers of capability being added into products like this. So dense scene mapping, and also some capability for semantic understanding. I just think we need to keep working on this, and maybe these are not completely separate layers. Maybe they become much more intermingled. But that's the thing that will enable an embodied device to really interact usefully with its environment. So the general kind of discussion around this kind of topic of spatial AI, if you're interested in reading more of my thinking about that, I've got a couple of papers called Future Mapping 1 and 2. In particular, the first one, Future Mapping, the computational structure of spatial AI systems, really hones in on defining what a spatial AI system is. And it has this hypothesis that to enable embodied AI, a spatial AI system should build a persistent and understandable scene representation or world model, which is close to metric 3D geometry, at least locally. So I think that the representations that these robots need to be really useful will at least locally be quite metric. It is in the end the most useful sort of representation of scenes. But how good does that representation need to be? How accurate does it need to be metrically? What other sort of properties should that representation include? So it should certainly include semantic properties as well as just raw geometry. And then the other thing I'm really interested in, which I'll mention a little more at the end, is what is the computational patterns in terms of storage and computation that will really enable this? How can you make it efficient? And how does that relate to the hardware that we'll actually use to implement these systems? So another kind of discussion paper that I was involved in recently, which I think is very interesting to people thinking about 3D vision and robotics, is this one called Rearrangement, a challenge for embodied AI, together with a really interesting set of co-authors. So this is really thinking about a general class of robot problems that I think we can hold out as targets at the moment for the sort of things we might expect robots to be capable of in the future, that involve essentially rearranging scenes. So, a really tough example of this might be a robot that could tidy up a kitchen, for instance. So it involves, in my mind, really understanding that scene in detail. And it's hard for me to imagine a robot that could tidy a kitchen without building a really kind of quite high quality, persistent, close to metric 3D representation of that space, that it's always kind of moving around, localizing with respect to, and updating as it makes changes to the scene via manipulation. So I think we need these persistent, real-time updatable compositional scene representations. Okay, so having made that argument, let's look into a bit of detail, and in particular going through some of the things we've done in my lab over the last few years. So how are we going to represent scenes in a way that's useful for robotics? And I think this is very much still an open question. So definitely there are various kind of well-known classical ways of representing detailed 3D geometry that I still think are very useful things to think about. So for instance, we had some work, this is the system called Elastic Fusion from 2015, which is a depth camera based SLAM system that builds a dense 3D map of a scene using a circle representation. So if you zoom in close, you would see that this map is made up of millions of tiny little oriented disks. So it's a bit like a point cloud, but with a bit of extra surface information. So that's a representation that can fairly efficiently represent the surface shape of a scene in a lot of detail. Other well-known representations would be, meshes or volumetric grids of different types, or occupancy grids, or maybe sign distance function grids in methods like Connect Fusion. So very, very useful representations of geometry. We can also, add semantic layers to representations like that. So some of the earliest work that we did in that direction was in the work called Semantic Fusion. So this was basically taking Elastic Fusion and then combining that with a pre-trained off-the-shelf neural network that was able to label views with per pixel semantic identities. And what we would do in Semantic Fusion was essentially just fuse those per frame labels into our 3D circle representation. And we were, therefore starting to get this 3D labeled scene. But this worked well in some ways, but you can already see, also some of the problems. It was quite hard to do that consistently and accurately. But already we were, doing better than single view semantic labeling, because we were fusing information from lots of different views. So thinking about this question of representation, of course, what's happening recently is thinking more generally about neural representations of scenes. So having worked a lot on real-time 3D dense SLAM systems, once we heard about this new style of representing 3D scenes via directly neural networks, so obviously in methods like NeRF, so this idea that you could train an MLP in quite a general way to represent a scene, we immediately thought, well, could we actually make a real-time SLAM type of system based on this MLP idea? So this was the first work we did in that direction. So this system called IMAP, which was published at ICCV 21. So let me just show you the video of this. So the setup here is very similar to what we might have had in Elastic Fusion or any number of other kind of SLAM systems we've worked on. So a real-time camera being moved around in a room. And this is a depth camera, so it captures RGB and depth. But what we showed in this paper, so at the time when this work was first done, NeRF was something that was taking hours and hours to train, with pre-captured views, with camera estimation already done. Here we're doing all of that incrementally and online. So from the stream of RGB and depth views, so that's something that we did to make this easier than the NeRF problem. We're using depth images as well. And the other thing that we do that's a bit different from how NeRF normally runs is we're not trying to predict and render all of the pixels all the time. We're doing this sampling. So what you can see at the bottom is as we're moving this camera around, we're choosing a certain subset of those frames as keyframes. And then at each point in time, we're choosing one of those keyframes. I'm just going to pause this for a second. So we'll choose one or a set of those keyframes, and then a set of points within those keyframes to actually try and train our model. So what our model of the scene is just an MLP network. It's actually a really small MLP, only about a megabyte of weights. And it is in this kind of coordinate style like NeRF. So this is an MLP where you feed in a coordinate X, Y, Z, and it will output the estimated color of that point in space, and also the occupancy of the density of that point in space. So to train this network, we render views from it, from lots of from the positions from which we've got captured our keyframes. So we render a set of points here. So these are the RGB and depth frames we've captured at a particular keyframe. This is what our network is currently rendering from that position. And then at each of these points, we calculate the difference between the actual captured values and what we're currently rendering. And then, of course, propagate that loss back through to update the network such that if this is all working perfectly, this should look exactly like this, and this should look exactly like this. But we showed that you could really do that incrementally. So you start with just one frame, you start training the network, then you gradually add more frames, you continuously train, and this model just gradually converges to something that looks like convincing 3D geometry. So let's keep this running a little bit longer. So this has been running in real time for, I think, 3 or 4 minutes, while we're actually moving the camera around. We're still adding extra frames. You'll see that the camera kind of might go over to look more closely at this part of the scene, which is like a table with some objects on it. We capture some more detailed views of that part of the scene, and therefore we get more accurate scene reconstruction of the objects on the table. And then we're also, doing camera tracking to camera pose estimation within the same framework here. So that's not a separate thing. That's also done within the same optimization. So I think we're close to the kind of end of the real-time run here. So let me just skip forward here, and we can see the kind of some different projections of the 3D scene that we have reconstructed. So yeah, I mean, in this question of, is this a good representation of 3D scenes that's useful for robotics? So in my mind, we were very much comparing this with, for instance, what we might have done with Elastic Fusion or Kinect Fusion. So some of the properties you'll notice is this is not at the moment a super accurate reconstruction. It looks fairly sort of low resolution. And that's mostly because we've used a small MLP, and we were kind of forced to do that by wanting to train this, fast and in real time. But on the other hand, it has some really nice properties. So it's very kind of smooth and continuous and kind of coherent. And in fact, those were some of the properties that we found really, really interesting. So I'm just going to skip this back a little bit and play it. So one of the things you'll notice is the whole thing seems to sort of vibrate. And that's because we're continuously training this, there's stochastic gradient descent going on through the weights here, and everything is changing a little bit. But some of the aspects of that reveal that there's this sort of automatic compression going on. So for instance, look at this orange thing here is a football that's on the floor, and you can see that its shape is kind of, oscillating. But interestingly, it's not like, random noise on the surface of that thing. It's like the whole shape of the football, gets bigger or smaller in kind of quite coherent ways. So in my mind, what that really reveals is that within this megabyte of weights that are representing this scene, there's probably a pretty small number of those weights that are associated with the shape of that football. So somehow the network has found a way to apply these weights that it has in an efficient way to represent this scene. So what that really means is there's a lot of kind of coherence. So the nearby elements of this object here are reconstructed, by the same small set of weights within the network. That's a sort of automatic kind of decomposition and compression that has happened of the scene. So that's very different, for instance, from something like a point cloud or a mesh. It doesn't have any of those properties. So in terms of how this might be useful for robotics, those were the sort of properties that we pursued. And in particular, when in the next step of this kind of work, we started trying to add semantics to these representations. So we had this paper called Semantic Nerf, which I think was the first paper sort of adding semantic properties into these MLP representations in a general way. But I'll show you this one, which is iLabel. So this is a real-time interactive, semantic MLP representation of a scene. So I'm going to show you exactly the same kind of scene that we just looked at here. It's a room scene. And we're running very much the same thing as we did in IMAP. So we're feeding in RGB and depth images, and we're trying to reconstruct the 3D occupancy and the color of the scene. but now we slightly modify our network to have some extra outputs. And these are just like, so 10 extra outputs from the network that we interpret as a kind of vector of indicators of what is the semantic class of any particular point in the scene. And what's really interesting is we don't really have to predefine what those mean. So initially, we've just got 10 semantic outputs here. And all that we're rendering in this view at the moment is which of those outputs fires highest at any particular point in the scene. And initially, that's just kind of nonsense. It just, will show some kind of messy color map here. But interestingly, this is already a somewhat coherent looking color map. So it's not just a random cloud of points. Again, because of this kind of coherence property, and because these outputs are being generated by the same small network that's generating, density and color, they kind of inherit those coherence properties. So they tend to latch themselves onto object-like things, even when you haven't given them any kind of extra information. But what we show here now is now what we can do is add a tiny amount of supervision to this. So this is a system that's never had any semantic pre-training at all, or it's never in fact seen any other data other than these live frames of this view. But what we're going to do is now apply a little bit of human labeling here. So we apply some clicks to the scene. So what we do here is we click these points here, and for each of the clicks that we make, we say, this click here, the green label should be highest. And here we just type in a word and give the green label the name ball. And then we add a few blue clicks here, and we define this shelves class. And then we add a few clicks here and call this the bed class. But what you can see is even though we've only added a very small number of clicks, these kind of labels spread into the coherent kind of object-like regions in the scene that have been discovered by this kind of automatic decomposition that has happened just by making an MLP fit this scene. So the result of keeping doing this is that we can label the semantics of this whole scene by making only, I think it's 140 clicks within the whole scene, and we can get really kind of accurate semantic labeling of the whole scene with this incredibly efficient human interaction. So that's very interesting, but you might think, okay, but you need a human in the loop here still to add these labels. So the kind of next thing that we did was think, well, what if a robot was actually kind of making its own clicks? So this paper that we presented at Coral at the end of last year is essentially the same system, but here we call it an autonomous robot experimenter. So we're running this iLabel network. So here's a robot arm. It's got a depth camera attached to it here. And as the arm moves around, we're going to capture some views of the scene. But now, instead of kind of a human clicking to add labels, the robot is going to go down and make some sparse interactions with the scene. So what it did there was it went down and kind of poked the scene. And what it's trying to do is to classify this scene into hard and soft. So whenever it pokes the scene, it can use a little bit of force feedback to determine whether the thing that it poked is hard or soft. So here it poked this kind of cushion here with a cat on it, and this is soft. So it added a soft label over here. And it's just going to keep doing that. So the places that it touches are guided by the entropy of the current label map that you can see visualized down in the bottom left here. So it's going to try and make touches where it's least able to predict the hardness or softness of the scene. And you'll see that each time it makes a touch, it gets another observation of either hard or soft. And then it keeps predicting this hardness or softness property for the whole scene. And you'll see that after very few touches, this converges to something really quite accurate. So we've now got this sort of segmentation of the scene into hard and soft things. So let me show you just one more slightly different version of that. So this is now what we have a different sort of interaction where the sensor that we're using is not touching, but we have just a small spectrometer sensor here. So this is just a sensor that shines some infrared light of different colors onto the scene, looks at the amount of reflection of the different colors, and then based on a simple classifier can determine whether it's most likely that the material that it touched is wool, cotton, synthetic, or the table. And so now you'll see that it starts making touches on the scene, and then on each touch here, it says, okay, that was wool, that was cotton, that was also cotton. So with no prior information, it now just knows that it's good to group the things that are coherent in the neural map together. So again, with very few interactions, we're now getting this quite high quality segmentation of the scene with no prior information at all. Okay, so this is a slightly kind of artificial example in a way, you know, it's a real robot, it's real objects, but it's a kind of simplified setup. But we think this is very promising to show that how you know, what we think the interesting property of these neural representations are that might be interesting to robotics, this natural kind of coherency, and you might not need super accurate geometry for the things that a robot would do with this scene. Okay, so that was if you didn't have any kind of prior information. So one of the latest things we've done on this line of neural field work is, what if you do have some pre-trained network? So this is, you know, similar to some things that, you know, several other groups have done. We've done it in a real-time system here, so very similar to iLabel. So this is saying I've got a neural field that instead of trying to render color from the scene, it's trying to render some general kind of feature maps. So instead of trying to train this against color images, we will take every image that comes from the camera and send it through some pre-trained network. So this could be, you know, the early feature maps of a CNN, or it could be something, you know, more sophisticated like Dino features or something. But essentially, it will turn every image into a feature maps. And then when you render from your neural field representation, you also try and render feature maps, and then you train your network so that it's rendering feature maps that match up with the features that you're actually measuring from your camera. So this, compared to the previous demos, definitely gives a more sort of, you know, a grouping of similar things in the scene, which just comes from the feature maps. And that is then in addition to this kind of natural coherence and grouping that comes from the neural field. So that in some ways gives a more powerful system, yeah, but it does require this pre-trained network. But on the other hand, we think that these sort of feature generating networks are very, very general and useful for all sorts of different tasks. So what I've shown you so far are systems that are trying to make representations of whole scenes. I think that the other kind of key approach in particular for you know, representing scenes in ways that are useful to robots are to directly decompose the representations of scenes at the level of objects. So to explicitly have object level representations. And this is something we've also worked on quite a lot. I think the key question here, if you're trying to make object representations of scenes, is how much prior information do you have? And I think that is a sliding scale from, you know, some objects you'll have really strong prior information. So this system, for instance, so we've had a couple of papers along this line. There's one called More Fusion, and the one I'll quickly show you a video from here is called Reorient Bot, published last year. So here we're assuming that we do have strong prior knowledge in the form of CAD models. So we know, you know, precise 3D models of the set of objects that we expect to see in this scene. So that doesn't mean this is an easy problem, because if we come up to a cluttered scene, this problem of accurately fitting the 3D models of those objects and essentially going from this real scene to this kind of digital twin that you can see on the right, that's still a tricky problem, because the objects might be, you know, occluded and lying on top of each other and that kind of thing. But if you can do that, it gives you you're in an incredibly powerful position for manipulation. So here the robot was tidying up that scene in a very kind of general way, dealing with these cluttered objects, even doing things like re-grasping them if it needed to be able to place them accurately. So if you really understand the 3D shape of objects well, you can do more than just pick them up and drop them. You can pick them up and place them very precisely in a scene, which is exactly what a robot that needs to tidy up scenes would have to do. This work is a slightly looser situation of prior knowledge. So this is called node slam. So what if you don't have precise CAD models for objects, but for each of a different class of object, you have a sort of flexible shape model. So in this system, for 4 different types of objects, so cans, bottles, mugs, and bowls, we've pre-trained a 3D shape model. So that means that at runtime, we can detect the classes of the objects, and then for each one, we bring in the appropriate shape model and we optimize a low-dimensional shape code that gives us the precise shape of an object. So again, we've got a robotics example here. So we want to, sorry, in the right place. So we want to tidy up these objects and put them away neatly into this box here. So the camera makes a couple of observations of the scene. We fit these object models. So in the top left, again, here you can see this kind of digital twin representation. And you'll see that, you know, we don't just estimate the rough positions of these objects, we estimate their position and shape and size really accurately. And that means that we can do precise manipulation with them. So here what we're doing is we're picking up the bowls one by one, and we're going to neatly, you know, stack them in the corner of this box. So the kind of grasping stuff here is just some off-the-shelf path planning. The grasping stuff is easy once you've solved the perception here. And these are objects that it's never seen these precise objects before, but it's seen a data set of mugs, you know, which are, you know, span the space of the general shape of mugs, for instance. Now, of course, still there will be objects that you don't know about in advance. So the most kind of recent work that we've done along this line, and in fact, this is going to be presented by my PhD student Xin Kong here at CVPR, is the idea that you might have no specific prior information about objects, but you're going to make a separate neural field model of each one. So what we do in this system called VMAP is we're using the same kind of method as IMAP, in that we're going to use a neural field to represent 3D shape, and we're going to run that in real time. But rather than having one single neural field to represent the whole scene, we're going to pre-segment the scene into objects, and we're going to have a separate neural field representation of each object. So here you can see that as the camera is exploring around the scene, we're gradually building up this database of objects, which we're incrementally reconstructing. So now each one of these objects has these nice kind of coherence and completion properties because it's modeled by a neural field. And you know, one of the cool things in this paper is to, you know, train all of those neural fields. So we might have, you know, 20 different objects represented at the same time. And we're training, therefore, 20 neural fields in parallel by this vectorized training method, so that they can all happen in real time. Okay, so just to kind of get towards the end of the talk, so we've talked a lot about spatial, you know, representation. Another kind of key interest of mine at the moment is how that relates to computation hardware, and this idea that, you know, CPUs and GPUs that are the things we use a lot at the moment are just the starting point of, I think, you know, a huge explosion and diversification of the type of processors that we're going to use for spatial AI in the future. And an example is something like the IPU from GraphCore. So this is a company in the UK, massively parallel chip, but with a really more general type of parallelism than a GPU. So one of the things I discuss in the future mapping paper is, in order to make spatial AI really, you know, efficient in the future, we need to really think about the graph structures in the algorithms that we're designing and in the data stores that they have, and as far as possible, try to map those down onto the computation hardware that we're going to be using, because the key to efficiency is to avoid moving data around. So if we can kind of really co-locate processing and storage on graph-like computing hardware, that will really be the way forward. And in my mind, what we're going to have to come back to, and what will still be crucial in all of this, is probabilistic inference. So that's what I've really learned over the years in SLAM, it's the only thing that really works. If you want to do things like long-term incremental mapping, loop closure, you want to continuously learn. So, some of the kind of things that are currently limitations in systems like IMAP, that we want to continually train this neural representation of a scene. But in order that we don't kind of forget about things that it knows about and has seen in the past, we have to keep kind of showing it old data. We have to have this kind of replay method of continual learning. And that's not really going to be scalable. So I really think we have to get to something much more probabilistic, where the representations we're using for 3D are intrinsically representing uncertainty. So what I'm really thinking about a lot at the moment is going back to, factor graphs and traditional graph-like representations of scenes and how to make those really general. So one last paper that I'll show you, which is also going to be presented in this conference at CVPR by Eric Dexheimer, and also he's going to be doing a live demo of this in the demo session, so definitely see that, is some of our latest work on probabilistic SLAM. And in particular, this uses a neural network, and so we're all very interested in how to use learning together with probabilistic information in SLAM. But what is the right thing to ask that neural network to do? So you can feed an RGB image into a network and tell it to predict depth. That works reasonably well. But how, if you've got depth predictions for many frames, how do you actually combine that into a 3D representation? How do you take account of the uncertainty in that depth? That's a difficult thing to do. So in this work, we do something a bit different. What we ask our neural network to do is to predict depth covariance. So this means for any subset of points in an image, what our network will tell us is how similar it thinks the depths of those points will be. So here's just a bit of visualization where we look at some different points in the scene, and the network will tell us. So here, for instance, this point on the floor here, the network is telling us via this heat map here how correlated it thinks the depth of this point should be to other depths of other points in the scene. So clearly this whole kind of floor region here is coherent with this point here. It should have similar depths, where it's not very likely to have similar depths to these other objects. So what we do in this paper is we build that into a full kind of monocular real-time dense SLAM system. So this is a kind of keyframe based dense SLAM system that uses multi-view optimization together with this per frame depth covariance prior to give us this kind of real-time 3D scene reconstruction, which is really good, for instance, at even picking out small detailed objects like cables and the legs and wheels of this chair. So definitely go and see Eric's paper and demo. So more generally, yeah, I'm interested in incremental graph-like estimation, and in future mapping too. And especially, I talk a lot about Gaussian belief propagation as a general probabilistic framework that I think has the right properties that we need. And if you're more interested in this, I would point you to this. It's called A Visual Introduction to Gaussian Belief Propagation. It's an online interactive article that talks a lot more about that. Okay, so I think my time's nearly up, so I'll just conclude. So spatial AI research is exciting. I think we're still going to be doing it for a long time yet. So one of the things I've focused on this talk is these kind of special properties of neural field representations of scenes that I think could be useful for robotics. Even if they're small MLPs, they don't necessarily give us really precise reconstruction, but they have these compression and coherence and completion properties that I think could be really interesting for robotics. And maybe we'll see a kind of forking between those sorts of small representations that might be good for robotics and manipulation versus, for instance, high resolution, NERF style photometric, photorealistic reconstructions. There are definitely good applications for those things, but I'm not sure you need that for robotics. And just to mention my affiliation, so I'm leading the academic lab, the Dyson Robotics Lab at Imperial College. So we collaborate with Dyson on scene understanding and manipulation. And I'm also co-founder of SlamCore, which is a London-based startup. Okay, thanks very much.
Right. Thank you, Jason, for the presentation. And do you have any questions inside? Can you just go to the mic so that everyone can hear you?
Hi, thank you for your talk. I'm quite curious, what device are you using for the IMAP and iLabel?
What device?
Yeah, like GPU for training or CPU.
So I mean, this was a couple of years ago now, but it was a fairly standard desktop GPU. The paper will certainly give details. I can't remember exactly which GPU it was, but yeah, a single GPU. Yeah, just a desktop style. Yeah, and then we're using an RGBD camera.
Any other questions? Okay, so actually, I have a question. So regarding the IMAP, iLabel. So when you the reason of using the simply implementation is kind of because it's coherence or continuity, and but like for like 3D representation, I can see that because like the input modality is directly implicit. I mean, it explicitly encodes the geometry, but for like semantics, for example, a flat surface with multiple, it can have like multiple semantics. So how can this like coherence property of this implicit neural representation be adapted to this interleaving like semantics, sometimes some like type of this kind of data? How is it possible to do that?
So of course the MLP is generating color as well as shape. So if there's coherence in the color of the scene, that's something which it should also take account of. But you're right that those properties might not be so strong on just truly planar scenes, for instance, with complicated patterns and so on. That's where I think probably this idea, like in the feature fusion work that I showed, you'll get those properties more strongly if you're sending your images through some prior network that's turning it into a feature representation, where I think that sort of kind of those will also give you good cues to segment the scene into different objects.
I see. Thank you. So do you have any other question? Oh yeah, what?
Thank you so much for the impressive talk. And as you mentioned, the visual rearrangement task actually motivate a lot of those advanced like scene representations, for example, the compositional properties like the completeness. So, but if we look back to the task, so from your view, do you think this visual rearrangement is really a must-have functionality like for robotics in the future?
Well, yes, definitely. So, in that paper, we discuss rearrangement as a really kind of general kind of catch-all problem that I think describes all sorts of, tidying tasks, maybe also things like construction tasks, for instance, taking a set of blocks and building a tower, you could think of as a rearrangement task. So I really think it's a very good kind of description of a wide, class of problems that I think are essential if we want robots to do useful things. So, my main kind of interest application-wise, working with Dyson is home robotics, and we're really trying to think of, what would be useful robots for the home. So, yeah, people I think would really value a robot that could tidy up a scene. So, for instance, you've finished dinner and the robot could come and take all those objects and tidy them away and put them where they're meant to be. So when I talk about rearrangement, it's that sort of task. It's taking a scene where which is a sort of object level scene, and taking the objects from starting positions to goal positions.
Okay, thank you so much for the for sharing. Thank you.
All right. I guess you have just one more question. Yeah, that's the last question.
Thank you, Andrew, for a very interesting presentation. My question is about BMAP. Maybe if you could explain a little bit. I'm interested in terms of the reconstruction of the individual object in the scene for different neural. You use different neural network for different objects. Do you look into the same object, glass, like for the same chair, but there are multiple instances in the scene, and you can create a more complete 3D reconstruction of the chair from different view of different chairs, and maybe some observation about how you pass the images of individual segmentation. Does the error from the segmentation affect the reconstruction geometry of the individual instances?
Yeah, I mean, that's a good point. I mean, that's something that we're not doing at the moment in that paper. So we really do build a separate reconstruction of each object, and there's no kind of sharing. So if there were multiple instances of the same type of object at the moment, those would be separately reconstructed. So yeah, of course, it makes a lot of sense that if you can identify that these are the same objects, you should use, you know, all of the data to contribute to both of the models and make a kind of unified model. But there I would say it becomes a little tricky with regard to, yeah, again, this whole question of how much prior information do you have. So I mean, if you had good prior knowledge of those objects to start with, I'm not sure that you would want to do this VMAP style thing of just bottom-up reconstruction. I would think you might want to do something more like, you know, the model fitting type of approach, and you would identify the relative pose of those objects and fit the same model to them with slightly different pose. But yeah, in general, this question of how to reconstruct an you know, pretty unknown objects, I think, is still a really open and difficult question. So thanks.
Thank you. All right. Thank you again for the presentation and the QA session. That's good. All right, our next speaker will be Angela Chang, and Angela is an assistant professor at SFU, and she worked on text 3D scene generation and yeah, and various data sets for 3D deep learning. And so actually, can you just join over the Zoom so that? Sure. Yeah, I think it's easier to like switch the setup. I think I sent in the first email this morning.
Oh, okay. I was
just saying, like, say it for you. No G. It's like, yeah, this one. So you can share your video, but mute yourself. Open your camera and mute yourself, and then share screen. I think it's okay.
So I just share my own screen.
Yeah, share your own screen. I think everyone can see the screen. Yeah.
Okay. Hi, everyone. Can you hear me? Okay. Okay, great. Just wanted to check. Thank you all for having me. And I'm very happy to be here. So maybe I'll start by saying a few words about myself. So I'm Angel. I'm from Simon Fraser University, which is actually located maybe roughly 30 minutes away from downtown. And my interest is in connecting language and 3D representations. And I'm interested in helping to build helpful AI assistants who can help you in the house. And because of this interest, I'm also very interested in having large-scale interactive environments. So here's just some pictures of what I think of robots that can help us around the house. Maybe you have a little robot that can help you vacuum the floor, or maybe serve you breakfast. And more recently, there's an effort so this is actually also a kind of rearrangement where we have the robot want to move one object from one position to another. So here we want to move the stuffed animal from the chair to the sofa. And yeah, and so here's just a little video of this stretch robot doing that. move my stuff. Okay, but how do we get to such intelligent home robots? I think this is something that will take a lot of people's efforts from different communities, robotics, vision, and I also think in language, because we want to also communicate with our robots using language. And I myself have done a lot of work in developing different frameworks and also benchmarks. So I will start with that. And what we want to do is we want to be able to make it easy for everyone to work in this area of robotics, not just a select few people who can have specialized skills. And in addition, we want to make it easy for not just roboticists to explore how to build these things, but different people who are maybe just vision researchers or NLP researchers who don't really want to necessarily deal with physical robots. And so there's this more general term, embodied AI, where I think of it being a little bit more inclusive, and we're perfectly potentially happy with just doing everything in simulation, but we're also happy with, showing that what the models that we trained in simulation works as well in the real world. But for all of this, what we start with is we want to have simulation frameworks that allow us to design the tasks and explore the problems that we want to explore, as well as having a set of data, 3D assets, different kind of episodes that we want to do, as well as from which we can then define very specific tasks like, oh, we want to set a table, put the plates on the table, put the silverware around it, or do we want to do a different task such as, move one object to another? And once we have all of this set up, then we can start to explore different approaches and compare them to see which one works better than other. So as I mentioned, I've worked, and this is also collaboration with a lot of other people because building simulation environments is not easy. So I've been privileged to collaborate with different people from UCSD, from Facebook and so forth to build different simulation environments. And here I just show some snippets from two, Sapien and Habitat 2.0, and I highly recommend both. And so Sapien, it consists of two parts. One part is the actual simulation framework that allows a robot to interact with different objects, as well as a data set, the part that mobility data set, which consists of over 2,000 objects that has been annotated with their movement. And this basically is a step forward toward having this interactive vision robotics research that has a very diverse set of articulated assets. And so here's an example of a robot working in Sapien that's able to move areas around and able to also, close and open drawers. And based on this framework, and also this is work actually from Hao Su's lab, UCSD. They've developed different challenges if you are interested in participating in the many-skill challenge, which is so tomorrow, there's this huge, big embodied AI workshop that it's a whole day thing. You're all welcome to participate or to join, and then you can, take a look at all the different kind of challenges that are presented there. But the manual skill challenge focuses more on manipulation and being able to interact with different kinds of objects and to move things around. On the other side, I've also helped to work on Habitat 2.0, where it's basically a fast simulator that allows for interaction. And in order to allow for this, again, you need to have the assets, the scenes that allows for manipulation. And so there's a set of replica cat, it's a set of interactive scene layout that allows for people to interact with, and as well as a way to procedurally generate clutter. So you can, if you wanted to pick up soda can, you want to have the soda can be placed in different things. And one of the highlights of this work is that it's just a very fast simulator. And in this initial work, again, we're focusing on rearrangement. In this initial work, we focus on rearrangement task where you can move objects from a specified initial position to target positions. But these are all specified via just their geometric coordinates. So here there's no language, but it does still require the robot to learn to chain different skills together. Like it has to move and navigate to somewhere, as well to be able to pick something up and then place it. And so here you can see it's going around, opening drawers and picking up this bowl and placing it away. Okay. And you can pick up different things. And with this, then once you have this setup and once you have this framework, then you can start to compare, what methods works well. Is it a monolithic RL agent, which you train end to end, or is it something that maybe you a more modular approach where there's a component that does some task planning, and then maybe for each skills. So for instance, I mentioned that you need to be able to navigate from one point to another. You need to be able to pick up object and place object, and maybe you train a skill for each set. And so you train a neural network for each skill. And so here, this, you don't need to pay too much attention to these graphs, but the main thing to say is that you can compare these approaches, and basically with monolithic RL, it often takes a lot of experience to train. And so far, in that plot, the robot that method is not as good as others. But that's not to say if you train further, it won't be as good. But overall, for these long horizon tasks where you have to do one thing and then another and then another, you can see if you just do one action, it can be maybe even close to 100%, but as you do more and more, the errors compound and it's gonna drop off. And so the idea of these different simulation frameworks and these environments is that it allows you to do these different kind of tasks and to be able to compare. But in order to support all of this, one thing is very, very important. And I think this is something that we as a community have been starting to recognize its importance and starting to build more and more, which is data sets. And by data set, what I mean is these 3D assets that allow you to do these different interactions. So I've, again, worked with a lot of different people on a lot of different data sets. And so the latest of which is this a set of data called Habitat Matterport 3D data set, or HM3D. And this is a fairly large scale set of data where we have you have near complete reconstructions, and it's fairly high quality. And it is one of the largest ever data set of 3D reconstructed indoor spaces. We have over 1,000 high resolution 3D reconstructions, and they come from all over the world. And with so these reconstructions are multi-room reconstructions. So you'll see here that they have a large span of floor area as well as potentially multiple floors, and they have a variety of rooms. And this is just showing a 3D turntable of houses. In this CVPR, this is through a lot of manual effort. Basically, workers have semantically annotated this data set so that if you wanted to know where the bed was or the kitchen, now the semantic labels, and this is 3D semantics. And for this, this statistics may be a little bit out of date, but at one point there was only 200 or so things annotated and 3,000 rooms or so. And this took just tons of human effort. Yeah. More recently, we've been working on a synthetic data set. And why do we want to go for synthetic data set instead of going for this realistic semantic like real world scans. The synthetic data set, what it allows for you to do is to have these different rearrangement of the rooms. And in addition, you'll notice that when we were looking at the scans, some of it, the scan quality may not be very good. It may be noisy, it may be very partial or incomplete. These synthetic data sets are very complete and high quality. And in addition, they allow for interaction. This particular one doesn't allow for interaction yet, but we do plan to have a support interaction as well. Interaction meaning that the cabinets can open and close. And this particular HSSD data set, we basically try to have it, it's connected from human designed scenes. And so the placement of object can match that of the real world, such as the HM3D SEM, much better than say something that's procedurally generated like Proxor. And in recent experiments, we actually can show that in a small quantity of these HSSD scenes, if you were to train your end-to-end RL agent that navigates to say a chair or a table, can work better when you take this pre-trained model on this small number of HSSD scenes and transfer that to say the HM3D data set, it can work much better than if you were to train with 1,000 Proxor or generated scenes. So there's value in having high quality data that match the real world. But okay, I'm gonna continue with more. I said that we want synthetic things because you can interact with them. While with scanned things, it's very hard. But can we actually take scanned things and create these interactive environments as well? So this is an effort that took a number of years, and it was presented at New RIPS last year, where we built this, we took scans of the real world, and we annotated not just the semantics, but the articulation parameters so that you can create this environment that can, with these cabinets and drawers that can open and close. You will notice that this is actually also incomplete. So the next step will be to complete the geometry so that you can actually put things in the drawers. And to do so, we actually took a space and we would take multiple scans, and we would basically have, obviously each space has multiple objects, which we will semantically annotate, but we annotate not just at the object level, but at the part level, so that you can actually annotate that this drawer is supposed to move in and out. And with the multiple scans, we will also correspond which door is which across the two scans. So you have this, basically you have the same environment in two articulation states that you can see. And in addition, we also provide an oriented bounding box for each object, as well as the articulation parameters for all the parts. So we do hope this data set can be very useful for the robotics community to investigate robots that can manipulate objects based on real world scans. Oops. In total, we've collected 108 environments, and these, again, if you count the number of objects, it's almost 10,000 objects with 4,000 or so parts. And here's just some more visualizations of the articulated objects moving in and out. And we can, and to do this, we basically created a pipeline for scanning and annotating. And I already told you about data set, and we also did some preliminary benchmarks for some tasks that could be of interest. Mainly, these are kind of, I would say, simple tasks such as object instance segmentation, part segmentation, part mobility. And we do plan to run a challenge in the future that will, and so if you're interested, look out for this. And so moving on to what else I think we need to get to intelligent home robots, it would be great if we can also have, so I've talked about having end-to-end RL methods, but I don't quite believe that's the way to go. So instead, I think it's important to have modular approaches. And whether there are subtasks that we can define and submodules that can be helpful as building blocks. So I've already kind of mentioned this, but I think one useful subtask would be to, take say a single view image or a multi-view image and be able to predict what the part and motion is. And this allows you to, if you are a robot, it allows you to maybe forecast how something could move when you open it, or if we're in the data creation regime, it will enable us to maybe potentially automatically create more of these interactive environments. And so some work that we did that was presented last year at ECCV, we would take a single view image and we would want to have as output for each part, what kind of part it is, as well as the motion parameters, such as the type of motion, is it a rotation, is it a translation, the axis, and then for rotation, you also want an origin. And we focused on basically just only 3 different part types, like drawers, doors, and lids. And these are things that you can open. So we called our task the openable part detection. And to do this, we basically leverage 2, this is image-based data set, which we call OPD Sense and OPD Real. And the OPD Sense is synthetic object that's based on the partlet mobilities, while the OPD Real is single object with articulations that we captured with the multi-scanning pipeline. And in order to do, we propose 2 simple baselines for this task, which is basically a detect and predict strategy. We detect what parts there are and predict the motions. And what we do is we leverage existing instance segmentation networks, and we just add prediction heads for the motion prediction. And we use 2 popular instance segmentation models. One is MaskRCNN, and we would just add, we would basically try to predict the pose of the object and then the motion parameters, the axis, the type, and origin in kind of a canonical object coordinates. And we would do the same thing based on using mask2former as well. Add the different heads. And here are just some visualizations of the predictions. We do fairly well, but with the mask2former based method, it's able to be a bit more accurate. So here, what the numbers are is kind of the error that you would get. The other thing I'm interested in is doing more modular approaches to embodied AI. So beyond saying defining like what some good tasks there could be, we are also interested in saying, what should the architecture of the agent be? And to do this, I basically investigate. We first set up this. We set up this multi-object navigation. So it's kind of like the single object navigation, but we do, instead of navigating to just one object, we navigate to a sequence of objects. And part of the reason for this is that if you think about this initial thing, that video I showed of a agent that's going around and taking the stuffed animal from one place to another, it basically needed to go to 3 different objects in order. And so we can think of this task as being basically the same task, but instead of you having to manipulate the object, you're just going to the different objects. And with this,
Seems like is that you're muted? Maybe you can unmute yourself.
Okay. Oh, sorry. Okay. Should I mute?
Yeah.
Very tricky.
I think this one has an issue.
Oh. Should I mute myself?
Yes. Yeah, I think maybe you should mute yourself and. I think there's some issue with this, the microphone, this kind of tricky. Say something.
Hello, just a little bit of echo. What if you just stop your speaker?
Actually, I already stopped. So actually, your voice comes through this one.
Okay. You can show me to it. Somebody said the previous setting works fine.
Okay. Yeah, then maybe let's just keep the previous. Because someone said in the room that like you are muted.
Oh, okay. It may be.
Okay, okay.
Okay, sorry for the interruption.
Okay, I think it's working now.
Okay.
Okay, okay, sure.
Okay, sorry for the interruption. I was talking about the semantic memory for embodied AI. So we initially proposed this multiple object navigation for two reasons. Again, one is that it's a simplified version of this, rearrangement where we, instead of having to pick up something and place it, all we needed to do is to go to the different objects in order. And here we actually, what you see here is actually a simplified version where we would actually not even go to real objects, but just inserted cylinders of different colors. And the other idea is that we wanted to propose, basically do systematic investigation of different map representations, because if you are just doing a single, navigating to a single object, maybe you don't need to remember anything else. You can just do it. While if you need to navigate to multiple objects, then ideally you would want to go back to, if you've already seen the object that you need to go to. Okay. Okay. So based on that, we also developed a kind of a more modular approach. And before I go to the modular approach, let's just have some visuals of what this going to multiple object means. So basically we have a little robot. We want to go to object one, and this is indicated by a one hot vector of like, this is the type of object you want to go to. And once it locates it, it's supposed to issue this found action. And then after that, it's told what object it needs to go to next. And so, and once it finds that, it says find, and then it goes on to this another object and so forth. And then you'll notice that here, there's also other cylinders that are not the yellow, the blue, and the white that it didn't need to go to. Those are kind of distractor objects where maybe it's good to keep track of them because it doesn't know exactly the colors it needs to go to, but it doesn't need to go to them in the end. Okay. And the action space that we looked at was basically being able to go forward by some amount, turn left, turn right, and then calling this found action. And like I said, we first proposed this in order to investigate memory and mapping. If we have a modular approach, then we can actually systematically explore the different modules. But let's first take a look at the memory and mapping. And so this initial work, we basically just was actually training end-to-end agents. And we wanted to see, okay, what happens if you have a map where you know everything, you know where things are. As you you as well as knowing what object is at each position. You can also do a RNN, which doesn't have this spatial map, but it will accumulate memory of what has happened, as well as maybe a map where it's slowly revealed over time, but once you see something, you get the oracle information. And in contrast, you can also have this map where it's still GUID-based, but instead of storing the semantic label, you would project features into each GUID. Or you can also use those features potentially to be able to predict what object was at that location. So if we look at these different methods, so this is, I think, going for 3 different, going to 3 different objects. And you can see as you train more, with more training experience, all these methods improve, but it definitely helps to have a map. Of course, if you have the ground truth information, it's the best one if you need to predict what kind of things is there, it's less accurate. But I think what's more interesting is to see what happens after you find the first object. If you want to go to the second object, does it remember where it has gone, where it has seen the object and can accurately go back to it? And so for this, we kind of separate the case into 2. One is that the object was previously seen versus one it was not. And you can see if you had oracle information, it didn't really matter if it was seen or not. Like if you had oracle information of the whole map, complete map, doesn't matter if it was seen or not, it would be able to, there's only a small improvement for things that has been seen before. But for these maps where you're learning and you're slowly, progressively revealed, then being able to build this map is very helpful, especially compared to something that just accumulates information in a non-spatial way. Okay. I think I have 5 minutes. I'll quickly go over this our modular approach. Our modular approach is that we're given the goal and the RGB and depth, and then we have a object detector that will tell me if the object is there, and then we slowly again accumulate information to our map, and we'll put information on, build it up with. And then in addition, there's a component that decides, okay, do I need to explore or not? And if I explore, where should I go? And then this I call the planning component, but this is really basic. This is basic. If I have the object in my map, then I go to it. If not, then I pick whatever the exploration policy told me. And finally, we have this other module that will say, what action to take. And as I already mentioned, we can, if we have this modular approach, we can systematically study each component. And in general, it's good to be able to pre-train the different modules. And it's even better if our system can be tuned end to end. So I think the using of pre-trained models is not anything new. It's very commonly done for the object detection part. And what's slightly less common is potentially, using a pre-trained module for the navigation, but you could very easily put a pre-trained point nav agent in there, because what we're trying to do here in navigation is we're just saying, here we are, and this is the relative place we want to move to, and that really fits the point nav. And what we show is that you can do potentially much better. This is with the Oracle semantic map, with the point nav model, partly because it's much faster and it doesn't get stuck. Okay. And we have a challenge. So we are part of the CVPR Tomorrow's Embodied AI workshop. You should all come. Unfortunately, nobody participated in our challenge this time. Our focus is on small objects, so we place little objects on different things, but we'll keep our leaderboard open. So if you're interested in participating, please participate. And also the key is that if you participate and there's not that many people you can, and if you get to be number one, you can present at the workshop, you know. So there's some, it's better to participate in the less popular ones. So I don't know how many minutes I have, but I'll say that I want to advocate to the use of language for task specification. So large language models are very popular now. They can be a source of knowledge, and you can use these models to with language specification for perception, planning, and control. And people are doing this. I actually haven't done very much work in this, but other people are doing it. Perception, you can do like open vocabulary perception. Planning, you can maybe ask ChatGPT to help you break complex tasks down into subtasks. And control, you can actually generate programs that can control robots via API. Again, this is not my work, but this is just examples of people using language models for open vocabulary detection. And here's an example of me querying ChatGPT about how to set a table for 4. And maybe it's a little bit hard to understand what ChatGPT told me, but it seemed to know a lot. It says that robots need to gather all the materials first, that plates, utensils, glasses, and napkins. And then it says, you know, you would place them around the table and so forth. So there's a lot of knowledge there. And I think this could be a very exciting direction. Again, not my work, but you can use these models for planning. You can, you know, if you want to do, you know, different, how do you brush teeth? How do you throw away paper? It'll give you step-by-step instructions. And yeah, and then this paper, do as I can, not as I say. I think it's fairly, I feel it's fairly famous, but maybe you guys haven't heard of it. I don't know, but it's from Google. It's basically saying how you can use language to basically figure out what's possible. It can give you a list of potential suggestions, and then you can use perception to say, okay, which of these actions can I actually do? And you can select from them. Okay, I'm pretty much at the end. So I opened this talk with a video of some robot going about and picking up a little stuffed animal. And this is part of the Home Robot Open Vocabulary Mobile Manipulation Challenge at NeurIPS 2023. And for this, we basically use the HSSD things that I introduced, as well as object from a variety of different data sets. And the idea here is that what you want to do is you want to find some object and some start receptacle that's specified, and then you want to place it on some goal receptacle. And there's different variants where maybe the goal receptacle is not specified, so forth. And here's just a baseline, but this is a NeurIPS 2023 challenge. So you're all encouraged to participate and try out your nice method. And that's it for me. Yeah. Okay, repeat and say language as well. Okay. Thank you.
Do you have any questions? Actually, I can ask the first question. So actually, like one general question regarding like all this like data set, synthetic data set, or like scan data set. What do you think is like the biggest difficulty that hinders from like model learned in this data set to apply them to the real world application? What do you think is the biggest gap, like the reality or the reality gap, or the like the scale, or all this stuff? Which one do you think is like the most difficult?
I guess I think it depends on exactly what you're doing. So I do think that each role, so maybe that question is kind of, I feel very general in the sense that there's, you know, if I have a robot that's trained in synthetic data, then it may not work in the real world because maybe it's just noise. So one thing I will say is that some of what I've shown is that, you know, noise-free environment. So in the real world, there's always noise, right? So that's one of the biggest gap. While in the synthetic world, you can simulate noise, but do you simulate, how exact do you need to simulate the noise? And what part of the noise is important? Do you simulate all the noise? That's one thing. And then there is also, depending on the modality you use, the the sim to real gap can be either less or more. For instance, if you are in the synthetic world, if you use point clouds or depths, then there's less sim to real gap than if you were to use color. But maybe if you were to able to randomize enough in the synthetic world, then you would be able to cover such a broad space that even so reality you didn't quite match, it's just a small subset. So maybe you're okay. Yeah, but you can go on and on here.
I have a question about the language model, using the language model to elaborate the sub-plans. So these language models are based on some common senses.
Yes.
But in some environment, this robot needs to interact with the environment in certain kinds, right? In
Yes.
that case, how can we deal with the situation that this common sense is not applied to this particular environment?
So maybe a couple of thoughts. One is that I think language models, you're right, it's just common sense, but I think we're just at the point where this is just starting to be able to happen. So it's very exciting. So you do it.
Right.
But for a specific environment, I think you still need to have perception in the sense that you can't just rely on common sense. You need to actually see what's actually going on. And that's where maybe perception is going, where you would use your perception to say, okay, usually, for instance, a mouse, usually most people are right-handed, so maybe the mouse is on the right hand of the thing, and you would use the right hand. That's where you would look for the mouse. But some people are left-handed, right? And maybe the mouse fell over, and you have to find it. And then so you need to use like the perception to actually figure out what's actually the state of the world. And in my mind, the language model maybe can help you, but maybe it's better if you can actually build a representation. I like structured representations. I actually like Andy's talk about maybe you have like graphs.
I guess my better question is whether we need to fine tune this large language models, or whether we need to get this basic common sense and combining with this perception and just generate something else with some other models or something. So I'm not very sure whether we have to fine tune it or we need to introduce new model to combine it with fusion. We don't know, right?
I can speculate a lot, but what I will say is that maybe this is why it's so exciting. You can go explore. And I suspect that you have to do fine tuning. You will have to do new modules. You will have to error correct. You will have to do everything. And that's why this is just a lot of opportunities here.
Sure. Thank you.
Hi, Angel.
Hello.
That was a really delightful talk. Towards the end, you advocated, or I guess kind of throughout the talk, you advocated for using language as a way of sort of like specifying the tasks and kind of providing a natural input to these embodied agents. Where do you think we're at for in terms of the embodied agents communicating back to us in natural language and kind of improving the legibility of what they're doing through language? Are we ready for that? Is that
we are? So I will maybe have two parts. One is that I think they are, because it's if you use ChatGPT, it's actually amazing what it can do, right? So I think maybe we are at the stage where we can actually have these things try to tell us what it's doing and why is it doing it. It probably won't make sense at this point, but I think that would make sense. That it will make sense as the next step to try. But I also, even so, I advocate for the use of language as an important like avenue to pursue and an important component. I do not actually believe that it should be the only one, in the sense that, maybe I want to say, put the dishes there, and I want to gesture there, and I want to be able to point, And similarly, if we talk about how the models communicating back to us, I think language is great. It should say, okay, yes, for one thing, if you told it to put the dishes there, maybe it would be good if it said, yes, I will do it, versus, maybe it's grinding away, but but you don't know really what it'll do. So it'll be very helpful to, if we can say, yes, I will put the dishes on the table, or it could also just point as well to say, yes, I will go put the dishes there. So it can combine. And also a robot, you can have other like visual outputs or whatever to show. It can show you the map it learned. It can show you on the map what it's gonna do. So there's other ways to augment its communications.
Great, thank you.
Hi, hello.
Hello.
Nice talk. I'm really fond of your work since minus and all of the data sets that you are presented and the simulators. Just I want to know from your perspective point of view, what are your opinion with respect to implicit representation for cities? From one side, we have this scan environments where it's coming from the RGBD sensor and we are aggregating the data. From the other side, we have the synthetic environments where we can have some manipulator or have some options. But we, as you mentioned, we lack of noise and the explicit reality. But we have also now this new version of a scene representation, this implicit representation. I could like to hear from you, your point of view about implicit representation for the same task of planning, control, and learning from there.
I guess here, I feel I'm not very qualified to answer the question very well. First of all, implicit, exactly what does that mean? It means different things, I feel, to different people, in the sense that, you know, maybe what it means is that you have a network that's predicting the, you know, sign distance function, let's call it, or you have a network that's predicting something, or maybe you have a latent representation. It's implicit, it's not, you know, explicit map representation, let's say. So I feel it's hard to, depending on exactly what you mean by implicit, the answer could be a bit different. But what I would say is, in general, you know, whatever representation is useful for the robot or the agent is good. You know, if from practice implicit representations work well, that's great. But at some point, we need to be able to understand what the robot is doing. We need to communicate with it. And that's where I think the more explicit representations are very helpful, where, for instance, you know, you have something that maybe it doesn't really have a map, but if you can have this explicit representation for map that it generates for me to look at, that I know I can understand what's going on there, versus whatever implicit things it's in the latent vectors. I'm now using implicit to mean, you know, say latent vectors versus explicit maps. I don't know what's going on there. So yeah.
Oh, thank you.
Okay.
That's it. Okay. Thank you again for your great talk. And everyone, please join tomorrow's embodied workshop and the challenge happening nearest 2023. I forgot what the title is.
But there's many challenges. So
thank you again.
Thank you for having me.
Okay, so our next session is a spotlight talk, again, afternoon session. And so, one moment. Where is my cursor? Is Pamela here? One moment. Let me put your video on that side on the screen. Okay. Still one thing to do. Last time I forgot. I think when you're ready, just click the space.
Okay. So, hello together. My name is Patrick Palmer. I'm a PhD student at the TU Dortmund University at the Institute of Control Theory and System Engineering. And today I want to present our work on reviewing 3D object detectors in the context of high resolution radar sensors. Oh, didn't start the video. Okay. Okay. Yeah, so what are imaging radar sensors? These are a new type of radar sensor technology that have a higher point density than previous radar sensors. And we want to solve the problem of doing object detection using these radar sensors. And they use a similar representation of points like an LiDAR sensor. And so we want to investigate how current approaches for doing object detection on LiDAR sensors can be transformed to these radar sensors and which of them performs the best. So we implemented or changed a lot of different object detection architectures from the LiDAR domain to the radar domain, and investigated how they perform on one specific data set that includes this imaging radar sensor, the view of Delft data set, and compared them. And what you can see from our results is that currently we don't have any clear best performing model. It looks like the PV-RCNN approach performs relatively well. Also other approaches like the voxelnet or point pillars in blue perform relatively well on radar data. And we also only have one outlying architecture, this point, which stands for point RCNN, which gives us the conclusion that point-based architectures may not be suited well to radar data. Okay, now we also compared them visually and identified a few limitations of the detection on radar data, especially the time continuous detection. So it is not possible for our architecture on radar data to detect objects well over the time horizon. So they have a lot of like holes in the detection where they get detected not in all time steps, but have missing detections. Also, the class of detection might not always be really clear, so there might be certain limitations there. Compared to LiDAR data, we have the you can see that we get a relatively good detection, but still can't reach the performance of the LiDAR data. Yeah, thank you for your attention, and I hope to see you at our poster.
We'll have the question at the group QA session. All right, our next speaker is William here. Yeah. Yeah, we're ready. Just click this.
I'm sure. Can I move that out of the way? That reporting.
So
I move that play bar down to the side.
Yeah, you can just click now. Yeah, you can do that. Great.
Hey, great. So hi everyone. My name is William. Oops. Yep, and I'll be talking about our project. The stilled feature fields enable open-ended few shot manipulation. So imagine we've given a robot a few examples of how to grasp objects. Now, how can we enable robots to generalize in new scenes with objects of different shapes, appearances, and perhaps categories? So we've seen 2D foundation models trained on internet scale datasets embed a lot of common sense knowledge and generalization about the world. However, these models such as CLIP inherently lie on a 2D plane, whereas for a lot of robotic manipulation tasks, we want to understand 3D geometry. So we know one way from going from 2D to 3D is by using NeRFs. So given a lot of RGB images of a scene, we can reconstruct the scene in 3D. However, what's still missing is the feature fields. So we also want very rich semantic features over the entire scene. So how can we get that? So the approach we're using is called distilled feature fields. And basically we take the RGB images taken by the robot, we extract dense features for those, and then project them onto the geometry learned by the NeRF. And as a result, you get this very high resolution feature field. And what you see on the right is the PCA visualization of the feature field. So we now have this, and how can we actually make it useful for robots? So we're going to be learning how to grasp from a few demonstrations. So for example, if we grasp this mug, what we can do is we can sample a bunch of features around the query points. So we query the feature field for each of these points, and then concatenate it into a single vector, which represents the grasp pose. And in a new scene, we can then optimize to find the pose that best matches this. So let's go back to our initial scene where we set up a whole bunch of objects. We have clip feature fields, which are vision language models. How can we use language to guide manipulation? And this is using only 10 demonstrations across 4 object categories. So first of all, we get a robot to scan the scene, we train enough and distill the features. And then after that, we can use language to designate what objects we want to grasp. So in this case, we have Baymax. We can compute the similarity of Baymax over the entire feature field, then optimize and predict the grasp and get the robot to execute it. And just note the robot has never seen Baymax in the past. The closest thing it's seen is a caterpillar plush toy. So language also allows us to specify objects by color. So in this scene, there's a blue screwdriver and a red screwdriver. But by using language, we can specify which type of object we want to manipulate. We can also generalize to out of distribution object categories. So in our demonstrations, there's nothing about bowls, but we know how to grasp mugs by their lips, but we can generalize that information to this new category. So this is the red screwdriver, showing we can grasp both the blue one and the red one. And finally, we have materials, so transparent jugs. So you can see there's a transparent jug and a metal jug, but we're successfully able to get the transparent one. Yep, so thanks for listening and hope to see you at the poster session.
Thank you. And our next presenter, Hongyu, is Hongyu here? I just do a full screen. Yeah, so I think it's our start.
Oh, okay. Hello, everyone. My name is Hongyu. I'm glad to present our work, Stereo NavNet, learning to navigate using stereo camera with auxiliary occupancy voxels. This work was advised by Huaizu Jiang and Tashkin Badir at Northeastern University. So for visual navigation works, there are 4 models. Like typically we give a visual input and it is processed by training from scratch or pre-trained feature extractor models to generate a feature, visual feature, and the visual feature generates some sort of actions and feed into robot. So it could be characterized as a visual input to occupancy features. However, there are 2 limitations. One is it lacks geometry awareness and it's hard to generalize to different domains, like from simulation to the real world. Therefore, we revisit the traditional approaches like the dynamic window approaches and A*. So basically, they only leverage the geometry feature of the environment and they have no domain gaps. So basically, it's the same in simulation, also the real world. Therefore, we propose to use auxiliary occupancy grid as the intermediate layer. From the vision, we have the occupancy grid and extract the geometry feature from the occupancy grid and use that occupancy feature with geometry to extract the action for robotics. However, if you look at this occupancy grid, it is 60 by 60, 64 by 64 by 64. It is still too large. So how can we make this better? Because we have to use 3D CNN to process it to extract the feature. So in our prior work, we showed that the curvature sampling is an efficient and robust state compression strategy for learning-based navigation planner. So the curvature sampling is based on the mobile robot's kinematic model. And we combine the best of 2 paradigms. So we leverage learning-based method to process the visual input, and we leverage geometric feature to provide geometry awareness and robust to domain shift. This is our pipeline. So in the green box, which is the perception module, we extract voxel occupancy grid using stereo voxelnet, which was my ICRA 2023 work from stereo images. We combine it with curvature sampling. We extract occupancy features, which is low dimensional. Here's a proof of concept experiment I did in a gazebo simulator. So we collect expert demonstration. They toyed as it in a environment and perform evaluation on 2 novel scenes. And we have more experiments, more comprehensive experiments in both simulation and real world. Thank you very much.
Thank you for the presentation and the last presentation in our group. Yeah, all right. Ready to.
Okay, hi, hello everyone. I'm Haorang Dong from Peking University. I'm a junior student in Peking University, and I will present our recent work. Oh, sorry. I will present our recent work. Learning part, we are visual actionable affordance for 3D articulated object manipulation. Parts are fundamental building blocks in our daily objects. We human can identify a set of commonly used parts such as buttons and handles. Even on normal object, we have no problem with recognize the parts, and we know how to interact with them. We thought argue that some part classes are more elementary and fundamental than object categories, and thus worthy of more research efforts. And to this end, our previous work, GapRNet, we conduct a large-scale part-centric interactive dataset GapRNet with rich part-level annotations for build computer vision and interaction tasks. It has 9 commonly used parts classes and provides rich semantic label and post annotations. And given the part and the post definition, GapRNet then investigate cross-category tasks, part segmentation, part post estimation, and part-based object manipulation. We need to train unseen object category and then need to generalize to unseen object categories. And here we also propose to utilize affordance as an intermediate representation between perception and interaction. And here we can see the affordance map is how likely the pixel or points P is actionable. And we know that only the parts are actionable, and the same part class have similar affordance. And the difference come from different local geometry. We thus propose to first learn a part-aware affordance map. We first predict a prior with part prediction results, and we then add the residual affordance to get the final results. Oh, sorry. We also propose to use part level affordance to select the best part for manipulation. For example, here we have drawers and handles, and we select handle. And this is the overview of our pipeline. Our method shows that our experiments show that our method outperforms previous method. And here are some quantitative results. Thank you. And you can scan the QR code for more information.
All right. Next is our group QR section. Do you have any question regarding the all the previous 4 presentations? If you have, you can yeah. Also, the authors can go to the front, maybe sit in the first row, or just come to the front. Yeah. So yeah. I have one question regarding the distilled feature fields. So for demonstration, how many demonstrations do you use for training?
So in our experiments, we had just few shot manipulation without language at all. We only used 2 demonstrations of the objects there. And for the language ones, we're using 10 demonstrations across 5 tasks, but generalizing to different
When
kinds
you
of
say different tasks, it's different objects, or
different object categories. So grasping a mug by the lip. So the 5 of them were grasping a mug by lip by its lip or its handle, caterpillar, toy by its ear, screwdrivers, and putting a cup onto a rack.
I see. Yeah. I see. So only 10. That's pretty.
Yeah, only 10. But I guess the demonstrations encoded a lot about general grasping strategies.
I see.
And the features allow us to generalize that.
So the demonstration is continuous grasping motion, or just open loop grasp pose?
Right. So we're only doing a single grasp pose.
I see.
Then using a motion planner to get there.
That makes sense. All right, thank you. There's online questions. It seems yeah, actually I just have one more I'll go to that. Oh, yeah, sure. Yeah.
The grasping is very interesting. I'm interested in the problem that you deal with the transparent object. So you have a cup there, but the one that you have a bit, I think it's made up out of bit white. Is some scattering material. Have you tried something like a glass with more transparency and reflection?
Right, so we did try, I think at one point, a glass filled with like orange juice. So it did successfully do that in that case. And I guess also more transparent jugs as well. So I think the nerf allows us to reconstruct those sorts of objects pretty successfully.
Regarding the benchmarking, the object detection. So I see you're like comparing like LiDAR with radar, and like radar was giving very like bad performance. So is it because of the data modality? Is it sparse point cloud or something like that?
Yeah, it's a really sparse point cloud. So in comparison, like in this data set, the LiDAR sensor had around like 120,000 reflection points per scene. And the radar sensor was more in the field of 500 to 1,000 points. So, and even these points that we get from the radar sensors are really noisy. So it's a much harder problem to predict objects from there than from the LiDAR sensor.
So are the radar points more like, is it like uniformly distributed or like scattered around like certain objects? Or
they are scattered around certain objects. For example, for a car, you have certain regions that reflect radar beams really good, like the wheel well. You get a lot of reflection points from there, or from other scenes than from like corners or something. Like you can see like street corners where the pedestrian path is raised above the street. You can see these points really good in the radar sensor, but so they're not distributed uniformly.
I see. Thank you. Okay, so let's go to the second group of like spotlight presentations, which are all like over the Zoom remotely. So I'll just play the video. So since they're remote. What? Okay. Wait, is there sound? It seems there's no sound here. How are you online? Maybe we can just first skip to the second. Never mind. Hey, this one is.
Hi, I'm Yixuan Wang, and I'm glad to present our work, Dynamic Resolution Model Learning for Object Pile Manipulation. We human reason the environment using a dynamic representation. For example, when we grasp the box on the cabinet, we first represent the box as a holistic object and approach it. When we are close enough, we use a more refined representation like pose and geometry to finish grasping task. Object pile manipulation task is very challenging due to its high degree of freedom. We choose this task as the test bed to show how to choose the dynamic representation that is both effective and efficient. We represent the object pile as particles because particles are very general and flexible and can model the interaction between object pieces naturally. Images here show an example of representing different objects using particles. We use particles subsampled from the RGBD observation to represent the object pile. For robot workspace shown here, if we represent the scene using too few particles, it might not contain enough information to generate effective robot action. If we use too many particles, there might be redundant information that makes the system inefficient. Therefore, a good representation needs to contain the minimum information that is sufficient for downstream robot tasks. Given the current state and the target, we use Bayesian optimization to find the most effective abstraction level that can maximize the task reward. I will show our robotic framework here. Given initial observation and target location, the resolution regressor predicts the optimal resolution. Then, the resolution and current observation are input to the perception module to produce the representation. The dynamics model takes in the current representation, action, and resolution to predict the representation. The predicted representation will be compared against the goal to compute the reward. The trajectory optimization will find the optimal action that can maximize the reward. We conducted experiments using objects shown in the left image and the setup shown in the right image. We show that our framework could accomplish tasks like pushing the object pile into all letters. This is very challenging considering complex shapes of letters like G. Due to time limits, we do not show all results here. We also conducted experiments like pushing the object pile to Go region, pushing the pile to Chinese and Japanese characters, and sorting object piles. Please check out our paper and website for full results and method details. Thank you for listening.
And our next remote presenters.
Welcome. We present our work on reassembling broken objects using breaking curves. To introduce the topic, here's an overview of the related work and the state of the art. Early works use geometric methods to detect broken surfaces to support the assembly. Last year, solutions using learning-based methods have emerged, thanks to the release of the Breaking Bad dataset, which contains hundreds of thousands of meshes of realistically broken objects. However, learning the assembly is a challenging task. Latest methods have constrained application and still show margin for improvements in terms of accuracy. We developed an algorithm that takes inspiration from the literature and does not account for a specific shape, aiming at reassembling both real and synthetic broken objects. Currently, we assemble only 2 broken parts, but we assemble also incomplete objects, and our approach is ready to be extended to the multiple part case. The pipeline receives as input 2 point clouds. This is divided into 3 main steps: extraction of breaking curves, segmentation of region following the curves, registration of segmented region, and reassembly. Breaking curves characterize object fracture. To extract them, we represent a point cloud as an epsilon graph. Then, for each vertex, we assess its corner penalty value, which account for the ratio between the first and third eigenvalue of its neighborhood. The flatter the area, the closer to 1 the value will be. We keep only such vertices having a corner penalty smaller than a certain threshold, fixed for all our experiments. Further, a sequence of pruning and dilation operations are applied to remove isolated branches and promote the creation of closed breaking curves. Once the breaking curves are extracted, we found the region enclosed by the curves. To do so, we use a constrained region growing technique resulting in a set of several regions. The registration between 2 fragments started by their regions. The 2 small ones are discarded. Then we perform ICP alignment over all pairs of regions in 2 sets, and compute the chamfer distance as a matching score. We pick the 2 regions with the highest score and consider their alignment parameters as the one for the entire fragments.
These are the qualitative results obtained on 2 real 3D scanned datasets that are brick dataset and fresco fragments from the repair project, and on the synthetic breaking bed dataset. As it can be seen, our method correctly assembles broken parts of real and synthetic objects. We compared our method with the DGL, which was reported as a superior method on the breaking bed dataset, and ICP as a baseline. Our method significantly outperforms DGL and ICP in all datasets in terms of relative rotation error, and in the majority of datasets in terms of translation error. So, in conclusion, our method is able to estimate the correct rotation and translation to assemble pairs of fragments across different datasets. At the moment, extending the reassembly task to multiple broken parts is under exploration. Also, we are on enhancing breaking curve extraction methodology to make it more parameter-free. You can access the project page using the given QR code here. Thank you very much for your attention.
So for our last presentation, Hannes, you're online. You're online. Hello? Hello. Okay, good. We can start presenting. You can start now. Am I talking? Yeah. I think I did. I think he's not muted, but just can't hear him. Somehow we just cannot hear you. So. I guess it was like severely over time. Maybe we can just go through the Q&A session, or should we wait a bit? We're supposed to end at like 2:50. Yeah. So do you have any question regarding the previous two presentations, the reassembling and the object type manipulation? Okay, so I have one question regarding the reassembly. Is Arthur online right now? Okay, it seems.
Yes, we are here if you need something.
I just want to ask a question regarding like you're using chamfer distance to match the like broken region. So when you're saying broken region, it's like a surface, a point cloud of surface, or it's like a point cloud of the rim, or like a 2D point cloud in like 3D.
I'm not sure that I get your point. Excuse me, because you say that it's a point cloud in 2D or in 3D. So
So you're saying like you're using the chamfer distance to actually you're matching the broken region. When you say broken region and you use like chamfer distance to match these broken regions. And is this broken region like a surface, or is just like the rim of the broken part?
it's a surface actually that we are matching.
I see. So it's like a complete surface. Okay. Thank you. All right.
I think make any assumption it could be a surface or the rim or something else. We just divide the regions and then we test all the possible regions and we select the best candidate. It could be 2D or 3D. We don't have that.
Okay, then it makes sense. Thank you.
You're welcome.
Okay. I guess no more questions, and I can't hear him. He's not replying. Maybe we can just like continue to our poster session and we'll come back for the So this is like here we enter the coffee break and also the poster session. You guys can go to visit our posters at the poster number 192 to number 201 at West Exhibition Hall, and we'll be back at 3:20 p.m. today with Xiaolong's remote talk. Right. Are you online? Hi, Xiaolong, are you online?
Hi.
Great. Yeah,
Yes.
we're still waiting for like more people to come back to the room. So maybe you can
Sure,
please
sure.
test the screen sharing
Okay.
and audio. I think the audio and video is fine. Just want to test your screen sharing.
Let me try. Okay, should work.
Yeah, it's working pretty fine. Yeah, so yeah, let's just wait like 1 or 2 minutes for like more people to come back into
All right.
the
Sounds good.
Okay, I think it's about time. So yeah, so our next speaker will be Xiaolong Wang. Xiaolong is the assistant professor at UC San Diego in the ECE department. His research focus is on learning 3D and dynamics representations through videos and physical robot interactions data. And Xiaolong, you can continue.
Right. Okay. Thank you. Thank you for the introduction. All right. Okay. I think the screen share should be working.
Yeah, it's working.
All right. So thank you for coming to the talk. I wish I could have get here in person, but just due to visa restrictions, I couldn't make it. But in any case, today I want to talk about the dexterous manipulation work in our lab. So it is connected to 3D a lot. So we have worked on this topic maybe for like 3 years now. So there are basically a long story on how we developed and how we come across challenges in this direction of work. So essentially, I will talk about all these things in the beginning as well. So we are going to solve this problem mainly using robot learning. The idea is of using robot learning for this kind of work is really, we try to leverage a lot of data. Wait 1 second. Somehow my sharing is not working. Just like, okay, should work now. So yeah, so the learning from data and the data-driven learning or learning from large-scale data has been shown like very successful in vision. So we have now very beautiful kinds of segmentation results now, and then we also have like ChatGPT, which allow us to write things much more easier, and all this thanks to large-scale data-driven learning. So can we migrate this success to robotics as well? There's a lot of recent efforts basically try to migrate these 2D pre-trained models using self-supervised learning or text-supervised learning, and then transfer to the robotics task. For example, people have tried to basically use like self-supervision, perform self-supervised learning on egocentric videos, and then use this pre-trained model to transfer to the robotics task for performing grasping and pick and place tasks with this parallel gripper. So
why this success is very encouraging. A lot of tasks is still relatively simple, and a lot of these tasks also does not have rich 3D interaction or context. So what I'm actually want to talk about today in here is something I feel like is missing a lot in this robot learning community, is to learn manipulation skills that require 3D geometric and context understanding. And particularly, I like a lot on these directions of learning dexterous manipulations or with multi-finger hands. So here are some examples of manipulation skills that requires very rich context and geometry understanding in 3D space. So if you think about, if we really try to rely on using pre-training, using 2D legworks, it's actually very hard to use those backbones or representation and then apply on this task and find it is helping. So it's very hard to squeeze the 3D information out of those self-supervised pre-trained legwork. So we basically imagine if there's a smarter way to utilize the large-scale videos. So the hope is that if we can watch these human videos doing things, and then if we are able to somehow extract useful 3D information out of these videos, then this information can be very helpful to teach how the robot should operate objects in the world. I think a lot of people, a lot of researchers are also aiming at trying to work on this direction, and it makes perfect sense to do so. I think in the ideal world, we should be able to extract the 3D hand pose and 3D object poses and obtain the trajectories on how humans are doing things, and then basically use this to generate demonstrations and then do imitation learning. Okay, so all this sounds beautiful, but in reality, when we try to work on this problem like 3 years ago, we find that the 3D estimations of hands and objects are still far away from actually like usable for obtaining demonstrations. So that basically make us to go back a little bit on doing a work which now looks like basically looks like a computer vision work in the 90s. So essentially, we try to collect human demonstrations on doing things, but then just use like a green background. So only with this green background, we're actually able to extract the 3D, more accurate 3D hand pose and object pose, and then convert it to the third road, basically the object, the robots and object interaction demonstrations, and use these demonstrations to help performing imitation learning for the robot to learn. So these here are basically some examples. We are trying to convert this human interacting with the object to robot hand interacting with the objects. Well, even though it is like a green background thing, which is not very computer vision, still the pose estimation is still very bad. In the sense that if you look closely, you can see the hands are shaking, the objects are shaking all the time. And then there's also penetrations between the object and hand. So in general, we find it really, really challenging to extract geometry from the videos for learning, for generating demonstrations. So because of that, I kind of moved to try to go back to basically try to see if large scale learning can help solve this problem. So a lot of work on pose estimations in robotics community is actually focusing on the YCP objects data set. So in here, essentially, I would try to see if we can kind of get around this problem. Instead of solving these 20 objects in YCP data set, can we actually scale up the objects into much larger scale, and then perform pose estimation using this large scale data, try to learn pose using this data set instead of just 20 objects. So we collect the data set, basically contains 1,700 objects, and also use it to basically try to learn better and generalizable pose estimation for 60 pose estimation for the objects. So the idea is if we can scale up the data, maybe we can get better pose, and then maybe we can pass the human videos on the internet on the object, estimate the object geometry instead of the green background video. So here are some data we collected. So it's essentially just use the iPhone and go around the objects, and then we collect basically object-centric videos used for training. But still, there is still a long way to go from making this kind of object pose estimation working. It's still a very challenging problem. So it's still a very challenging computer vision problems, and then it takes a long time. And we continue to take a long time to make it work. So up to this point, I think you can all agree with me that it's really hard to extract geometry from videos and then use it to help robots to do learning. So instead of learning all this from videos, so in this talk, I'm trying to talk about one of the other directions to get around this. Basically, is using teleoperation. So in this video, my student is basically doing some teleoperation inside the simulator. So we talk about this work. And then another thing that is very hard to infer from human videos is essentially the force. So by looking at the human interacting with the objects, if you just look at the pixels, I mean, it's almost impossible to guess how much force it is applied on the object. So how much force between the object and the human fingers. Okay. So how can we utilize this force information and help robot to perform manipulation tasks? I'll also introduce a work in this direction. So essentially, we are trying to doing in-hand manipulations and then using force sensor to do so. Okay, so that basically leads to the two important topics that I want to talk about in this talk. In general, we are following the pipeline that use reinforcement learning and sim-to-real transfer. I'll first talk about how can we get more human demonstration data by using teleoperation, and then do more general manipulation tasks using sim-to-real transfer. And then the second part, I will talk about the tactile sensing part. So how can we get force sensors work and then also perform this in hand manipulation and then in a sim-to-real setting. So I will start from this teleoperation part. So essentially the goal is to ask humans to collect data in simulators and then train an algorithm and then perform sim-to-real transfer to basically do some tasks in the real world. So we propose a very simple teleoperation system. It's a visual teleoperation system that requires only a laptop and iPad. Actually, right now it works with a laptop, only a laptop as well. So essentially, we are trying to make this device to collect data as simple as possible. So eventually, we hope that this approach can be scaled up to many mechanical turkers instead of just operating the lab. And we don't need any VR or AR devices. So we don't need to buy the Apple Vision Pro to do this task. So the whole pipeline is following basically, we try to use a visual teleoperation system to basically collect data first inside the simulator. Once we have these demonstrations collected in the simulator, we can do retargeting to get the demonstration that is basically useful for our target robot hand. And then we can perform sim-to-real transfer to get it working in the real world. So I talk about this step by step. So essentially, we have experiment with 3 tasks in this paper. And then what we do is really just try to get human pose estimations done in simulations, and then convert this human pose to the robot hand pose, and then operate objects using this robot hand inside the simulator. So let me give you some demonstrations how this works. So essentially, so the user, the student, is trying to first calibrate his hand inside the simulator. So you can have this hand playing different fingers. So this is a calibration process. We have designed, we basically we are very thoughtful. So we have designed, we can have different size of hands, given different size of the operator's hand. So we have different robot hands to make you feel comfortable, essentially. So the human, the user in here, basically is trying to operate the task opening the door. So on the bottom right, you can see him is basically operating things in the air, but then he's actually controlling the robot hand inside the simulator to open the door. So essentially, we want to, the idea is basically, although there is still physical gap between sim and real, but the geometry, interaction, and the kinematics are actually correct. And this already is becoming a very useful information for robot to learn. So all these interactions, all these 3D ground truths can be obtained for free from the simulation. And if we can collect this kind of interactions, ground truths, then it can help doing imitation learning or reinforcement learning by a large margin. So once we collect these demonstrations, actually with the hand that is like customized for each individual user, we can actually do retargeting to convert this hand to many different other robot hands, depends on the downstream applications. So essentially, we can convert the customized hand, which is on top, into different robot hands that is basically like on the bottom, on the right is the Lego hand, in the middle is the shadow hand. So it can be applied to different manipulators. So we just need to collect the demonstration once, and then we can use in many different manipulators. So here is examples on the top left corner. We basically see that the demonstrations collected by this hand, and then on the other 3 videos are basically retargeting results, essentially retargeting the hand pose into different actual robot hands. Once we collect these demonstrations, we can basically add it into our reinforcement learning pipeline inside a simulator. I will not talk about too much into the pipeline. Essentially, we applied an algorithm that is proposed like 2018 with the demonstration augmented policy gradient approach, essentially combine the reinforcement learning turn and the behavior cloning turn using our demonstrations. So I think I like these experiments a lot, especially because it shows that learning from human can actually generate very robust policies in terms of the sim to real perspective. So let me show you this result. So on the left is just pure reinforcement learning. On the right is actually doing imitation learning using the data we collected. So we basically show that when you are learning from human demonstrations, you can get more robust graphs that is easier for sim to real transfer. So here is the task of flipping the cup. And if you use reinforcement learning to learn this task, you basically obtained a policy that is trying to just like touch the surface of the cup and then flip the cup. But if you learn like what humans do, you basically put the finger inside the cup and then flip it. So I think this is an interesting observation for ourselves, is that learning from demonstrations not only just make learning faster and more accurate, it is also providing a more robust policy. Learning behavior like humans do, actually allows much easier sim to real transfer at the same time. So in this work, we have demonstrate some applications, not just flipping a card, but also doing a lot of grasping tasks. So this is a work done maybe one or 2 years ago. So we can grasp a lot of different objects. We show some generalization ability of the policy by training on a lot of human demonstration data. So this year, this work is actually get extended as an internship project in NVIDIA. So we basically did a lot of software engineering work for this work that we extend this teleoperation system to, we call it any teleop. Essentially, we apply, it's not just for a simulator. We actually make it work on different simulator, different hands, and also real robot as well. So these are some the environments and simulations and real robots we have tried our system on. So the starting point is that we have a single system, and then it works just the same interface, the same system work on all the simulators and also the real robots and all the environment and different kinds of hands. So it's called any teleop. So here is another demonstration, basically showing that the student, actually the same student, we just marked the face. It's playing basically the hand in the air, but in the simulator is actually the hand is playing the piano there. So this is the working in the Isaac gym. So this is the Isaac gym environment. We put a piano inside Isaac gym, and it also works in real. So essentially, this is a lot of student. You have a camera in the bottom basically, and then you can just do teleoperations on the real hands on his left side. So here is a lot of examples on opening the drawer. So the same again, it's the same system that allows us to collect data not only in simulation but also in build at the same time. So it makes it's a unified interface to do all these tasks. So besides this, like contributions on this teleoperation system software side, we have a lot of software perspective that I really like. It's basically visualizer. It's built on the Meshcat from Russ Tange's lab. So if I give you this video, maybe it's not looking very exciting, but it's actually looking very exciting for me. So essentially, this is actually disentangling the simulation and the visualizer. On the left side, you're running your simulator on your server. On the right side, you're actually running your visualizer on your laptop. So you can actually not necessarily install both things in the same computer, but you can run your simulation in your web server, in your servers, and then you can use your laptop to do all the visualization. That actually, how to do visualization conveniently is actually a very important thing for robotics, but not really solved well. So with this tool, we're actually able to do something that we basically can ask. It allows us to ask Mechanical Turkers to start collecting data using just a web browser. So I'm going to do a demonstration now. Hopefully it will work. If it doesn't, I mean, I'm at home, so the network connection is better. So usually it work. I've done this talk in some schools, and then there was always a Wi-Fi issues. So sometimes it doesn't work. So I hope this I'm sharing the whole desktop, I think, and then right. So let me. I already did the environment initialization, and I copy this comment, and then it's running. Okay, so I put my hands in front of my webcam in the laptop. Okay, so the arrow disappeared because its initialization is done. So now, if you can see my Zoom videos of me, I'm actually playing my fingers, and then the robot finger is basically following what I did. Okay, so essentially, if you can see it from another angle, that is basically trying to, so if I can try to just close my fingers, I can grasp things, and then I can put 1, 2, 3, 4. I can, for 4, I actually to have all 5 fingers basically opening up, because it's like the retargeting is not getting my my small fingers. So I can wave as well. So essentially, I think this is basically showing that the potentials of this kind of pipeline, that it actually allows a very easy and low cost way to help us to collect data. So everyone can hopefully perform teleoperation by just opening a website using a webcam instead of doing complex devices. And this is also thanks to, we are actually running the servers in AWS and then the visualizer in local. Okay, so that is basically this teleoperation system. If you have any questions, please ask. I'll just keep playing these things maybe for one more minute. Yeah, so if you have any questions, I know it's hard to probably get Q&A in the virtual talk, but then if you have any questions you want to ask, now is the right time, because I'm still playing my my robots in here. Yeah.
So actually, so I have one question. So how do you handle like the absolute position of your palm and the relative position of your palm?
Right. It's actually a very good question. So it is true that essentially we don't have a depth camera in here. So we actually basically prepare a slide to answer this question in case it happens. Yeah, is this one? Yeah. So it basically it's just like we are basically it doesn't work. Okay, we cannot play. Yeah, so we are basically estimating the relative scales of the hands in basically based on just pixels. The closer one would be the larger hand, the farther away one would be the smaller hand. We are really just based on how the scales of the pixel changes to to kind of get a sense on far and close of the hand to get the scale of the pen in this way. Yeah, and then use a little bit of camera intrinsics to do that. So in here, it's purely based on pixels. There's no depth. But if we happen to have good depth sensors, it would be much easier.
I see. Thank you.
Okay. So yeah, so this is can be a very convenient manipulator for collecting data in the future. Right now, we are still working on a lot of things on writing JavaScript or any other, actually HTML codes for to making it work much faster. So it's not, it doesn't sound like much like a research problem, but I think actually still, in general, in robotics, data is really the big problem. We have collected 3D data, we have a lot of 2D images, but we don't have interaction data. So how to get as many interaction data as possible. So that is the very, very important thing. And I think this is one way to go for it. Okay, so I will move on. So let me know if you have any question. You can also put on chat if there's more. So essentially, this is one way to collect a lot of data. And then we can train a reinforcement learning once we collect the data. But then how do we do sim-to-real transfer? Sim-to-real transfer is really, really hard problem. Actually, I think it is also one thing that stops a lot of robotics like working on simulator, because a lot of times it doesn't transfer. I just want to briefly talk about this work that we find that it's actually much easier to perform sim-to-real transfer when you are learning a policy using point cloud input. Because a lot of times when you are trying to train on simulation and transfer to the real, if you just do your RGB image input or estimate the state based on RGB, it has a very large domain gap. But if you use point cloud, you just build a policy based on geometry. So for example, in here, there's actually one is on simulation, one is on real. I asked a lot of people about which one is sim, which one is real. It's actually very hard to tell in a lot of cases. So essentially in here, actually on the right is simulation, on the left is the real one. So the sim to real gap is actually largely shortened by using this point cloud as input for policy learning. So what we're doing here is really just we train a reinforcement learning policy based on using point cloud input instead of just RGB or pixels or estimated object shapes that we state as input. And this policy can be trained on a lot of different objects, and then you can generalize to allow objects in test time as well, and unseen objects in real robot as well. We also have the task on opening the door. Essentially, we actually do some wood crafting. We make the door ourselves. So we didn't make a lot of doors, so we basically changed the handles a little bit to show some generalization results. So this kind of thing, this method I just want to mention a bit. So so basically try to show that performing reinforcement learning on the geometry input has actually a very large potential and also helps sim to real. So yeah, and also helps generalization at the same time. So these are actually all the vision part. And then how about force? So can we model the force to and use it in a generalizable way? So essentially, the touch sensor is really something. It's very hard to use actually in general, because I will talk about actually next. So essentially, in this paper, what we try to do is that we try to perform in-hand manipulation using touch sensor only without vision. Okay, so the task is basically you just try to close your eye for 1 second and then pick up some object in your hand and feel about the object. You just try to rotate the object by feeling on it without actually seeing it. So that's what we try to do. So in here, we are trying to rely on the touch sensing to do it. So the problem of touch has been studied for many years in robotics, and especially a lot of work, recent work on visual tactile sensor is based on gel sites on a digit sensor like this. So one big problem I have for all these sensor is that it's usually just applied on your fingertip. Okay, so for parallel gripper, that's so much you can do just on the fingertip. And the digit sensor is also a fingertip. It's a very small scale. And then actually when you are applying on the hand is usually very large. And then when you try to use your hand, especially the electro hand to grasp objects, you will find that your fingertips a lot of times barely touch anything. So instead of going for just like fingertip kind of touch, what really important is that is actually the whole, every place is on the hand. So our work is also kind of motivated by the glove from Antonio's group, not Antonio's group, but at the MIT groups. And essentially, so what we're doing here is trying to attach the force sensor all over the electro hand instead of just fingertip. So on the left is real, on the right is simulation. So we can get a closer look at the hand. So essentially, we are attaching a very low cost FSR sensor, force sensing sensor, on top of the joint of the hand. So this sensor is very cheap. It's $12 per sensor in Amazon. If you search now, you can find it. So essentially, we try to use this sensor instead of a very complex tactile sensor because it's actually very hard to create a simulator for a complex tactile sensor. There's always a large symptom you'll get. So instead of try to create a better and better touch simulator, what we try to do here is actually the opposite. We just try to apply as many sensors as possible, and then we binarize it. So essentially, we only have information receiving touch or not touch. Okay, so here is examples. On the left is basically you touch the sensor, you can get the continuous signals on how large the force you apply. On the right is binary. You just touch or not touch. If there's a touch, there's a pause. If there's not touch, there's nothing. The idea is that getting touch or not touch actually largely minimize the domain gap between simulation and real. So because in simulation, it's also very hard to, very easy to get touch or not touch. You cannot model the details, how things are touched, what is the textures after touch, show in the gel side, like when you want to see in the simulator. But modeling whether it is touch or not touch is very, very simple. Even though this is just binary signals, but if you have a lot of them, it can actually capture a large portion of the object state. So that's basically the idea. So we are trying to just use touch or not touch, and then perform reinforcement learning in, again, Isaac Dream. So this is trained with PPO. We just rotate objects in one direction. In here is Z direction. We also do the other X and Y direction. So we train on diverse objects, just doing this task. The policy is very, very simple. It's a PPO policy. It takes the contact, touch or not touch in each jump as input, and also the previous actions and the rotation axis as input. So here is a zooming example. So you can see the little pieces of touch sensor on the hand. If you turn green, it means that it touched something. If it is red, it doesn't touch anything. On the top right, we basically have seen some pause on whether each sensor has touched something or not touched something. Okay. And the training is really just we use a reinforcement learning, and the reward is defined on how much the object has been rotated, the angles. So larger the angle, you have larger the reward, essentially. So in our experiments on the top, we basically show that if you train with a single object, train and test on a single object, it doesn't really matter if you have the touch sensor or not. Okay, so the blue line is with touch sensor, the red line is without the touch sensor. So you can just overfit to one object. It doesn't really matter if you have touch sensor or not. But in the bottom, we basically show that once you try to train on multiple objects, adding the touch sensor, very simple touch sensor, binary touch sensors, a lot of them can help a lot to get much, much better results. So this tells us that even though this is binary sensors, a lot of them can actually help capture the geometry of the object. To validate if this is actually correct, we did a little thing. We didn't use it in training, but actually only use it for evaluation. So what we try to do in here is that we just rotate the objects in one circle, okay? Once we have trained this policy, we just rotate the objects for one circle. And then we collect the touch sensing information. We collect a sequence of touch sensing information as input for a neural network. And then this neural network can do 3D reconstruction of the object shape. And we basically actually can see quite reasonable object reconstruction results by just touching the object. So this essentially shows that actually just using this touch information, we can still get very, very enough and information to understand the shape of the object. So we perform sim-to-real transfer along the object that is not seen in training time. We also have these demos on basically we try to rotate object in the dark. We didn't make a lot of these videos because in our floor we need to do it. We need to shut down the lights for the whole floor. So many labs cannot work if we do this demo. So we just do it once. But essentially, you get the idea that you can just touch it without seeing it and do the things. There's some comparisons, of course. So on the most left side is open loop. It means that you just use the same motion all the time, whether you can successfully rotate the block. It turns out you cannot. Or in the middle, you can use a closed loop policy, but without the touch sensor. So you still know the state of your fingers all the time, but you don't have the touch information. So it works. The object is easily fall down in this way. So we apply this approach in many objects as well. So the most difficult one I showed in the beginning is the duck. So we are actually able to still rotate the duck even though it's without having seen it in training time. So we can also operate on soft objects. So we are showing basically this tomato is from Whole Food. It's not a fake tomato. So we basically show that it doesn't squeeze the tomato and still rotate it pretty well. So there's objects from there's also other directions. So this is y-axis, and then there's the x-axis. So basically, yeah. So rotating in different directions, not just one directions. On diverse objects as well. Okay, finally, there's one demonstration basically showing that we can just rotate one single object, but just input different commands and then try to rotate the same policy, take in different commands, and then you can rotate it in different directions. So that's basically all. Yeah, so these are basically the two main things I want to introduce today. So essentially, two ways to learn generalizable dexterous manipulation skills. One is towards scaling the data collection. The other is how to scale the force sensing, utilize simulation, and then very, very simple touch sensor, but a lot of them. So that's basically all. Thank you. If you have any questions, please go ahead.
All right. Thank you for your talk. Do you have any questions? Oh, you have one question here.
Thank you for the presentation. So I have two questions. So the first regarding the teleoperation. So I like the idea like it's low cost and you can do a demo like in real time on your laptop. But,
right.
I'm thinking, what do you think about using using haptic glove? Because it seems like a more elegant solution to me.
Right. Of course, better device is always better. But essentially, the idea is still try to scale up. So we are actually working on like getting Amazon Mechanical Turkers to help us to collect data. So if we need to scale up that way, it's very hard to send a haptic glove to everyone. So
Right.
so essentially, yeah. So I think it works with a few haptic gloves and that makes sense. But then essentially, if we really try to scale up the demonstration in like imageless scale, so we need to have some way that they have very cheap device and still working. Yeah.
Thank you. So my second question is about your tactile project. So I think
Right.
there are like two core characteristics of the hand. So one is you binarize the signal, and second one is
Right.
the resolution of the sensor is 1, basically it's super low. So I was thinking like my question would be, because I haven't read through the paper, but have you evaluated the gain from binarization, and like how does binarization contribute to sim-to-real transfer, and also like what do you think if we have a higher resolution texel-based sensor, for example, standard setup of Ligro, you have Zella sensor, which has a higher resolution. Would that harm the sim to real transfer?
Yeah, I think it really depends on how the tactile works. So yeah, our work, we did show that comparing continuous signals and binary signals, continuous signals still works, but then definitely using binary signal helps. So that we have a comparison there. It's just that even with such just one single point of touch, still there's a large sim-to-real gaps on how false it sends. Definitely, we would like to explore more delicate sensors. It's in general just like maybe the sensor you have just mentioned is also quite expensive. No, I'm not sure whether you are mentioning the one I'm imagining, but it's like 50K to buy the set of them. So it's actually quite expensive. I think it's possible that you can do sim to real, but in general, it's just a more high resolution sensor. Usually, just like we need to like larger sim to real gaps, and then we need to do more work between simulation and real. So actually, I would in general prefer to make the hardware as simple as possible, and then try to use learning to fill up the gap. And just use learning to imagine what should we do instead of like designing more and more complex hardware. So I probably would go for that more instead of buying more and more expensive sensors.
Thank you.
Yeah.
All right. Due to the time constraint, I guess we'll leave the other questions off. And again, thank you.
Thank you. Thank you so much.
Can you join over the Zoom? Oh, you're already in the Zoom. Yeah, you can directly share your screen actually. And you probably need to like show your camera.
So it's going to project from me rather than.
Yeah, it's going to project from your own computer.
Okay. Okay. So then I need to this guy share.
So I can also like open your video so that people can see. Yeah. Good.
But do I unmute or?
You do not unmute because your voice goes through the microphone here.
Okay, and let me minimize this.
Yeah, it's good.
It's good.
Yeah. Okay. So
can people see on Zoom? Is it okay on Zoom? Nobody's complaining. Okay, fine. So we will assume that they are not. Okay, there's someone on chat. Let's see if they can hear it. Okay, they're good.
Good. Okay. So do me too. I guess that's a funny introduction because everybody knows. Yeah. I just give you the stage.
Okay, great. So so starting 40 minutes. Yeah, 40 minutes. Okay. Hands and objects. What's happening? Okay. So in the talk, I want to talk mainly about so let me pause a bit. So I'm going to talk mainly about manipulation, but I'll start with some work on locomotion. So about 5 or 6 years ago, I and my research group got into robotics. And the reason was that there are certain problems in computer vision which have made a lot of progress, like object detection and segmentation and so on. And I worked on those for 20 years, and I felt like I wanted to do something different. And it's clear that vision and robotics is, I think, 20 years behind vision. So the time has come to help solve robotics. And I think vision people have a lot to contribute. I think the confluence which will solve robotics is a combination of vision and learning. Okay, so with that as background, I want to show you some set of results. I'll start with locomotion results. These are older, so I won't spend much time on that, just give you a demo. So we worked on legged locomotion. This is a problem which people associate with Boston Dynamics, and they say, oh, Boston Dynamics has solved it. The answer is no. Boston Dynamics has done lots and lots of very impressive CAN demos with controllers, but really the future is with learning, and learning gives you flexibility, and also it combines well with the use of sensors. And so I think that's where things are going. We have done work on walking, where we basically showed that you can train in simulation and then bring to real with zero shot, with the use of this technique called rapid motor adaptation. So I'll just show you this demo, and after that, the rest of the talk is focused on manipulation, because I think that navigation is close to solved, locomotion is 0.8, manipulation is 0.2. Okay, take these numbers with a pinch of salt, but this is what we can do. So there's an onboard camera, there is no offboard computing. Everything what you see is what you get. And it's exactly the same policy. It's not 15 different policies, one controller for climbing stairs, one for going on ground, one for going on somebody's living room. No, it's one controller, period. Okay. These are stairs in CMU. Okay, so I'll stop here, but what you saw was the most important thing is generalization. Okay, that's what we in computer vision realized, right? In the 1990s, we had approaches to recognition, but which could recognize one very specific object, like a stapler or something. But the important thing was generalization, and that's why we needed to bring in machine learning. So that's what happened in the early 2000s. And then in 2010s, we switched to deep learning. Generalization. Generalization is equally important for robotics. You need to be able to walk in all these different kinds of terrain. And yet generalization has not been so emphasized in robotics. If you go back and look at your typical robotics paper or video, there will be some green cloth behind as a background to make the problem easier. They might use some markers and have a sort of a motion capture system. They'll design an MPC controller which works for that object, etc., etc. All that is great. That is like what we used to do in computer vision in the 1990s. I think the time has come to move beyond that, which means generalization, comma, generalization, comma, generalization. I showed it to you for walking, but as I said, I think the hard problems are left, which are in dexterous manipulation. Okay, so let me skip this. And this is an example of what we can do with our hands, what humans can do with their hands, right? There's a list of kitchen verbs. Okay, a 12-year-old can do all this. Okay, no robot can. Okay, this requires innovations on multiple fronts. It requires innovations on the hardware. You're not going to get to do all these things with parallel jaw gripper. You need to have multi-fingered hands. Second, you need to have sensing. You need to have vision. You need to have touch. It's not going to be done without sensing. Third, you need to have learning. It's not going to be done without learning. Learning, what does that mean? I think currently it means a combination of reinforcement learning and imitation learning. And we are working out all the details, and this will take 10 years. And I want to assure you that ChatGPT can't solve these problems. So it's ChatGPT proof. There is a role for language and instructions and high-level reasoning, but To solve robotics, you have to solve robotics. So you need to solve the low-level problems as well, or first. I don't know about first or last, but you have to solve them. Okay, so I'm going to pick, I want to do all these things. I can't do all these things. I will pick as the representative one task for dexterous manipulation. And again, as I said, parallel jog grippers are so boring, and pick and place is so boring. So I'm going to move on beyond that, right? Okay. So I'll start with this task of in-hand object rotation. And Xiaolong also showed some of this. And I think that this is a good canonical task with which to, to master our these techniques. And hopefully those techniques will work on other tasks. And there will be like, okay, so here are some results. Okay. So maybe I'll show put on the, okay, I won't put the sound on. So first thing you note is generalization, right? So that's important. We can do this in-hand rotation with these 4 fingers. So this is the Allegro hand, and we can do this for a variety of objects. So when you look for a robotics talk, that's the first thing you should look for. What's the generalization? Is it working for different objects, or does it work for one object? We will never be happy in computer vision with a chair detector which recognizes only one chair. Okay, you should not be happy with a robotic system which only rotates one object. Okay, that's one. And then to make it very clear, we've got these specs, the sizes of the object, the dimensions, the weight, and things like that. So these are the things you should generalize over: softness, hardness, all that kind of stuff. Then there are subtle things which make some tasks harder than others. So that I will just show those here. One is that we have 2 aspects of this problem. I mean, there are variations on this problem that people have worked on. And I have one part here which makes the problem a bit easier, and one that makes it harder. The part that makes it harder is the challenge that the rotation is in the fingers, as opposed to rotating in the palm. Rotating in the palm means that you have the palm as a base of support. So if you don't do anything, the object won't fall. But when you're rotating in the fingers, it requires dynamic stability. Okay, if you stop rotating, it will fall. You need to have, now you can hold obviously you can keep it stable with the fingers in a certain way, but when you're moving it, there's a dynamic stability involved. In a way, it is analogous to what happens in walking. In walking also, you need a notion of dynamic stability, and that's what this finger gait does. So you should be more impressed when the task involves not using the palm versus using just the fingers. Now, the part which makes it easy, which you won't notice, but because if I didn't tell you, is that it's rotating about the z-axis, which is slightly easier than rotating about other axes. And I'm going to show you results of that. And then I should note, by the way, if you think even further, there's a version of this task which is even harder, which is to rotate the object when the fingers are above the object, which I haven't shown. I'm pointing out all these things because there are these subtleties which make variations of the task easier or harder. And often there isn't standardization in the field. The robotics is not as standardized as computer vision is. And as a result, we need to watch out for these ways in which sometimes a problem may seem like it's solved, but it's not solved. But take it from me, dexterous manipulation is not solved. It's going to take several years. And I want to encourage the people in this room and broadly in computer vision to sort of jump in. And a very small request is please accept papers which come on vision and robotics. I'm really annoyed when I have referees who say vision and robotics, this paper should be submitted to robotics. No, the vision field needs to help solve these problems. Okay, so so these are just more examples. And then, my generalization part is good. And I will see if one of you can guess. There's a cheating bit here. There's one category of object. What category of objects does this fail on? It fails on very heavy object, but that's understandable, right? That part is not a problem. Notice that none of the objects that I have is very long and skinny. So if it is a pencil that I was rotating, this technique would fail. Again, that's the kind of thing you need to watch out for. And in robotics, people get away with this because they get to choose their examples. In computer vision, you don't get away with this because there's a standard data set and it's going to have all the chairs that people have collected. And if your technique works for chairs of type A, but not on type B, you're going to pay for it. So we need that kind of standardization of tasks, but it isn't there in that field yet. But we're trying. It'll get there by and by. Okay. So I want to say a little bit about how we solve this problem. It's done by reinforcement learning in simulation, completely in simulation, and then zero-shot transfer to real. Okay. And for this, there's a technique we developed called rapid motor adaptation, which we developed in the context of the walking work, but it applies for in-hand manipulation as well. I'll just sketch it very quickly because I don't have the time to go into details. So first, the vanilla version of, and why do we do this in general? It's because RL has high sample complexity and we can't run a robot 100, million times or a billion times, right? So what we have here is training a policy in simulation. There are pretty good physical simulators, and I know people will complain, oh, the simulators are not good. If they're not good today, they'll be better next year, and they'll be even better the year after that. Okay, this is the part where you should count on the fact that our Moore's law, or the successor to Moore's law, plus our colleagues at NVIDIA, I mean, they will take care of it. Okay, I don't know if Dieter is in the room, but people like him and his group are doing great things. Okay, I believe in simulation. Okay, so the policy here is trained with some cost function. The cost function, if you read the equations, they basically amount to saying rotate at a speed which is as close to R max as possible, and then try to minimize energy. And of course, you shouldn't let the object fall. So it's fairly straightforward, and RL is basically trial and error, and you use PPO and it will work. Okay, the twist in these problems is that the reinforcement learning problem becomes very hard when there are lots and lots of variations. So the variations here are the object can be heavy, it can be light, it can be deformable, it can have different kinds of aspect ratio and so on. And these are the things which require subtly different policies, and how do you acquire that? So there is a formula for this which has now become standard after a few years, and which is use privileged information in training. At training time, supply this, you have that information in the simulator. What's the mass of the object? What's the aspect ratio? What's this and that, friction, etc. Supply that information which the simulator has also to the policy. And now what we do is we take that, but we run it through this compressor, this object property encoder mu, which spits out like a 5-dimensional version or an 8-dimensional version or what have you. And that's the Z sub t. And then the policy is therefore like it's allowed to do different things because based on the Z. And then the O sub t's are the observations, and the observations will be like the joint angles, and there will be and the last set of actions. And with that, you train a policy. And then when you want to make it work in real time, you will not have access to this privileged information. So you must estimate it in some way. We don't try to estimate all those variables, all those parameters. We try to estimate this low dimensional Z sub t. And we can do it from the proprioceptive history, just the last second or 2 seconds of all the joint angles and actions. And this is another learning problem. That's what we call adaptation module, what this adaptation module phi is doing. And it can be trained in simulation, and it basically is it's a supervised learning problem for it to essentially emulate what the object property encoder should do. And we did this for walking, and we're doing the same thing here. And now you have a policy which can work in the real world, because in the real world, you have only the proprioceptive history. So by the way, the example that I showed so far, it has no use of vision and it has no use of touch. It's just proprioceptive history, meaning knowing all the joint angles. And then it works. And then, you can gates emerge, just like gates emerge in walking, gates emerge in the case of this task. And here's a little bit of intuition of what's inside that Z. It captures properties like the scale of the object, the mass of the object, and things like that. So the Z is like 8-dimensional, and 2 of those dimensions are shown below. Okay, so so this is a paper we presented last year at Coral, and it looks very impressive, but I gave you the caveats. In robotics tasks, you have to look at the subtleties. So the subtlety here was that I was only rotating about the Z-axis, and that's an easier problem than other kinds of rotations. And so we have now solved that problem, the one of rotating about general axes. So I, J, K, if you remember your physics 101, I, J, K are the unit vectors along the X, Y, and Z axis. So we want to be able to rotate about those 3 and an arbitrary omega. Okay, so so we'll show that. And we'll show that it also generalizes to a diverse set of objects. So first, let me note the failure. We tried to do this with just proprioceptive information, and it didn't work. That's where you realize that sometimes, so people, if I just looked at that previous task, I would say vision is unnecessary and touch is unnecessary. No, it's necessary for when the problem gets harder. Similarly, as we saw for walking, you can do blind walking on flat ground. But blind walking is not so good when you're walking on stepping stools and when you're walking up on stairs and so on. So the same will be the case here. And we have these very nice results of how much is the value of vision and how much is the value of touch. And I'll show you that in a second. So we want to have it work for any axis, arbitrary axis of rotation. And it should be generalizing, and we want to use vision and touch. So view this paper as paradigmatic of how to use vision and touch for dexterous manipulation tasks. So what's the vision setup? You see that there's the hand, and then there's an object in the hand, and then there's an RGBD camera. It's this Intel RealSense. So, and then the next image is the raw depth, which has got the image of the fingers, but in addition, an image of the object. And then computer vision to the rescue, use segment anything. And then it can get the mask corresponding to the object. So the beauty of this is the computer vision community delivering for robotics, and it means no damn green cloth. Okay. In the past, if you look at many robotics papers, they have green cloths or brown cloths or yellow cloths or whatever, which are all meant to solve the segmentation problem. And it is in a way a statement to the inadequacy of the computer vision community that those folks had to do that. But finally, we have delivered. No more red cloths or green cloths anymore, please. Okay. And then, of course, we have the tactile image. There are on these fingers, we have tactile sensors. There's this line of work which starts with gel sight from Ted Edelson's group. There's digit, and so on and so forth. These sensors are quite cool because they're about touch, but basically it's touch converted to a vision problem, because inside the finger there is some source of light and a camera, and then there is this membrane, and the membrane deforms when it is touched, and that causes a change in the appearance which the cameras capture. So read the details in other work. But we have those images now from because each of the 4 fingers has this sensor. Okay, so now let's see, have we solved the problem? And let's see the results. So now, let me see if I can put the, okay, I guess there's the sound is not particularly impressive, but this is rotation about the x-axis. And you can see it's a rickety setup with some cables and this and that. I think that in the field of robotics, the hardware problem is not done. The hardware for multi-fingered hands is not done. The hardware for sensing is not done. It's not like in computer vision, we don't worry about cameras. The camera on your iPhone is good enough. But 40 years ago or 50 years ago, you did have to worry about the capture. Well, robotics is in both multi-fingered hands and sensing is still like active research. Okay, but anyway, you are seeing the demo. I do believe that this works. So now it can rotate about x-axis, and maybe later on you'll see rotation about. Okay, so this is still x-axis, different objects, right? I hope you're by that. And then this is rotation about the y-axis. Okay. And it's harder than rotating about the z-axis. I mean, the z-axis is easy. We showed that last year. And then we can even do some arbitrary axis. Okay, so now let me get into the, so this is a definite advance. So instead of z-axis, it's an arbitrary axis, but we needed to make use of vision and touch to make this work. Okay, and how did we do it? It's the same philosophy that we used previously, where there is at the top is an oracle policy being trained, where in simulation you have access to the shape, the true shape of the object. How do we capture the shape of the object? In computer vision, we know that one good representation for 3D shape is point clouds. So take a point cloud, run it through PointNet, okay? So that's, and you have, at the oracle policy stage, you have access to the ground truth shape. Okay, and then you have access to the physics and all the rest of it. So you train that policy with this complete knowledge. And then when you are going to run this in the real world, what are you going to get? You're going to get RGBD measurements, right, from this, this Intel RealSense camera. And you're going to get the signal from these 4 fingers. And from that, what are you trying to do? You're trying to estimate the Z. So it's the same philosophy as we had for RMA for walking, but now this estimation of Z is going to capture some proxy of shape and so forth from the vision and the touch. And that's it. And this can be done in simulation, because in simulation, you can simulate the RGBD camera and so forth. And that basically works. Okay, so train an oracle policy in simulation. This includes lots of information which you won't have access to in the real world. But in the real world, when you're running the policy, you'll run an estimator, which will have proprioceptive information plus the RGBD sensor input plus the tactile sensor input, tactile sensor output. And now what do we do at training time? So the thing in sim to real is you just have a lot of variety in sim to real. So you have all these various objects, you sample their point clouds. Yeah, it's compute, but that's fine, right? You just train on a whole lot of objects. This idea has now been shown to work in multiple settings. It was first for navigation, then for locomotion, and for manipulation. I really want to stand behind it. I've sat in these rooms where people have argued that simulation is never going to work for robotics. This is nonsense. It's now, I mean, it's now, I think, quite well settled. Okay, so that's what, okay, I think I captured all this. So in the real world, we use vision and touch. Okay, so how do we train vision and touch? Okay, so now what do we know in the last couple of years? If you just woke up now, you should learn that in the last 2-3 years, there's this thing called transformers. And in every setting, wherever you were doing before, now use transformers, you'll get better. So here, the transformer is using the observations which come from images as well as from touch, and they are being used to estimate the Z. Okay, but yeah, it's like some past history, and then there's a transformer which tries to estimate that Z. And yeah, so it's conceptually quite straightforward. How do we train? Okay, so in simulated vision, so you see the difference between sim to real, right? In simulated vision, you get this very clean looking images of the fingers and the object. And then in the real vision, it's a bit messy, but it's fine. Okay. Touch, here you see the sensor, you see when you poke an object, there's some impression created. And somehow, so this is where I differ from Xiaolong's talk, where he claimed that you just needed that binary thing. Here we are getting more information about exactly where in the finger. And I think that those conclusions will vary depending on the task and the setup and so on. So we need lots of experiments to come to conclusion. So my assertion would be actually it does matter that you have more fine information, like exactly where on the finger is their touch. Experiments. Okay, so we do lots of experiments in simulation and then in the real world. And how much time do you have? 10 minutes. Good. Okay. So, and there's this Oracle, so this HORA, the top row, I apologize for this being not better visualized. I would, I mean, I would normally make my students do better, but we were in a rush. Okay. So this HORA is the old policy, the one which can rotate about the z-axis. And basically, what those numbers say, I'll give you the summary. Z-axis, we could do well before. X-axis and y-axis, there is a big difference between the old policy and the new policy. So the new Oracle policy does much better. But if it did not have, if you retrained it without the shape information, it wouldn't do as well. So the fact is that the second row has lots of bolts and the lower row doesn't. That's like an indication that shape matters. Okay. And then, okay, there is this very tedious kind of table, but I'll just focus on the first column, which maybe, and the first column and the bottom 4 numbers. I apologize. This is not how you should present results. Okay. But that 118, I mean, so higher is better. So 118 is the score when you use both vision and touch. If you don't use vision and touch, neither of them, you get 80. And if you use just vision, you get 102. And if you just use touch, you get 99. So it's beautiful. So 80 without vision and touch, about 100 with either vision or touch, and 120. This is beautiful. This is the kind of result I want to see when you talk about the benefits of multimodal information. Vision adds value, touch adds value. The two of them add even more value. And this got to be the case, right? What else is it bound to be? But if you get some other results, it's because your task is too simple or you did something, whatever. I think this is the future. Dexterous manipulation has to rest on a bedrock of vision and touch. Okay, both are needed, and we can do it. I think, and this is one canonical task, but I think other dexterous manipulation tasks are like this, in my view. So I'm very happy about this result because it's what you wanted actually came out to be true. And then the benefits, here we have stage 1. You can now do experiments where you don't have access to shape information and you have access to shape information. And it turns out that for the weirder shapes, the more elongated shapes, the benefit of knowing about shape helps. And that knowing about shape comes from the sensing, from the vision and from the touch. So this is intuitive and good. We can play the game of trying to infer from that Z, what shape does it correspond to? And it turns out that that's what this table is about. So if you look at the rightmost column here, that's what's the shape which is implicit inside that Z? And you can compare it to the ground truth. It is not the ground truth. This is where I think a philosophical point needs to be made. So this is Gibson, right? Gibson and affordances. We are doing a task, and what do we need for the task? That is what is being learned and captured in this policy. It does not have to be a metrically accurate reconstruction at the millimeter level. I mean, that's a task we defined for ourselves. And for some applications, maybe it matters, but that's not what we do as humans. We are needing to solve tasks, and there is some inference we do in a clever way. And the cleverness is we are using vision, we are using touch, and we are using integration of information as we are doing the task. And all of that comes together. And that representation in the right column, I think, is beautiful. Okay, so that's affordances. Okay, that's the information. And what kind of touch we should use, and this is too much detail, but basically it does matter to have more than just binary touch, at least for this task in our experiments. Real world evaluation. So yeah, we did all these objects. I think you saw some of those demos earlier. So, okay. So that's, okay. Now I have 5 minutes, right?
Yes.
Okay, good. I'll do 5 minutes. So now I want to go really high philosophy. This is a slide which some people have probably seen 15 times from me, which is Turing's statement about how to develop embodied intelligence. He didn't use the term embodied, but that you start with a child and then you grow it. And then Smith and Gasser, who say these things about multimodal, incremental, physical, explore. So actually, I've shown you multimodal, I've shown you incremental, I've shown you be physical, I've shown you be explore. So what's left? Use social and use language. Okay, I won't do language, okay? I leave it to the chat GPT junkies, but be social I have to do. Okay, so be social means learning from others. That's what culture is about. That's what learning from parents is about, which I translate to imitation learning, okay? And we can do a lot on human mesh recovery. Okay, this is the show-off slide, so maybe I should skip it. But we can do really well in 3D recovery now. Okay, so this is work from collaboration with like Anju Kanazawa and our students. But anyway, let me skip this. So left is the image. Anyway, you can download the code and run it on any video. It works. So 3D reconstruction of humans is solved. Okay, but hand-object interaction, that's the social part. So look at the scene. I want to use 156, there's 156 million hours of video in YouTube. Okay, probably at least 1 million of it must be about hand-object interactions. We should be able to take that and use that to train our robots. So what do we need to do? There are like 1 million ways, but the one angle that I'm going to show about here is in 3D. So lift the hand to 3D, lift the object to 3D. Okay, and then there's a hand model and there's an object model, and then we have these 3D reconstructions. We have some pipeline, but I'll just show you some results. This is the kind of reconstructions we got from single images. Okay. And then this is work, more recent work with Ilya is my grad student, and Austin and Andrew Wang were 2 undergrads. And in this, we are trying to actually use videos and then use that for training a robot. So suppose we have, so we can do this at a frame level, and then we can do this over time, where you can get to enforce temporal continuity. So, so these are some results there. So you are seeing a video of a human doing something, and then the hand is being reconstructed and the object is being reconstructed. Okay, I should be honest here. This is a little bit creaky. It doesn't work. Like it, I made very bold claims about general 3D reconstruction of the human body. This stuff is held together with wax and string and so forth. So it works sometimes. It's like your 1990s computer vision paper. But if you assume, I think in a couple of years, it'll get much, much better. But okay, I'll let you watch the videos to see that essentially there's a general technique, right? You can do it for bimanual, one hand, whatever, right? And now what we do is, okay, this is the obligatory zoom out shot that we have reconstructions of hundreds of videos. And now you want to train a robot with this, okay? So the robot, and now there is a challenge because the morphology of the human hand and the robot hand may be different, but the object is the same. So imitate the motion of the object. And that's what is being done. Reinforcement learning works better when you have a dense loss. So at every frame, you're trying to copy the hand and the object. And there's some initial reward to bring blah, blah, blah. Okay. But we actually have it now running on a robot. I mean, as I said, it's held together with, string and wax, but it does work in some cases. I think more importantly, I think this is the right direction. And I think if we keep working on it, we'll get better and better results. And this is culture. Humans don't, if we just learn what we want ourselves figured out, we would still be hunter-gatherers somewhere. Okay. Modern society is based on learning from the experience of others. And that's what we can do now, at least in some cases. And there's a lot more to do. And I'll end here. Thank you very much.
You'll have a question, just go to the microphone.
Is it
Sure.
Cool stuff as this one? Cool stuff as usual. So like you, I've gone a little bit back and forth between vision and robotics communities, and the cultural difference I noticed is in benchmark heavy communities like vision, we tend not to make claims like X is solved. We tend to make claims like we have a 2% improvement in that paper,
Yeah.
or this data set is saturated and it is time to retire the data set and
Yeah.
move on. I fear that we're falling for the same trap. I do not know all the tasks that you've solved, but in a single talk, you have told us that the 2 or 3 things are solved. Do you think they're actually solved, or that it's time to retire those benchmarks?
No. It's first of all, we don't really have enough benchmarks for these. Most of these, like all the robotics tasks, as you and I both know, we need to move out from we have solved the task to 37% versus 43%. But the community needs to agree on that, right? So that isn't quite there yet. So that's what we have to work towards. I do want to make a distinction between when I say with appropriate poetic license and the desire to entertain the masses, right? I have exaggerated. Okay. So, but I do have a sense of some problems I think are pretty close to being done, and some problems are quite primitive. So general dexterous manipulation is pretty much not done, I would say. I think navigation and locomotion, I feel much more comfortable about with respect to robotics, with painting with very broad strokes.
Fair enough. Thanks.
Yeah.
Hi, I'm Hadi. So how much do you think deploying to hardware is slowing down robotics? Like, do you think if we can have a good enough abstraction to avoid having to like deploy on hardware for every single paper, like would that help speed up robotics and like speed up the
If
pace?
you
Or
have
may
to
not
do
be there
robotics,
yet?
you have to do robotics. So ultimately you have to do it on hardware. And the point is I think physics simulators are good, right? In terms of just the physical process of Newton's laws and so on. But actually capturing those, the hardware in say your simulators is not always so easy. For example, tactile sensing has proved quite challenging to put into hardware, put into the simulators in an accurate way. Okay. So we go back and forth on this. So I think in that sense, it's totally okay. I mean, the classical roboticists, they insist that you show results on real hardware in the real world. And I buy that. I think that final proof has to be like that. Where I would disagree is that are the simulation results at all useful? I believe that they are substantially useful.
And what do you think is the golden task that should be standardized as soon as possible in robotics?
There are many tasks here, right? I think we have had great luck with navigation first. And then we did work on like rearrangement. I mean, Dhruv has been part of these efforts, which for mobile manipulation. But for dexterous manipulation, there are many different capabilities. So I don't think we even have a very clean taxonomy. So right now, what I believe we can do is we can pick one task. Like I like this rotation task, okay? And think of it as representative. We could standardize for that, okay? I think we might be able to standardize on, say, vision representations, which are pre-trained for use in a variety of like pick and place tasks. So, but the perfect is the enemy of the good. We can't solve the whole thing. That does not mean we should do nothing. We need to find where there are glimmers of light, to let us look there.
Thank you.
Yeah, my friend Sergey.
I like that you make bold, controversial statements, because then challenging on those statements makes for interesting Q&A.
Yeah.
So there's 2 things I want to cross-examine you on. So you said something about simulation, which was roughly along the lines of like, well, like, NVIDIA and Dieter Fox will kind of figure out how to make the sim really good. Something weird about that to me is that The exact same thing could be said about computer vision. In fact, arguably rendering realistic images is something we're a lot better at than generating realistic physics. And yet almost all computer vision, especially that's used in like production, uses real data and very rarely makes extensive use of simulated imagery. So what's up with that? Why is it not the same way in robotics?
No, the thing is that getting real data in vision is much easier than getting real data in robotics, because we just take lots of photos and people have taken those photos and put them up on the web. And that has had that diversity. So let's consider the diversity of chairs, right? Now, there's one way of getting chairs, which is all the internet photos of chairs. That has a ton of diversity automatically built in. If I start to model chairs and put them into my simulator, there is a question of the artist pool that I have, which will produce if I get the variety, that my rendering will be fine. But my worry is that I will not get that variety. I'll give you the case which I actually, right now, we care a lot about, which is human behavior. And the problem is that human behavior, we just don't have good enough models and so forth, right? I mean, so that's holding us back. Yeah.
So that's an excellent argument against simulation, but why do you think we need then less variety for the robotics problem?
No, I think you need okay, so that's a case by case thing. So my conjecture is that the variety that we need is captured by that quote privileged information. And that's what our empirical tests will reveal. So I'm saying, yes, you need variety of the friction and mass and blah, 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 right? Those attributes, deformation. And what we are hoping for is that we can create a somehow low dimensional, okay? And that may be easier to capture in a simulator than all the varieties of chairs, because the varieties of chairs don't reflect variations in physics. They reflect variations in human culture. And I have greater faith in physics than in human culture. Okay, or in capturing human culture.
Fair enough. I do have another question to cross-examine you on, but I think I should let the next person ask the
Okay, cool.
I have a general question that I think that learning-based precision models are very well used in robotics and they show high generalization performance, but we get high uncertainty from the visual encoders about the state, and that can be propagated to the policy. But in actual robotics, we mostly use controllers in practice, and I think that's because of the uncertainty from the visual observations that we use a learned visual encoder. So if you want to use a visual encoder and also achieve some theoretical bound about the policy, then how can we make this?
Okay, so I'm not sure if I've totally got your question, but I have one interpretation of your question, which is that in the classic robotics pipeline, there is a line drawn between perception, which is used for state estimation, and then you have your controller trained with MPC and so on. Okay, control with let's say with not trained, but using MPC, and I just think it's wrong. Okay, so I'm not. I just feel that the classic robotics way is. I think it just. The time has come to move on beyond this. I mean, the robotics people need to do the same rethinking that I had to do in 2013, which is when I was happy with computer vision in a certain way, and then these deep learning results made me question my beliefs. And I would like the same degree of questioning of your faith in MPC-based controllers and a perception stack which delivers state.
Yeah, I meant that in robotics, some constraints like safety are very important, that it should be satisfied. And even not using MPC, we can use some constraint RL or some other learning-based policies to achieve that. But most of those approaches have an assumption that we use a linear encoder. So, but we actually do not use the linear encoder. Like, as you said, transformers are very good. So if we use that transformer, can we still train the visual encoder to achieve some mathematical property like triangular inequality in the embedding
Okay,
space?
no, okay, so this is a fair question, which is safety is important, okay? But I feel that this is what I think research needs to continue, and I'm not claiming at all that robotics is about to get solved. I think that we need to work on this, and I think that this will take years. But I think we are essentially presenting to the control theory community a dichotomy. They can stay in their safe cocoon, okay, or they can go out into the slightly wild and crazy world. And in that wild and crazy world, they will. I think there's this right now this dilemma, which is you want performance and then do you want safety guarantees? And I think eventually we want both. And this will require the development of new theory and all the rest of it. So I totally appreciate that. I think that in the beginning, we have what we are doing is like cowboys in the Wild West. We are untethered by the requirements of rigorous proofs.
Okay, thanks.
Yeah. Sergey.
So the other thing I wanted to ask you about is you made this point about culture. I know partly it was like a little bit of flavor to motivate the work, but I think there was some interesting philosophical question about the role of imitation in this stuff, in the sense that, like, well, it's clear that imitation from observing people is really important, but at the same time, it seems doubtful to me that, you know, in learning how to pick up a bottle, a really critical part of it is watching other people pick up bottles. Like, you know, blind people can figure out how to pick up a bottle or a microphone. In general, it seems like there's a very delicate question as to where to draw the line between things that ought to be learned from one's own experience versus from imitation. I wonder if you have any thoughts about that and how that fits into the work that's.
No, I concur with you. I think that there is a delicacy there. I think that imitation learning, it may become a bit, there are negatives of imitation learning, right? One is that you may not find creative solutions. You may be very stuck with the morphology of the human, whereas the morphology of the robot may be different. So I think these are quite valid points. I don't know the answer to this. I feel that from what we have seen in the last several years, I think both RL and IL are both promising, and we need to push both, and there'll also be hybrid approaches. So I just like right now, like, okay, the most concrete thing is what will I go and tell my students to work on? And my answer is both. And I will hope that in a few years, we can have better answers.
Just need enough students to do that.
Yeah, sure.
Hi, thanks for a great talk. My name is Ali. I just have a question about how well would this transfer to more unconstrained setups, especially if you have a human involved and they're directly teaching the robot more in the wild kind of learning or personalization, for example.
I mean, so like if you're talking about human robot interaction and settings like that, I mean, I have no work in that area, so I can't speak to it. I feel that, I mean, what can I say? I think, look, I feel comfortable about navigation and locomotion. I think those approaches are quite general. We have locomotion, we have tried in quadrupeds, in bipeds, etc. In manipulation, all I have is one task, rotating an object. And we have just, the generalization is where we could, it took us 2 years to do Z-axis, and now 1 year we can do X and Y too. Okay, so, but I feel that we are doing it the right way, which is we have got the good angle on how to use proprioception, how to use vision, how to use touch. So that I feel good about. How it scales to other problems. I think this is early days. I made up this number, right? 0.2, right? That I think manipulation, I think of as like 0.2 of the full task, whereas when manipulation, in locomotion and navigation, I feel like it's 0.8, 0.9.
Yeah, I agree with you on the locomotion part. That's why I asked about manipulation, or especially mobile manipulation, when things become a little bit more.
No. I think look, but we need to approach it in the right angle. I feel that so much, I mean, there is volumes of literature in the robotics community on manipulation, but how much of it is based on parallel jaw grippers without any proper sensing, right? And then 95% of the work is pick and place. right? I mean, okay, fine. I mean, I think that maybe Amazon will keep you employed that way, but I don't care. I really don't care about that problem. I care about the problem of domestic robots. And you're not going to get robots in the home unless they can make an omelet. What do you need to make an omelet? It's a bunch of dexterous manipulation tasks. No robot can do it today.
I agree. Yeah, thanks. Thank you. Yeah.
Yeah.
Yeah, great talk. Thank you so much. Just have you mentioned a very interesting point between like camera and how computer vision was solved by all the images, and then you mentioned something about the robotics hardware, like some like near future someone will figure out the hardware for a robot, but I don't really think there is a like a parallel story between camera and photos versus like robotics hardware, and how the mass adoption of robotics hardware probably comes after we solve robotics. So I don't think there's a motivation, or I'm not sure like robotics hardware will be solved before
No, it's a co-evolved thing. I would say that the hardware co-evolves with the policies. So in my view, I'm conjecturing here, but in the past, a lot of this more funky hardware was not in use in robotics because the standard design methodology of your MPC controller couldn't handle this sort of stuff. Okay, so then you said, oh, we don't want to mess with those kinds of hardware. Let's keep things simple. And I'm saying that funky hardware and funky sensing can be dealt with perfectly well by learning techniques. So we have expanded the design space. Okay, and now in this design space, we have to have co-evolution. We have to have people working on the actuation, the hardware, the hands, people working on the sensing, the tactile and so forth. Maybe the vision, we can say we just use your off-the-shelf camera. And we need to be finding tasks, and we need to be developing policies. And then after a while, we find, like, okay, let's take the example of tactile. There's a lot of debate about how much spatial resolution do you need for tactile sensing. I mean, in Xiaolong's talk, he wanted like 5 places where he could judge touch, and binary was good enough for him. I'm saying I need a bit more, but who knows? I mean, this is the work which only gets done when you really solve like 15 tasks, right? So all that data needs collected, and people need to do that research. And then maybe we'll say, okay, maybe we don't need high-res touch. I don't know. I mean, I think that maybe for most tasks, it's an empirical question. And then what will happen is that the community will concentrate their research efforts on this. How many degrees of freedom do you need in a hand? How many fingers do you need? All these things, you need to be exploring the space. You need to be, but it is like, I mean, that very traditional computer science thing is to say hardware, software, co-design. And here the problem is in spades. It's not just hardware, software, co-design. It is hand, sensor, policy. This triplet has to be co-designed. It's not going to happen in one day. It's not going to happen in 1 year. It's going to take years, but it is the right battle to fight.
Thank you so much. Do we have time for a follow-up question, or
just one last question?
Oh, okay. I guess. Okay, I'm the lucky one, I guess. Yeah. So just to follow up on that, like like maybe the robotics problem won't be solved really by robotics hardware. Like camera wasn't created for like taking pictures, not for computer vision. So maybe say like in 10, 20 years, really like the VR or whatever, those kind of stuff can be like what the actual like data source for robotics is, instead of like imagine so camera took a bunch of photos and then help computer vision develop. Maybe there's like another total line of different possibilities out there.
I'm a thoroughgoing opportunist, and I will exploit success wherever it comes from. Okay.
All right. Thank you.
All right.
All right, so thanks so much for the nice talk and discussion. So we're behind schedule, but that's totally fine. We're gonna cut the closing remarks short to still end at 6. But I think we should give people a time for a bio break and also get some water and coffee if you want to. So we're gonna come back to 5:10 for the panel discussion as our last item. So and while we are setting up, and feel free to step out to get water or take a break. All right. Yeah, and this moves to the
Oh, having sit next to me. Hello. Cool. Okay, so let's see. Let's go. Right now. Tell me all about it. How's it going? Okay. Oh, that's awesome. Likewise. That is really exciting. Well, I guess it's congratulations because there's a whole new instant whatever. It's been I'm gonna cancel stuff all the time, like before it gets announced. So the fact that it's sort of announced, I feel that sorry, I have one follow-up. Thank you. That implies sort of a minimum expand. It's like yeah, that's like I guess I don't know. I'm sort of it does now like well I guess I know what I not be ambitious and I agree. Don't feel like here
Hey, Pete, are you over the Zoom?
I'm here.
Oh, I can see you. Great, great, great. Yeah, I guess you're the only one online. All the other people are like in person. Yeah, I'll try to turn the camera so that you can see them.
Sure, thank you.
Might be a little tilted.
So the Jenya, you have like background blur on. Do you know what I mean?
And I mean, of course, like, I mean, also sort of like
Oh, true.
Yeah.
Yeah. Oh yeah, yeah. Yeah. So it's
Okay, folks, please have a seat, and we're gonna kick off like the panel discussion, and we have our moderator here, Ian Lee, and he's gonna take the lead, and we have the panel both online and in person. All right, so
okay.
Yeah, Ian, take it away.
Hi, I'm Aaron Lee from AWS AI. I'm going to be the panel moderator. We're going to start some, like high-level questions, and then going to ask the panelists, and then we can open up for discussion to the audience. Yeah, let's start from a very high-level question. So I want to reflect that, how we got ChatGPT and GP4. So it really started from, this scaling law, right? So the scaling law of language models, right? So as you keep scaling, and then test time loss goes down, and then it's actually equivalent to compression, right? You're compressing your data, and there's also a school of thinking compression is intelligence. And then as you keep scaling, with data compute and model size, and then essentially, some people think, oh, they're just statistics, but what we got is actually, something more than just statistics, right? Essentially, model are pretty good right now. I saw a lot of tasks. Of course, there are a lot of problems, but I'm sure everybody is impressed. So I think this is the guiding principle for, how we got here for large language models. My questions to each of the panelists: what are the guiding principles that can help us make progress in studio vision and robotics? I'd like to start from people from virtually, I guess. Pete, do you want to start? What are the guiding principles? Do we have them right now, or we don't? Or yeah, what are the guiding principles? I mean, it doesn't have to be very efficient, but the scaling law is also not very efficient. But at least we know what we're going to get roughly, right? Like as we keep grinding it.
Sure, thanks. I can say some things. I think it's a good question, kind of. Let's all take a look at the recipe of GPT-4 and try and think about how that applies to robotics or not. I think that there's certainly a certain amount that can, but I think the challenge of embodiment is incredibly challenging for a number of different reasons. If you just try and think about, okay, let's try and scale up the data to, orders and orders of magnitude more than we currently train with in robotics, because that is how it works in large language models and in large visual language models. Let's scale it up. Let's scale it up. Okay, so one question would be, what type of data is the data type that you want to scale? And I think no matter what you think the best answer might be, they all have huge challenges, right? So one that seems pretty scalable is simulation, of course, but everybody knows, anybody who's tried to scale up simulations to be super interesting knows that that's actually super challenging. And there's, of course, always going to be the sim to real gap at the end of that road. Let's try and scale up, just actual robot data, of course, would be another one to throw out there. But the cost of that, everybody knows, is incredibly challenging. There was a lot of discussion today on trying to scale up watching humans or, sort of more passive video. That is, of course, also reasonably good path, I think, but you don't actually have the action data, nor do you have sort of full access to the rest of the embodiment. And there's also another huge challenge here too, that like language models and visual language models, they're all kind of the same embodiment. They all take in text, they all spit out the same type of vision and text. But every time you try and train a robot policy, it's a different robot. Even if you have the same design, even if you have the same instances or different instances of the same sort of design of a robot, each individual instance is different. All these challenges compound. So I think there's a lot we can do to try to take a page from what has happened with large language models and other large multimodal models. But we do need more and different things in robotics. I think we're starting to see instances where we can transfer a large amount of knowledge to make embodied tasks work better, transferring knowledge out of vision and language domains, but that will only go so far. I think we need to keep fighting the good fight and figure out what we can do for trying to come up with new recipes as well in robotics. Maybe I'll stop there. That's some initial thoughts.
Okay, great thoughts. Thanks, Pete. And then it was Xiaolong. Oh, not online. Okay, then we come back to in person. Okay, maybe start from, yeah.
I think researchers suffer from a particular pathology that we want to be creative, and we are usually looking for creative insights and ideas, and somehow data engineering doesn't seem creative or interesting enough. And my response is the first order principles are the same, and there is nothing special about robotics. The first order principles are data, and most creative insights are second order or third order insights. Where does that data come from? Wherever. We'll take wherever it comes from. Simulation, videos, human data, disembodied data. Eventually, once robots have certain capabilities that are limited function and they're actually in the world, real world robotic data. But if I had a choice between hiring a creative researcher and annotating a data set, I would take the data set every single time.
Okay.
I think the last two answers are good. I don't want to add to that.
Let me see. So my background is in 3D graphics, 3D data sets, and simulation. So being a proponent of simulation, I'll add a little from that perspective. And I want to make an analogy with the success of large language models and ChatGPT. The data that enabled that, the sum of all human knowledge encoded in text, right? Essentially, it contains many things. It contains facts about the world. It contains imagined facts, right? Lots of different kinds of things that are encoded in all of that text. I think there's a role that simulation can play where it's not the real world, of course, but there are many possibilities. We can explore many axes of variation. We have models of the world, right? We can imagine alternative worlds, different parameters for physics. All of that data we can enable essentially with the use of simulation. And of course, real observation from the real world should be in that sum of data. And, the two together, I think can, hopefully by analogy to what happened with, text recording the sum of human knowledge, can drive forward progress in robotics. So some combination, I think, of simulated data and real data will, drive us forward. Yeah, and I agree with everything that's been said so far. Data, right? Push it, data.
Yeah, I give the quote from Sherlock Holmes: "Data, data, data.
Okay.
I cannot make bricks without clay."
I think I agree with whatever has been said, except I'll view this as an opportunity. I think scaling up was easy for vision. It was easy for language. It seems like it's not so easy for robots. And I think that's an opportunity. How can we share experience across different embodiments? Can we scale up gathering data in the real world? Being opportunistic, take things from videos, et cetera, et cetera. I mean, I think these are all opportunities on how we could. I think I don't have anything concrete to add, but in contrast to what Dhruv was saying, I think data engineering is important over here. We need to figure out how to get data, and that I think is a creative process in my view. And that's what yeah.
Okay, great. Okay, so we kind of converge on data. So my next question is, we can think of human data, right? Human data are, at least humanoid robots, right? So we have tons of human data. Like, how much can we push human data, right? Let's say we learn a policy from all these like internet video data, right? Like solve all kinds of tasks. I mean, then we can worry about how do we adapt it to robots, but like, what do you guys think? Is that possible? And let's see. So now I'm gonna start from Saurabh. Yeah.
Yeah, I think that's an excellent question. I think at the end of the day, there is embodiment gap, right? And in certain domains, there is more gap. In certain other domains, there is less gap, right? Like in navigation, videos or, egocentric videos and the view from a robot are, not the same, but similar enough. You can imagine some sort of transfer working there. You can, figure out what actions are there and such. For manipulation, I think it's not quite true. I think like hand is a lot more dexterous, but most robotic manipulators are either paddle jaw, which don't do much, or even if they have like fingers, they're not as dexterous and such. So there's gap over there. And I think in my view, you can't directly learn. I think it'll be difficult for us to directly learn from just observing and then motor policies. I think there'll be some agent specific work that will have to be done. And I think it's a good question to try to understand what is the limit. What all can you transfer and what all do you need to learn specific to the agent? I think that's an very interesting question. And if you can come up with some sort of a characterization of that, that'll be very nice. But I can't think of an easy way of doing it.
But is it yes or no? Like we can learn a human policy to solve all the tasks by just training from internet videos.
But no, I think my answer would be no, because there is an embodiment gap. Things that a human can do or things, is not the same as what current robots can do.
Okay, then a follow-up question: if we augment with small amount of like embodied data.
Yeah, then I think, and there are results of that form already, right? Like if you look at R3M work or visual pre-training work and such, I mean, it's doing that. It's pre-training representations on internet data and then using real-world fine-tuning to, and you find it is useful. It doesn't entirely work, but it is still useful, right? So I'd go up for that kind of a solution.
Okay, so that's a yes.
Okay, that's a yes in that case.
I agree with what was just stated. And I think it's important to realize when we say human data, right, what do we mean primarily? We mean these visual observations of humans doing things, right? And that's missing a lot of important aspects, right? So this, touch, of course, we are not getting that when we, talk about the form of human data that we can leverage at scale nowadays, internet data of humans. So a combination of visual observations of people with some other ways to, capture touch, the experience of, being an agent with different morphologies and trying to achieve a task, I think is required. We can't purely rely on, observation of people without, considering all these other ways in which, one needs to learn how to achieve a task.
So I generally agree with what was said, but maybe a point I'd like to make is private versus public. And the thing is that a lot of all the text on over the last 20, 30 years, whatever text existed before, it got put on the internet, right? All the books got scanned in. I mean, then you have Reddit forums and all the rest of it. So the text that was available for a chat GPT or GPT-4 was like pretty much everything, right? Okay, vision data, then we go into images, and for purely vision tasks, not robotic tasks, we had the benefit of YouTube or all the images, like 1 trillion photos on the web and all the rest of it. Okay, when you think about a robotic task or manipulation task, what you want is actually, it's very private. It's like all my muscle activations recorded over time, maybe even my neural activations, because those capture my intentions. So there are the intentions which are there in my motor cortex and prefrontal cortex. There is the muscle activations. There are my joint angles. If you could record all of those and put them up on the web, and 1 billion people did that, I mean, maybe we suddenly, we would have a lot of data. But that's not, that's what is there for language. Language is the most complete record of all. See, writing is a relatively recent thing in human civilization. So everything, but in writing is designed for transfer, and all of that landed up on the web so these guys could use it. I think that as we go towards the embodied kind of data, we have, it is a very private kind of data, and it is not readily available. And I, in fact, wonder whether we'll ever have that. Like, how many people will consent to have electrodes on their brains and in their muscles so as to record their lives and, put like 1 million people's doing that on the web. So, but we'll find ways around. That's why there's a lot of improvisation which has to be done in this space. It's not going to be exactly the same way.
Okay, thanks. Yeah, Jove, yeah.
As I heard some of these answers, I thought in some sense, the question you're asking is whether the embodiment hypothesis is true. Right? Do human-like minds require bodies? And I'm betting, yeah. And if that hypothesis is true, then no, you cannot learn everything from internet scale data sets that are disembodied. The example that usually people go to these examples, like, have people done that thing where you take a deck of cards, you split it into two, you try to shuffle them, getting them in, evenly interleaved. So just right now, I'm trying to describe this task to you. You've seen dealers at casinos maybe do it, but imagine trying to teach someone that task with, as I just did, with language. You're not getting it. Think about the people who can shuffle cards. How did you learn that? Maybe somebody showed it to you. So now we're getting to like imitation, watching someone else. But even after that, the first time I tried it, I just ended up with 2 slabs dropping one after another. And it's like, there's something in the fingers. It's my fingers versus your fingers. And there's a subtlety to the cards. This feels like qualitatively to me what's going on. There are tasks that require your muscle activations, and your brain is not a drop-in replacement in and out of your body. This is the mind. And so no, the answer would be no and yes. So no, just from disembodied data sets, and yes, with access to embodied.
Well, the question is like how much you need for embodied data, right? Is that if you just augment disembodied data with a small amount of embodied data, would that solve the problem?
I don't know.
Okay. Okay, good. So now we move to Pete. That's on Zoom.
Sure. Yeah, I think the question on any type of data is yes. Like, do we want it? Yes. And I think one thing that we learn with massive transformer or other similar very large capacity models is that they can take all of the data, and you know, we don't need to have sort of too much philosophizing about whether one source is the right single one to go after or another. It seems very likely that if we took all of the observation videos of humans doing things and all of the different embodied data from all of the different robots and all of the simulation data, that we could train something that could be useful on all of it. And in terms of, you know, what might we learn from watching humans you know, do things in videos? There's a lot of different things you could come up with. Even one is just a lot of just how the world works, you know, just you know, learning physics, you know, raw from data. I think there's so much dexterous interesting interaction that, or even non-dexterous, a lot of things that humans do that is just you know, rich in providing a general model of how the world works that could be useful for robots. So yeah, I think that over the past year or two, I've gone a little bit more towards this view that we don't need to pick one or the other. We can, you know, try to absorb it all. And it really comes down to a certain point, some very practical side of engineering, like, okay, how much gain do we get out of X type of data versus how much gain do we get out of Y type of data, and where do we want to be, you know, investing resources to try and make the biggest strides? I think that's a very practical way of thinking about it. I do think one thing that is challenging as well to think about here, and it relates to, you know, the limitations of just watching humans, is it's pretty hard to get really expert data. That's one thing that's very doable in language and vision language pure domains, and it can be really hard in robotics domains. You know, teleoperation, always, if you try to teleoperate dexterous tasks, there's always limitations there. And who's to even say that we want necessarily our robots to embody a specific form that is teleoperatable easily? So I do think that's one of the hard ones. And that, at the end of the day, maybe makes it such that in the embodied domain, RL is not this little thing that just comes in at the end to do alignment, but is actually maybe a bigger part of the puzzle potentially. But I am very pro just scaling up supervised as much as we possibly can and seeing how far that takes us, and then reassessing. And I think we're nowhere near, you know, actually doing that. So anyway,
Okay,
I'll
great.
stop there.
Yeah, good. Do you have a question or? Okay, go ahead. Yeah.
Thanks again for the answers, and taking inspiration from your question about using data and, like, you know, massive scale data, and also inspiration from the impressive work that Sandra showed about, like, you know, human mesh and like hand mesh and how this can be used for teaching robots. So stepping a little bit back from robots to actually 3D vision and thinking about what's still open to be solved from web scale data in the area of 3D vision. Like, for example, Sandra was showing the whole idea of, like, you know, like getting the 3D hand manipulation of objects and how this can be used for robotics, but staying in 3D vision space, what could be still be solved by looking at this massive scale web data in the space of 3D vision? And then once we kind of like hammer this with like array of like problems, hopefully this will lead to a new generation of you know, robotics techniques that can use this for imitation to solve the data problems.
I can speak specifically to the issue of, I'll make some sweeping remarks about the state of the world in 3D vision. So I think 3D vision is significantly behind 2D vision, and it's due to data. It's due to a lack of data. It may be that we have kind of the right kinds of techniques, but we don't have the right kind of data. So see, what can humans do with, I mean, an adult human? I can take a single image and I can lift it to 3D, right? And we can do that for a variety of objects and for people, and there's a lot of generalization involved in that. I can do it for this kind of chair, which I've never seen before. Now, what do we have in computer vision? We have a bunch of techniques which work, I think, in two regimes. One regime is what I would call very category specific 3D reconstruction, like humans. Humans is one category for which we have tons of data and we have a very good sort of model, and then we can estimate the parameters of that model. And that's basically the stuff that I showed is leveraging of that. The second category that we have is essentially SFM, multi-view geometry. You have lots of views and you reconstruct the world. And by the way, NERF is just multi-view reconstruction. I think there's just, NERF is great, but it's basically multi-view reconstruction. Multi-view reconstruction has been around since photogrammetry in the 1880s, okay? And there have been variations of that, but it's basically multi-view reconstruction. Multi-view reconstruction is far short of human capability of 3D-fying images, because we can 3D-fy an image where we can generalize across categories, we can do it from a single image. Somehow our experience, which includes multi-views and which includes motor interactions and so on and so forth, gives us, for the time you have a 10-year-old, this amazing ability to have this 3D capability. We do not have this in computer vision. And for this, part of the problem is we don't have enough data. If we had, for example, tons and tons of multi-view data for lots and lots of categories and objects and scenes, we would be in better shape, okay? If, for example, like everybody roamed around with an RGBD sensor rather than just an RGB sensor and put 1 trillion photos on the web, we would be in better shape. So there is a lot there. I really think the building blocks are there, but we haven't solved the, like, I don't believe that the problem of 3D from a single image is solved. We have just got results which are in very specific setting. The big model, right, for that doesn't exist yet. And, but it can exist if we had enough data.
Wouldn't like video data online?
No, video data helps, but video data is non-trivial. It doesn't capture that because oftentimes the nature of the video that people collect often doesn't go around an object. So you go look at, so they're like 180 views rather than 360 views. And so you don't get that full view of an object. Now, when people do this scanning with a Matterport scanner and so on, then they do it. But that requires special effort. But what do you have Matterport scans for? You have them for, you know, apartments and houses and so on, but it's still quite limited with respect. And then there's a lot of 3D data for the road environment. So there's a road environment, and then there are these scanned in apartments. And in those regimes, we are quite good. But is this the totality of the human visual experience? No.
Maybe a very short remark to add on that. So I think the time domain is really important here as well, right? So when we talk about 3D data, we are talking primarily about this, you know, mainly static view of the world, right? And it's really important to consider that, you know, maybe we're no longer talking about 3D vision, maybe now it's becoming 4D vision, but, you know, as humans, we can walk into a kitchen and very easily understand, okay, here's all the cabinets, how they could be opened and closed. You know, if I walk up to this fridge, you know, this is how it would, you know, I could swing open the door and get access to the things inside. That kind of data is, you know, we're missing entirely. So that's a big challenge, I would argue, for reaching that level of 3Dification plus time domain understanding that people have from the perspective of 3D vision. Yeah.
I think one more thing I like to add on top is I think it's also the question of what is the task that you are interested in, or what is a good 3D representation, and the answer may be different for different tasks. So if it's a graphics task, then maybe, well, precise 3D reconstruct, or let's like some AR VR kind of a task, maybe like precise 3D reconstruction is useful. But if you have a different kind of a task, maybe that's not very useful. Maybe something less is more informative, or you know, thinking about like support relationships is more interesting or useful. So I think the question of representation for 3D, and in particular, when viewed in context of downstream tasks that we would like to do, becomes very interesting and such. And for manipulation like tasks, I think I'm kind of pulling it back into the robotics domain. things deform, right? Like there are cloths, there is like free-form things, and they deform. And how do you represent these deformations? Is it again precise 3D or not? Or I mean, there are things that are supported. You have to reason about support relationships and so the representation question to me is actually very interesting, and it doesn't come in as much if you're thinking of if we just think of 3D in isolation. But once we start thinking of 3D, leading into other things, then that question becomes a lot more interesting. So.
I guess the only thing I would add is Jitendra actually made this claim, but he's made a different, more nuanced claim in the past, which is he said that the human abilities at 3D are better than machine abilities, but in some sense there's like zones of expertise. Humans are bad at predicting absolute values of height and depth and things like that, which point clouds and SLAM will give you accurately if there's enough data. And the reason might be that we don't need to. Maybe our representations of 3D are again from a first person perspective, that there is, I sometimes don't know how big something is, but I need to know, I know how I need to maneuver my body around it. And that is a representation of the world, which is in the reference frame of the embodiment that I'm operating under. I mean, more data is always good, but I wonder if there is an interplay here of eventually 3D representations should be captured from an embodied setting rather than like a SLAM-like perspective.
So I guess gets into the next question I want to ask, is sort of more specific, right? Come back to the really, 3D representation, right, for robotics task, right? So I think, you could do detection explicitly sort of represent like objects, right, as bounding boxes or masks, or you could have slots in the slot attention, like, architecture explicit has these slots, right? And then, or you could just like, nothing explicit, it's just transformer architecture or stable or diffusion architecture, right? So I think people have really found really surprising that, your latent diffusion model actually can represent objects very well, and then also knows object composition. So it seems among the three representations that, really compositional generalization only exists in this, text to image model, right? The other two doesn't have compositional generalization. So my question is, what do you guys think what are the right representations, right, first, for robotic task, and then can actually compositional generalize? And so that's one, right? Then later on, like compositional generalize, and then to be able to solve, really robotic task, right? That you can actually reason like this physical common sense reasoning in order to solve these tasks, right? So so I think maybe let's start from Pete, and then we'll come back to the in person.
I'll give try to do a short answer that it is very alluring to want to design representations, but definitely that just have some massive model that is trained to do all the different robotics tasks we could think of. Maybe that is enough, is certainly one possibility. Of course, robotics is very vast and there are many different tasks. So, this type of a representation for a robot might need to be capable of extremely long context and be extremely multimodal, and would push just sort of technically in a lot of ways beyond what we have now, but could certainly be possible.
Okay, great. Start from Joe.
I don't know what the right representation is, but I'm fairly confident on a wrong one.
Okay.
And in that, I would encourage people to just read Rodney Brooks's papers from the 1980s. I mean, that man has thought through most of the hard problems. The wrong representation is trying to come up with like the sensing planning, actuation, abstraction, and it lets you very easily pass on the burden to the computer vision community. Please give us not only objects, their masses, their friction properties, please give us a working model of the world, and then we can do planning on it. Excellent. That delivery is not coming. It's just not coming. And it not only is it not coming, there is a compelling argument to be made that that is the wrong representation. And that's not how humans do it. Yes, it doesn't provide you guarantees, but humans don't provide you guarantees either. If you want human like generality and general purposeness, maybe you have to live without guarantees. Yes, we can point to explicit representations, give you compositional generality, compositional generalization, but maybe that's not that important. Maybe if you have enough data, it doesn't matter.
Okay. Jitendra, yeah.
Yeah, I mean, I would like to say that I think maybe instead of thinking of it just as representations, because I think representations here often mean representations of trajectories and so on. I would rather think in terms of sort of controllers or policies. So we have policies, and then we have policies layered on policies, and these policies are always, there is some input and some output, right? And these are composed in some way, right? Obviously, if I say I want to walk out of this building, I mean, that policy has building blocks where the smallest level is me getting up from this chair, right? So the space that we want is really the space of policies. Then we can get into, are they model based or are they model free or some mixture or what? But now talking of the representation often leads you down to this partitioning, right? Okay, there's a visual representation. Now, I think we have probably moved beyond that very classical thing that Rod was criticizing, but I don't think we have settled on what that is. I think that we end-to-end training for one task will give you a policy, but that's not enough. I don't want, just like I don't want an object detector for chairs living in isolation. I want I want more than that, right? I want a sort of a bigger universe in which that is. And similarly, in language, I want that bigger universe, and those bigger universes bring you something. Similarly, there is some, these controllers or policies, they have to live in a bigger universe. And I'm not quite, at least I don't understand that space properly. I just don't know how compositionality like things play out in this space.
That's a good point. Yeah.
Yeah, I'm not sure if I have a lot of intelligent thoughts to share on this, but maybe I'll take a very different interpretation, a much narrower interpretation than the one that Jitendra just took, from the perspective of maybe a graphics person at heart. I think of when somebody talks of representation, I think of geometry, right? How do we represent the world? How do we model the world? And there are many choices, and the important aspect is what operations are easy and what operations are hard, right? Explicitly representing surfaces, can we, know sample points from the surfaces, or implicitly representing surfaces? Do we know whether we're inside, some volume or outside? Things become easier, things become harder, right? So my argument here is that some combination of representations will be necessary, and it really depends on what, computationally speaking, what operations will need to be easy and what operations will need to be hard for the task at hand, right? And critically, we need to be able to go from one to the other to the other. Now, this is very much from the narrow perspective of just talking about geometry, modeling the world. Perhaps there's, a generalization of this that goes up to, this broader perspective of, more broadly thinking of, okay, we have policies and we, compose things, and how do we make that work? Some way to, have different alternatives and be able to interoperate between those alternatives, I think will be important.
Okay, I think I maybe want to say three things. So one is I think one universal representation for 3D might not work for for efficiency reasons that, different tasks might care about different aspects of 3D, and it might not be efficient to have just a single representation which serves all, right? I think, at the end of the day, you can say, okay, I have a graphics kind of a thing, so everything should be reconstructed precisely and such, and that might be an overkill for some other application. I think that's my first thing. Second thing I want to say is, I think we would like, at the end of the day, it's also something to do with how much data you have to train and, the associative bias variance trade-off, that if you have less data, then you'll have to put in more inductive bias into it in order to get it to work. If you have lots and lots of data, then you can do with, even less structure and so forth. And the third thing I want to say is, I think we would like a representation is useful if you can not just do one task from it, but many different tasks on it, right? And going back to what Jitendra was saying, you don't want just a separate policy for each different task. You would like to do some sharing, and maybe that sharing, so I think it's a complex design space, and I wish I knew the answer.
Okay, yeah, thanks. You got a question?
Open-ended question.
Okay, sure, yeah. Sure, go ahead, yeah.
Just so we can hear online.
Yeah.
Okay, so throughout this panel discussion, we have speculated about the role of kind of passively collected web scale data for training embodied policies. We have also speculated on the role of sort of simulators for training embodied policies. What are our thoughts on using passively collected web scale data to improve the simulators? Is that a dead end? Is that just a giant distraction? Is that harder than the problem of learning the embodied policies in the first place? What are our thoughts on that sort of sub problem?
I can say,
yeah, go ahead.
Sure,
please.
yeah, I can say, I just think it's an interesting question and connects to a couple of threads of the conversation that just happened, because, there's kind of no way around that, at least a simulator in the way that we're probably mostly thinking about a simulator, like a simulator has explicit representations in it. So if you want to solve the problem of watching a bunch of video and then make your simulator better, I'm not saying you need to, but potentially you need to solve this whole thing that we were talking about, which is, kind of what are the representations and what's the right way to do it and what's the right way to extract it. And at least one thing to consider is that if you don't do that, then you could potentially avoid this question, and you can just have a ton of data and train on a ton of different tasks, and you don't need to connect the two. At the same time, I'll say that, but I'll also say that I do think, yes, for sure, you could try and do this, and there might be a bunch of interesting things that come out of it. And yeah, we could kind of consider this system identification of the world and put that into your simulator, and I think that'd be awesome. So yeah, I see both paths.
One specific thing I would say is we need to put humans in our simulators, and we are not going to put humans in our simulators without having reasonable models that we have learned of human behavior. And to acquire that, we would have to start from data like YouTube videos. So that's certainly one case, and there are more.
I think this is a really awesome direction. People have done little bits of this idea, as I'm sure you know, but there's briefly an idea floated of something called a neural augmented simulator, where you have some black box, not black box, but like a physics engine that is producing a state and observation, and a thin layer that takes in this observation and adds in a deformation. And you can learn those with small amounts of real world data. There's a version of this idea even in the Gibson simulator as goggles, if you will. And people have played around with this idea. I think there's some legs to it. It just hasn't been scaled up. The emergence of NeRFs and neural rendering I find very promising. I think if that can be combined with classical renderers as producing a diff rather than trying to produce the whole thing, that could be very cool. Same idea in physics, ST+1 from ST and AT, and then you have a delta ST+1 that you're producing from a neural physics engine. That would be very cool. I think in general, the benefit of this approach over directly trying to improve your policy is leverage. You get greater leverage here, because now you've improved your simulator, which you can, you can do model selection, you can train it for multiple tasks. It's the same reason why model-based RL makes a compelling argument. It's just, it's hard to get models, but the argument is the same. If you can, then you can use it to get leverage on multiple policies.
Anyone else want to? No? Okay. Any other question from the audience? Oh, go ahead.
Hi. So I guess like all of us agree that we need lots of data for like training models and stuff. But one thing that's kind of missing here is that we say we want to train models, but similar to what happened with ChatGPT, there was this proxy task of like trying to predict what's the next thing. And we need some sort of like self-supervision or some task, right, to learn these representations. Like, do we have a thought of like what can be this proxy task for robotics or like embodied AI?
For trajectories, we can do the same thing.
Sure, like reconstruction, and this works for like
masking in slightly different. There are variants of that for vision and for alignment, and this thing works for trajectories. There's literally paper for mask trajectory model.
Yeah, I mean like this works for like reconstruction and like predicting the future frames, like that works in the sense like, okay, you made an argument saying that we might not need like very accurate 3D and stuff like that. We can't do things like those or like some sort of like dexterous manipulation and those type of tasks with this sort of representation that we're learning with just reconstruction and say masked based tasks, right? I guess like the question then would be that you can do reconstruction of these signals, but can you force your model to like learn the right type of latents to reconstruct these signals, right?
This is the next time.
Yeah. Okay.
So I think if you can figure out the scaling law, right? So I think this, you're kind of trying to reconstruct, let's say, the next frame, predict the, the next trajectory, right, in the future. This is kind of you're compressing your data, right? So if you can sort of do a study, if you have a scaling law, I think you might keep learning the right representations, right? Yeah.
Okay. So I guess the answer is that like if we can get privileged information for all types of data, then just like doing like masked reconstruction is good enough.
It's version 0. Start with that, and then when you compare it.
Pete, you want to chime in?
Sure. Yeah, I wouldn't underestimate just doing exactly that, and even consider that the entirety of imitation learning can be considered a subset of this. So yeah, it could be pretty powerful, but I'm not convinced it's the only answer.
Great, go ahead.
Yeah, hi. So I wanted to ask a question about the future. So we've had these comments about how we need to collect this data, right? Clearly. And one option here is like you get these glorified vacuum cleaners, you put arms on them. Then they're now like 50 years from now, everyone in their house has them. And so you have this huge amount of data that you're collecting, which is of the order of, let's say, the natural language data sets. But then do you think our only real hope for the future is if the embodiment problem no longer exists? So we really want to collect data for humans, for like humanoid robots. At the same time, it's also really stupid to like make a robot with legs when wheels are better. So what's like the hope for the future? What do you expect all of this data from humans that we collect to work out for at the end?
So a few things in there. I think the cross-embodiment generalization problem will need to be solved. Even if you want to learn from human videos, you're going to have to solve that problem. There are already papers on like training a single navigation policy from Sergey's group. My group has work on that as well. It's coming. It's easier to study in simulation at first, obviously, like other things. I will challenge this claim. I'm now tracking at least 4 or 5 humanoid robotic startups or / efforts And if you talk to those people, they will give you their argument, their like 30-second pitch for why humanoid robots. And that pitch usually goes, if you want assistive robots to operate in human environments that are designed for humans, then they must have human form factors. You have to be tall enough to seize things on the shelves where humans have put them. You have to have arms and dexterous hands to open doors and drawers that have been constructed for humans. And their argument is that the only reason why people shy away from humanoids is because people believe the hardware isn't ready and it's not safe yet. It will fall on people and it's expensive. And that's the premise that they're trying to change. They will build hardware, they will provide the capabilities, and then people's bit will flip about that capability. So I'm obviously not bought into that enough to quit my job and go start a startup on humanoids, but it's a reasonable hypothesis. Like, it could be true. Humanoids could be coming.
Just add one thing. I think that, okay, let's say if we go back 20 years or 10 years, and then humanoids, I mean, there were these Asimo and various of these humanoids, and he looked at them and they seemed like, okay, so many man years of effort, you get this very clunky, stodgy looking thing, which you get one demo and then, where is it going, right? There was a reason why people were like, had an antipathy to those humanoids. But the point I made earlier in my talk, which is that some of the dislike for this was because we were using a certain kind of technology. You were building those humanoids with your classic control theory stacks and so on, right? I think that the technology that we have now is different. And this means that this is not your grandmother's humanoid, basically, right? I mean, it's not your that's perhaps the wrong analogy, wrong phrase, but basically it's not the same style of humanoids as, we saw it like 10, 20 years ago, and we thought, this is not the way to do it. It's best to not be anthropomorphic. So I feel the argument is robots are going to be really effective as a domestic robot in particular. Robots have to be in a space which has been optimized for humans, right? Now, outdoors, there can be tasks like, when we have construction machinery for building a building, okay, we don't care, right? But a lot of the stuff for a domestic robot, which is the branch of robotics that I'm most interested in, the home environment is optimized for human convenience. And therefore, a human assistant will in many ways be like that.
So one aspect of this, like you mentioned, is really like the use case, right? The task that is going to be used in, the environment it's going to be used in. The question I was asking is more about, does this now, does the humanoid form now unlock this new sort of data, which is you're literally collecting from humans? So is that the requirement for scaling? Or do you think the other future, which I mentioned, which is start at Roombas with arms and then scale up that way, that's like the more likely sort of future?
Difficult to make predictions, especially about the future.
I can throw one thing out there, which is, it depends on what goal, what level of goal you're shooting for. But if you want to have a humanoid robot that can kind of walk around and kind of do some things and is maybe useful in, less structured factories, or maybe can do a subset of things in the home, like in very certain types of conditions can, do a useful chunk of your dishes. And of course, like Roombas sell and they can't actually vacuum everything, but people still buy them. Then I think, maybe just scaling up, making 1,000 or 10,000 of a specific sort of style of design of a humanoid might be enough. But I do think that if you're actually trying to shoot for true, like, embodied human level intelligence, I think that thing will need to be capable of rapidly adapting to any new embodiment. And I think this is just somewhat inevitable, even just because of if you ever want to change the design of your humanoid, even just make it shorter or taller, or make one of the actuators stronger, et cetera, that might be close enough to your previous designs that you can kind of adapt. But I think that the human mind is capable of just sitting down at joysticks and kind of controlling anything that we're looking at, you know, very quickly understanding the mechanisms and being able to achieve good levels of control in a lot of different settings. I think this sort of like rapid, you know, almost zero shot, or, you know, few shot really adaptation to new embodiments, I think that's kind of what we need if we need like a true embodied human level intelligence.
Great. Yeah.
I think I'll agree. I think the answer won't be that. I mean, I think that my prediction is the answer would be that we learn how to do trainings across embodiments or adaptation, as Peter's saying. I think that would probably be the likely way it goes, but we don't know.
Anyone? I think that's a very good concluding question. Anyone has some concluding remarks on what's the future? Yeah, what's next? No? Okay. Okay. I think that's the end of our panel. Yeah. Yeah.
Yeah. All right.
Thanks to the organizers for putting this together.
Yeah, thank you so much for coming. And I know that we already passed time, so I'm just going to be really quick, 2 minutes remark. First, thanks for all of you for coming here today for this workshop. I think there's a lot of fruitful and insightful discussions. And thanks for all the speakers and poster presenters and also panelists and to join us today, and really enjoy all the other discussions. And also like our co-organizers and Kai-Chun and Christian Dieter, who cannot make it today, and they already also contribute a lot to the success of this workshop. We recognize that like some people do not get to enjoy this in-person event due to visa constraints, and also we got some video conferencing issues, and I think based on Chatundra's prediction, we're going to solve 3D vision years earlier than solve video conferencing. So we're going to try to be inclusive and follow up with speakers, and to see to try to put as much materials and talk videos online, and so that so for people who cannot join today to to kind of enjoy them later after the conference. And also I want to just do a special shout out to Zhen Yu, my student, who really spearhead all the organizing effort. You know, so I think so in the room, most of people know how your student does all the hard work, and then the advisor got to travel to nice places. So that's what happens here. So yeah, so thanks so much. And I think that's all for today. Yeah, enjoy the rest of our conference.